Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditation. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology, over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely
Check, sound check, sound check. Okay. Sound check, sound. Right. Good morning, ladies and gentlemen, and welcome back to the second day of the 2020 11th International Conference on Thermofluid. On the first day, we have had three amazing presentations from our keynote speakers, Professor Sutrisno from Universitas Gadjah Mada, Professor Gus Nathan from University of Adelaide, and Professor Wolfgang Polivka from TU Munich. Besides having the privilege to attend outstanding presentations from our keynote speakers, we've also had two sessions of the paper presentations with renewable energy and energy harvesting on the first session and fluid dynamics on the second session of yesterday's conference. For today, I'm glad to inform you that we have a very exciting lineup as well, because we are going to have two keynote presentations. They're of course going to be very interesting and very insightful. The first one will be delivered by Associate Professor Muhammad Aziz from the University of Tokyo. And then the second one will be delivered by Professor Nicholas Hutchins from the University of Melbourne. These sessions will be moderated by Mr. Den Darlianto for the first session and Mr. Indro Pranoto for the second session from Universitas Gadjah Mada. Afterwards, we will also have paper presentations from several researchers and academics with the topics of fluid dynamics on the first session, and the topic of heat transfer and phase change, combustion and automotive engineering, and thermodynamics and energy conversion on the second session, as well as the topic of multi-phase flow and fluid dynamics on the third session. The paper presentations will be moderated by Mr. Rian Anugrah on the first session, Mr. Agung Bramantya on the second session, and Mr. Arif Widyatama on the final one. So of course, we have plenty to be excited about at today's event. So now, allow me to jump straight into the first keynote presentation that will be delivered by Associate Professor Muhammad Aziz from the University of Tokyo. And before that, I would like to introduce the moderator for today's first session. It will be led by Mr. Den Darlianto. So for the first session, I believe we already have Mr. Den Darlianto with us. Mr. Den Darlianto, can you hear my voice?
Okay, no problem. Good.
Okay, so I'll just hand it over to you, sir. Good luck, and the time is yours.
Okay, thank you very much, Mr. Chairman, for the time. Good morning, everyone. Welcome to the first session of a keynote talk today. For this session, we have Dr. Muhammad Aziz from the University of Tokyo. He is an associate. He is an associate professor in the University of Tokyo. First of all, please allow me to introduce Dr. Muhammad Aziz to you. Dr. Muhammad Aziz received his PhD, Master, and Bachelor from the Kyushu University in Mechanical Engineering. He has quite a lot of professional experience, started from project researcher in 2009 until 2011 in Tokyo University. And finally, he is an associate professor in University of Tokyo now. As a scientist, Dr. Muhammad Aziz has already received quite a lot of scientific research awards, include such as the University of Tokyo Young Excellent Researcher in 2018. And then he has also received the Japan Institute of Energy Award for encouragement in 2014. Presently, Dr. Muhammad Aziz has already published around 118 peer-reviewed journals paper, and then he has already received one patents, and he has already published around 21 book and book chapters. As we know, Dr. Muhammad Aziz also how to say, he is also journal editor. He has also quite a lot of journal editor experiences. Ladies and gentlemen, we will not waste our time for just for the introduction. Now I would like for Dr. Muhammad Aziz to start your presentation. Dr. Muhammad Aziz, time is yours now. Thank you very much.
Okay, thank you very much, Dr. Dinarlianto. Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. Sorry, I just would like to share my slide first. Let me, okay. Could you see my presentations slide?
Yes, perfect.
Okay, thank you. And also my son, I think it's really no problem, I think. Okay, thank you very much. It is really my great pleasures and also my great honors to join with all of you today, and also to deliver a topic related to hydrogen utilizations, because it is one of our expertise in our laboratory. Okay, and today talk entitled Advanced Developments in Hydrogen Storage and Utilizations. And I am Aziz from the University of Tokyo. As the background of, or as the introductions of today's talk, I just would like to underline about the importance of three pillars in our energy systems when we are talking about the sustainability in the futures. And the first thing, when we are talking about this kind of three pillars, we are dealing with energy security, we are dealing also with the energy equity, and the third one, this is also very important when we are dealing with the sustainability or environmental itself. And okay, when we are talking about the energy security, we are not only talking about the energy in terms of its quantity, but the important thing also is that we are dealing with the energy quality. With the energy quality, it means that because energy, it means that the correlation between the demand also with the supply. When we are talking about the energy quality, it means that how far we can have any kind of responsive balance between the supply and also with the demand, especially when we are talking about the electricity or etc. And the second one is related to energy equity. It means that we are dealing with any kind of opportunity. What kind of opportunity that we can give to the society? So all the stakeholders or the players in our society, they can behave simultaneously as producers and also as the consumers at the same time. So it means gives the opportunity, the equal opportunity to all the stakeholders, and also would like to optimize or maximize the renewable energy resources in the futures. And the third one is also dealing with the environmental sustainability. When we are talking about the environmental, it means that how far we can reduce any kind of carbon dioxide emissions, and also several dangerous gases, including NOx, SOx, or etc. Or in this case, also how far we can also improve our decarbonizations from in our society, including the idea that how we can move from carbon-based fuel to non-carbon-based fuels. And when we are talking about the energy transitions, I've mentioned before, the main idea is that how far we can move from the carbon-based fuel to non-carbon-based fuels, or other words, we can say with the decarbonizations. There are four different energy transitions, several issues that we can have today. And the first thing is that decarbonization in the electricity sector, because the electricity sector is one of the biggest CO2 emitters, as we call it now here. It's about 48% of almost half of our emitted CO2 is coming from our electrifications. And the second one is related to decarbonizations, but in non-electrified sectors. And the third one is related to the energy productivity. It means that how far we can improve our energy efficiency, energy productivity, or etc. And the last one is in case that this kind of three scenarios cannot be established well, we don't have any other options. So it means that we need to clarify the scenarios, the scenario that can minimize the CO2 emissions in to our atmosphere. And this is the frameworks in our energy sustainability. As we could see over years that in the short term, it means that until about 10 or 15 years in the futures, we are focusing on the energy efficiency and also how far we can have any kind of clear scenario related to the low carbon technologies and also the introductions of renewable energy. Some countries are focusing on these issues. Okay, and at the second stage, which is about the midterms, we are focusing on maybe longer than 20 years or maybe 50 years in the futures, how far we can have any kind of zero emission targets. Some countries, including Japan and also United States, with the new presidents, actually, they have declared in 2050 about their commitment to have any kind of zero emission scenario in 2050. And for the long term, it is more than 50 years in the futures. It means that we need to have any kind of more dependent and more resilient society related to the energy issues. So in this case, how far any kind of society and another community, they have any clear scenario, how far they can supply by themselves, and also they can consume their energy that have been produced by themselves itself. And in case there is any kind of surplus energy in this one society, maybe this kind of surplus energy can be delivered to any other societies, neighboring societies. And actually, in our history, we have minimally 3 different energy transitions, starting from about 18th century, when it has been started with a industrial, what we call that, industrial movement at that time. We are moving from any kind of solid fuels, especially for the coals and also wood, something like that. But unfortunately, when around mid of 19th century, the refinery technology for oils or etc. was improved well. So at that time, the technology to refine the oils actually increased. So there was any kind of a shift to the liquid fuels, and we tried to forget the solid fuels. But unfortunately, 1980, 1970, something like that, we faced with the oil shocks. And also from the thermodynamic point of view, we can see that the gaseous fuels leads to more exergy efficiency compared with any kind of solid and also liquid fuels. So in this case, when we burn any kind of gases, including methane, including ammonia, including hydrogens, etc., we can have more or higher temperatures of combustions compared with when we burn any kind of liquid fuels, including oil, or maybe solid fuels, including coals or etc. So as the focus of my talk today, I would like to focus on the issue of related to the hydrogens as the potential secondary energy source. Why I am focusing on the hydrogens as the secondary energy source, because it can facilitate to be any kind of energy potential, energy carriers. And the second one also, it can also behave as the decarbonization scenario that I have talked previously. So when we utilize the hydrogens, it means that we oxidize the hydrogen. At the same time, we produce only the waters. So it means that the water is really environmental friendly. So for ourselves, actually, from environmental point of view, actually, this is very, very excellent. So the utilizations of hydrogen also has very wide applications, as we could see over years. It can be used directly for fuel cells and also for combustions, direct combustions, and also co-combustion with other fuels. Recently, there are some research related to any kind of co-combustions between hydrogens, ammonia, hydrogens, methane, and etc. That in this case, the co-combustion with hydrogen, it means that we would like to improve the combustion's performance, like including the flame speed, temperatures, or etc. But unfortunately, the problem with the hydrogen is related to its volumetric energy density. Although the hydrogen has very high gravimetric energy density, but unfortunately in the gaseous state or in atmospheric conditions, its volumetric energy density is very low. It is only about 3 watt-hour per liters. And this is the problems, it becomes the problems in hydrogen storage and also utilizations. And this is the big scenario for our futures. In our futures, actually, we are not figuring out that we will have any kind of energy trade in forms of carbon fuels, but maybe in the future we are we would like to have any kind of energy trade in forms of non-carbon based fuels, including hydrogens, ammonia, or maybe electricity itself. And this is the big pictures that we have in our lab, in our laboratory in our university. As we could see over years, we are focusing on how far we can have any kind of mutual conversion, mutual dialogue between the amongst the secondary energy sources, including the electricity and also any kind of other chemical energy sources, including hydrogens, ammonia, or etc. As I mentioned before, that the decarbonizations or shifting to any kind of non-carbon based fuel is very important in this case. So in our study, in our lab, we are not focusing anymore to any kind of methane productions or methanol productions. But in this case, we are focusing on non-carbon based fuels over years, which is hydrogens, ammonia, or maybe etc. So the main issue in our study is that how far we can improve the energy or the conversion performance from the primary energy sources to any kind of these secondary energy sources, including the electricity and also hydrogens, ammonia, and also how far this kind of secondary energy sources can be mutually converted to each other. Because by having any kind of flexible secondary energy sources, it means that we can facilitate widely both the energy supply and also in terms of energy demand itself. And this is the mutual conversions that we can have related to the conversions among the secondary energy sources. We can depart from any kind of electric powers or electricity itself. But actually, the electricity can be converted to any kind of other secondary energy sources, including chemical energy sources and also the heat itself. But actually, in terms of decarbonization, it means that we can focus on any kind of hydrogens, ammonia, or etc. Other options, when we are forgetting the decarbonization, we can have any other options, including the methane, methanol, DME, or etc. And this is the characteristic of hydrogens. We could see over years, the gravimetric energy density is very high. It is a lower heating value. It's about 120, but for the HHV, higher heating value is about 140. And also for the flame velocity is very, really high. It's about 350 compared with the methane is really significantly high, or about 8 times. Also, the ignition range is also very wide, which is very, very advantageous for us. And also from the safety point of view, we can see over years that the auto ignition temperatures of the hydrogens is very, very significantly very high compared with the gasolines. So it's about 600 degrees Celsius, which is in case that there's any kind of leakage to the atmosphere from any kind of hydrogen storage or pipelines, it means that the auto ignition temperatures is still, there's any big gap between the atmospheric temperatures and also the auto ignition temperatures. And there are some kinds of research topics for the hydrogen itself, including the conversions, storage, and also the carbon captures, because in case they would like to have any kind of clean or CO2-free hydrogen productions or hydrogen utilization, it means that we need to have any kind of carbon captures scenarios in this case, in case that we would like to produce the hydrogen from any kind of fossil fuels or any kind of carbon-based fuels. And also there are some kind of research rooms in this case for any kind of hydrogen utilizations and also integration with other aspects. And this is the conceptual chart for the hydrogen supply chains in the futures. In case of like Japan's or maybe any kind of consuming countries, including Japan, Singapore, and maybe some European countries, something like that. Our big pictures in the futures is that we would like to import further in terms of in the form of hydrogens or any kind of non-carbon based fuels in the futures, and will not import further the carbon based fuels in the futures. And this is the hydrogen value chains. But as we could see over years that almost today, currently the hydrogen is utilized for refinings, producing any kind of diesels, and also producing any kind of ammonia. But in the futures, I believe that these value chain, that these utilizations will be will shift or will be changed significantly, especially for the transportations and also for the electrifications or for power generations. And so we could see over years that the scenario to produce the hydrogens, replacing the currently adapted fossil fuels-based power generations, it becomes very popular. And the price of the or the cost of the hydrogen-based power generations will be quite competitive in about 2035 or 50. And in this case, in case that we adopt many renewable energy sources in the futures, it means that there will be any kind of surplus energy or surplus electricity. So we can produce the hydrogen from this kind of surplus electricity, including the wind, PV, or etc., and store this kind of energy in the forms of hydrogens. And this is our study related to the potentials of our hydrogen adoptions in the futures. We could see over years. We are comparing. This paper is still being submitted, but as we could comments and also the GDP related to the power parity purchase and also related to the research developments index. As we could see over here, when we compare between Indonesia, Malaysia, Brunei Darussalam, and also some consuming countries, including Singapore, Japan, and South Korea, we could see over years that Indonesia, unfortunately, although we have quite high in domestic energy per capita currently, but unfortunately, when we figure out in the futures about 2030, 2040, something like that, as our population is increasing and also our economic growth is increasing, the demand per capita will also increase. So it means that we would like to produce any kind of hydrogens in this case and export this kind of hydrogens to any other countries. Our capacity or our availability maybe will be getting down in the futures. And also, unfortunately, for the Human Development Index and the GDP or power purchase parity, we are quite low over years. And when we compare with Singapore and Japan or maybe Australia, actually these kind of countries, they have very strong Human Development Index and also GDP and also Research Development Index itself. So it means that the adoptions of hydrogens in the futures maybe will be quite easy to be adopted in these countries in the span of about 10 until 20 years in the futures. And this is the roadmap of hydrogen technology. Actually now we are entering, we are still dealing with the second one, with the second stage of building infrastructures. This kind of scenario will be quite different from one country to another country actually. But in case of several countries, including Japan, United States, Germany, Korea, actually what we are focusing today is that we are still building the infrastructures. So we are not still, focusing related to the hydrogen economy itself, but now we are still building the infrastructures and how far we can achieve the hydrogen economy. In our targets, at the big initial target, actually, we would like to have any kind of hydrogen economy in 2030. But I think it is really difficult to achieve that in 2030. So it means that we can extend further in 2040 or maybe in 2040. And this is several hydrogen methods for and also the density available. As we could see over years that there are several methods for storing the hydrogens, including the hydrides, whether it's in kind of liquid hydrides and also metal hydrides. And also we can have any kind of absorptions by any kind of activated carbon or etc. And also liquefactions and also the compressions. But when we are talking about the storage, it means that we are dealing with both volumetric energy density and also gravimetric energy density. And so what we are targeting is that we would like to have both gravimetric and volumetric densities. They are quite high over years. So we are targeting for adopting this kind of technologies, including liquid hydrogens, ammonia, or also etc. There are some required technologies and characteristics for hydrogen storage and also transportations, actually, including the materials, including the standardizations, monitoring, or something like that. But until today, actually, for the storage and transportations, we are still would like to establish this kind of standard and also what we need for our futures. And also for utilizations, actually, there are still many rooms or wide rooms for developments further including the turbines, hydrogen combustions, in case that we would like to combust directly the hydrogen itself, or maybe we would like to co-combust the hydrogens with any other fuels, including the methane, including the diesels, including the ammonia, or etc. And also, this is our study related to the potential routes of storage and transportation for the hydrogen itself. We were comparing between the liquid hydrogens and also the storage of hydrogen in the form of methyl cyclohexanes over years. Methyl cyclohexane means that we are storing the hydrogen in the forms of liquid organic hydrogen carriers. So we are forming the toluene. The toluene is reacted with hydrogens, forming the methyl cyclohexanes. And the third one also, we have scenario of ammonia. It means that we produce the ammonia first, and then we utilize ammonia directly, or we release the hydrogen from the ammonia initially, and then we use the release of hydrogens for any other purposes. When we are comparing between the liquid hydrogens and also methyl cyclohexanes and also the ammonia, as it is shown over years, the hydrogen density in terms of gravimetric energy density, okay, liquid hydrogen is very high. But unfortunately, when we are talking about the volumetric energy density, as you could see over years, ammonia shows very high volumetric hydrogen density, although compared with the liquid hydrogen itself. Ammonia has about 12% volume percent of hydrogens, compared with the liquid hydrogen, which is only about 7%. It is quite low. So it means that when we need to store the hydrogens in ammonia, in 1 liter ammonia, we can have about 10, more than 10% of its ammonia can store the hydrogen itself. But the problems with this kind of liquid methyl cyclohexane and also ammonia, actually, for the liquid hydrogen, actually the problem is related to the liquefaction itself, because the liquid hydrogen, it means that we need to cryogenically it means that we need to have any kind of cryogenic process to convert the hydrogen from its gaseous state to any kind of a liquid state. But unfortunately, the temperature is very low. It is about minus 253 degrees Celsius. And the energy to reach this kind of temperatures is very, very huge. And also the second problem with the liquid hydrogen is that there's any kind of formation change, or atomic change from the ortho to para hydrogens. So it means that when we liquefy the hydrogen from gaseous state to liquid hydrogens, the liquid hydrogens will be in ortho conditions. But as the times passes, this kind of liquid hydrogens from the ortho conditions will be changed to any kind of para hydrogens. And these will be followed by any kind of latent heat loss, because there will be any kind of heat loss from during the conversion from ortho to para hydrogen itself. So usually there will be any kind of the phenomenon of boil off. The boil off problems, it means that some kind of liquid hydrogen is converted back to any kind of gaseous hydrogens. And for the toluene or methyl cyclohexane process, the problem with this kind of hydrogen storage is related to the hydrogen release or any kind of decompositions or dehydrogenations of hydrogen from methyl cyclohexanes, because it needs very huge heat to release the hydrogen from methyl cyclohexanes. And also for the ammonia, as we could see that ammonia, the process to produce ammonia basically based on the Haber-Bosch process, which is really quite established well. But the problem is that when we would like to release the ammonia or decompose the ammonia, it means that also we need a huge amount of energy to release the hydrogen from ammonia. But actually the ammonia also can be directly utilized. So it means that we don't need to release the hydrogen from ammonia. But unfortunately, the utilizations of ammonia will be quite limited compared with the hydrogen itself. And also in terms of energy efficiency and cost, we could see over here that when we would like to store the hydrogen in the form of ammonia, and ammonia is directly utilized, in this case, we figure out to utilize ammonia for direct ammonia-fed fuel cells. We can have the total energy efficiency, the highest total energy efficiency over years, which is about 37, or maybe in the future we can improve to about 40 or 45%. And so regarding the cost, also actually the ammonia with direct utilizations also shows the lowest cost or hydrogen price, which is about 20 cents. And this is the scenario to store the hydrogens in form of ammonia. As we could see over here, as I've mentioned before, that ammonia has very high hydrogen storage capacity in terms of both gravimetric and also volumetric hydrogen density. And also the ammonia can be produced directly. In this case, that it can be used for the direct combustions for the boilers, and also for the generators, refrigeration fuel cells, and also it can be used for the spark ignition engines, and also maybe in the futures, maybe we can have any kind of gas turbines using the ammonia itself. But unfortunately, ammonia also has a limit in this case, actually, because the flame speed from the combustions of ammonia is quite low, and also the combustion temperatures is quite low. So it means that the exergy, from the exergy point of view, the efficiency will be quite lower compared with when we combust or when we utilize directly the hydrogen itself. This is our study related to how far we can improve the ammonia productions or the performance during the ammonia productions. In this case, we adopted the enhanced process integration technology, which was proposed also in our laboratory. And we combine between the air aspirations unit with the Haber-Bosch process, also with the power generations. From our study, actually, we can reduce or we can achieve very high energy efficiency. In this case, that for the nitrogen productions, we can have about half of energy consumptions compared with the conventional nitrogen productions. And so for the ammonia productions in total, we have quite high energy efficiency in total, which is about 60%. And also we have also study related to the direct carbon to ammonia production cycles. So in this case, we develop any kind of thermochemical cycle. So in this case, we don't need to produce the hydrogens, and also we don't need to produce any kind of special fuels like gaseous fuels or etc., like the methane or etc. in this case. So we can use the carbon-based fuels in this case, and the carbon-based fuels is reacted with the nitrogens directly, and we can have any kind of thermochemical cycle over years. The thermochemical cycles that we have today, actually, it has two different reactions. The first is reductions, and the second one is oxidations. In these reductions, we react the aluminum oxide with the carbons and also with the nitrogens, and we produce aluminum nitrate. And as we could see at the second oxidations, the second reactions, which is the oxidation itself, we have the reactions of aluminum nitrate with water, and we produce the alumina and also with the ammonia. And ammonia is separated, and on the other hand, the alumina is returned back to the reductions reactor. From our study, actually, this kind of direct thermochemical cycle to produce the ammonia from any kind of carbon-based fuels is quite promising, although the problem is related to the temperatures. Unfortunately, to decompose or to reduce the aluminum oxide over here, or alumina actually, we need very high temperatures, which is about 1,500 degrees Celsius. And it is very challenging. So our homework is that how far we can improve further this kind of performance and also lower the temperatures. And actually, we need to have any kind of mild and also lower thermochemical cycle for direct ammonia production from any kind of carbon-based fuels. And related to the hydrogen applications, we have several options for hydrogen applications. In this case, I am not mentioning the hydrogens utilized for any kind of passenger cars, because I believe that for the passenger cars, the electric vehicles will win. But unfortunately, for any kind of large-scale transportation sector, including train, buses, etc., or maybe for the aviations, including the plane, airplane, or etc., the hydrogen is quite promising compared with the electricity or electric vehicles itself. So also we will have any kind of shape, we will have any kind of power generations, which is for the power generations in the future. I think this is also the most promising one for hydrogen's utilizations. And actually the hydrogen is ready for scales, for utilizations. We can have several different utilization, including the power generations. Although now the problem is that the cost for power generation utilizing the hydrogen is quite high. In the futures, how far we can reduce and make this kind of power generation from hydrogens to be competitive. I think that's our homework for in the futures. But for the transportation sectors, this kind of hydrogen-based vehicles, actually their performance are quite competitive with any kind of conventional cars. And also there are another option for hydrogen's utilization, including industry productions, industrial utilizations, and also building or heating or etc. Okay, I would like to skip this slide. And this is the integrations of hydrogens in power and gas grids. It is very important because in the futures, currently actually the adoptions of hydrogen is very limited. As I mentioned before, only for the ammonia productions and also for the refinery to produce any kind of diesel or etc. But in the futures, this kind of utilizations will shift. There will be any kind of big shift or big change in this kind of hydrogen utilization in the futures, especially for transportations and also for power generations, including also for the industrial end users and also the end user or residential end users. And this is the power to gas scenario, but unfortunately in Indonesian case, maybe are not dealing strongly with this one. In several countries, including the Germany, actually they are quite strong for developing the scenario for power to gas. As we could see that like in Germany, there is a huge wind power in the northern part of Germany, but unfortunately the grid or the electricity grid to deliver the electricity generated from the northern part of Germany to the southern part of Germany is very, very limited. So the power generated in northern part of Germany cannot be delivered well to the southern part of Germany. So currently, the main idea is that how far we can change, how far we can convert this kind of surplus electricity from renewable energy sources to any kind of gaseous fuels, including methane, also hydrogens. And these kind of hydrogens and also methane can be injected to our gas pipeline, so it can be delivered to the consumers. And this is the direct fat ammonia SOFC. But I think I just would like to skip it. And also this is also the technology, is quite new technology to utilize directly or to combust the hydrogens directly. Because when we would like to combust or utilize or oxidize the hydrogens, it means that we produce the water. So the behaviors of the turbine itself will be quite different from our conventional gas turbine or maybe steam turbine itself. So in this case, we will have any difference curve, which is the curve, which is very, there is any spike, very high spike over years, about the temperatures about 1,500 degrees Celsius over years. And the teams in the Graz University, actually, they have developed what they call as the Graz cycles. So in this case, actually, they combust the hydrogens, they oxidize the hydrogens directly with the oxygens. So they need we need any kind of oxygen separations over years before the combustions. So we oxidize the hydrogens to produce very high temperatures flames over years. But unfortunately, although the combustions of hydrogens can reach the temperatures of about 2,200 degrees Celsius, but when we are talking about the turbines, especially related to the materials of the turbine itself, the temperatures for the turbine inlet usually limited to 1,500 degrees Celsius. And some part of the produced water in the Graz cycles is then returned back to the combustions to the purpose of these recycles are including. The first is to reduce the temperatures and also to improve or to increase the heat capacity of the gases entering the turbine itself. And this is also the integrated ammonia decompositions and also hydrogen combustion technology that we develop in our laboratory. We develop any kind of packet bed membrane reactor to decompose the ammonia and at the same time also to separate the produced ammonia and the separated hydrogens, sorry. And the separated hydrogens is then combusted with the air. It is quite different with the Graz cycles because we don't want to have any kind of oxygen separations, which is quite also energy intensive. So in this case, we would like to combust the hydrogens with the air itself. And we have combined cycles over years consisting of turbines or Brayton and also with steam or Rankine cycles. And from our study, we can have quite high energy efficiency in total. The efficiency of about 44 or 45% can be achieved in our study. But unfortunately, also we will have several different catalysts to decompose the ammonia itself. In case of rutheniums, yeah, although it is very costly, the energy efficiency can be very high, but maybe we can use or adopt any kind of lithium-based catalyst or maybe nickel oxide-based catalyst. And this is the South Asian countries' characteristics and challenges. Actually, for the characteristic itself, we have many problems with technology mastery. Yeah, because as I mentioned before, that in our study, including the GDP, including the Human Development Index, including also the R&D to develop the hydrogen technology itself is quite low. So, but on the other hand, actually, we have a huge potential for low-grade fuel or low-grade fossil fuels or etc., including the brown coals, including lignite, and also in any kind of industrial biomasses, agricultural biomasses, or etc., which is this kind of fuels are very promising to be converted to hydrogens first, and then hydrogens can be sold or can be exported to other countries. And also for the storage itself, because our characteristics are basically we are distributed. We are spread by any kind of oceans. We have many islands or etc. So it means that we need to develop any kind of storage which is matching with our conditions our geographicals, our social conditions, or etc. And also for utilizations, also we are dealing with the social acceptance. The problem is that related to the Human Development Index, how far our society can accept, can receive this kind of new technology related to hydrogens, and also to move or have any kind of paradigm shift in their thinking related to moving from any kind of fossil fuels to any kind of new hydrogen fuels, or etc. And this is also the example of scenario in our energy sectors, especially in Indonesia. We can have any kind of hydrogen production from different potentials, resources, including the natural gases and also lowering coals, and also industrial agricultural waste. And for the storage, I believe that liquid hydrogens and also ammonia is quite promising to deliver and also to distribute the hydrogens to our domestic consumptions or domestic users. And so for utilizations things, because we still have any kind of conventional power plants, it means that we need to have or maybe we can still maintain their existence. So in this case, we can have any opportunity to have any kind of co-combustion technology or to co-combust together with any kind of existing fuels, including coal, including diesel, or etc. Thank you very much for today, actually, and I would like to return back to Dr. Darlianto. And if you have any questions or maybe discussions, it is my pleasure to talk with all of you today. Thank you very much. Assalamualaikum.
Waalaikumsalam. Thank you very much, Dr. Aziz, for the very nice presentation regarding the scientific and technology development of hydrogen power and hydrogen energy. Ladies and gentlemen, now we have the time for the question and answer sections. I invite you to write down if you have any questions, I invite you to write down your question in Q&A box. Dr. Aziz, we have 15 minutes for discussion now. So we have two questions from the Q&A box. First, I would like to read the question from Fauzi Arsad Hendrawan. He would like to ask you about in order for widespread use of hydrogen, for example, in a certain country, you mentioned about how we need to facilitate production, storage, and the utilization itself. The question is, how expensive would it be in terms of operating of facilities, infrastructure, and could you estimate the break-even point of the investment, especially in Indonesia? And this is the first question. The second question is from Mr. Akmal Irfan Majid from Gajah Mada University. The question is, considering hydrogen adoption curve and hydrogen technology roadmap that you saw for us, where is the current Indonesian position and how to improve hydrogen adoption level? What do you think about the most feasible hydrogen development scenario for Indonesia? On the other hand, also, the third question will be the last question from the Q&A box. In slide 27, hydrogen production from alumina redox cycle, I presume that the high reduction temperature was required to break the aluminum oxide layer in aluminum Al2O3. Did you investigate the catalyst or reacting agent to increase the reaction kinetic? I think that is the question from the audience today. Now I will let you to explain your answer for those three questions. Thank you, Dr. Aziz.
Okay, thank you very much. And also, I just would like to answer the questions. The first thing is the first question is from Mr. Fauzi, actually, related to the how expensive the infrastructures or maybe the break-even point. Actually, until now, actually, there is no clear study related to this issue. although in Japan, actually, we don't have any data related to this one. Although new energy development organizations, NATO itself, they set up the scenario for this case. Okay, they set up the cost of hydrogens in the futures in 2030 is about 20 yen per kilowatt hour. Yeah, to produce the hydrogens, which is quite competitive with the conventional power generations, or 20 yen.
$20, yeah.
20 cents. So it is about 20 yen.
20 yen.
Yeah. So actually, this is the targets set by the NATO itself. But actually, practically, we as the researchers from our study itself, when we are focusing on adopting any kind of conventional technology, and yeah, it really depends on the technology for the storing, transporting, and also to utilize the hydrogen itself. In our study, as I have shown to you previously, actually, the cost of the hydrogen itself is maybe in 2030 is really difficult to achieve this kind of NATO targets. But in 2050, when we have any kind of further technological developments, including any kind of technological options, including the storing technology and also utilization technology in this case, actually maybe we can achieve this kind of targets with its 20 cents dollar or 20 yen itself. But in case of Indonesia, I think we need to further study related to this one. We have, yes, actually, we have, as I mentioned before, also actually we have potential resources which can be converted to hydrogen itself, like for the brown coals, or like for also any kind of industrial waste, including maybe any kind of palm waste, including also pepper milling waste, black liquor, etc. Actually, this kind of waste, and also this kind of low-grade fuels, actually their price are really quite low. So it means that when we can adopt this kind of almost free fuels to produce the hydrogens, maybe the price of the hydrogens can be reduced significantly. Okay, for the conversions technology, in this case, actually, when we compare between the like combination of gasification, shift technology, and etc., and also with any kind of direct electrolysis or etc. Currently, actually, maybe these kind of direct electrolyzations may be quite competitive. But actually, for the large scales in the large scale hydrogen productions in the futures, maybe we would like to produce on how far we can have any kind of direct hydrogen productions. So in our scenario also, we are now studying related to the chemical looping technology, although it is not well-established technology. But we hope that by adopting this kind of technology, maybe it is now actually there are some pilot plans for the chemical looping technology, but maybe we can figure out for the application for the chemical looping technology still about 10 or 20 years in the futures. And we are figuring out that this kind of chemical looping technology can be applied in 10 or 20 years in the futures. Maybe we can reduce the price or the cost of the hydrogen productions significantly. And also for the productions, for the utilizations, actually, we can, the most, I think the lowest cost is that we directly combust the hydrogen itself, or also we can co-combust the hydrogens with our existing power plants, including the coals, the diesels, or maybe with the oil itself. And for the second questions from Mr. Majid, actually, considering the hydrogen adoption curve, okay, the positions of Indonesia, I think, still in the introductions one, in this beginning state of introductions itself. Yeah. Because as I've has shown to you related to the potential of hydrogen adoptions, that the problem is that our human development index, and also our power parity purchase, and also our R&D related to the hydrogens are still very low in this case. So actually, like when I'm referring to Japan's case. Actually, in the Japan's case, we started from about 1990, so about 30 years in the back and the past actually. So when we are trying to move to apply the hydrogen society in Indonesia, although we can bypass this kind of technologies and also scenarios, I think we still need about 10 years to start or to initiate. Okay, from 2020 or 2025, maybe we can initiate this kind of introductions. But this kind of introduction maybe we can take about 10 years, another 10 years, something like that. So the building infrastructures also maybe will be started in 2035 or 2040. But also it really depends on how far these other technologies, like including the transportation, including the demand itself, is adopted in the futures. In case that there will be any kind of huge demand to use the hydrogen for transportations or etc., maybe our scenario will be fastened. But unfortunately, when there is no big demand related to the adoptions of hydrogen itself, and we follow this kind of trends in the futures, maybe we can start the building infrastructures in 2035 or 2040, and for the hydrogen economy maybe after 2050 or after 2060. And related to the second questions related to the redox cycles, actually, yes. The problems with the alumina-based redox cycles is with the temperatures. 1,500 degrees Celsius is really quite high. Although we can have it, because currently, actually, for the combustion technology, we can have about 1,700 and also almost 2,000. So from the reactor designs, it is quite possible. But unfortunately, this kind of high temperatures also becomes the problems related to the further utilizations and also further applications. So in our study, as you mentioned also in your questions, is that also we have any other scenarios to lower down these kind of temperatures. But we still focus on the thermochemical cycles, because thermochemical cycles in our scenario, it can or it is feasible to directly convert the fuels to the ammonia. So now we would like to adopt any kind of nitrate-based materials to convert the fuels to any kind of ammonia directly with the working temperatures of about 300, 200, 300, or for the maybe about 400 maximally for the operating temperatures. But yeah, unfortunately, this kind of research, we don't have, we still don't have any kind of pilot plan for this kind of nitrate-based thermochemical cycle for producing the ammonia. Okay, thank you very much, Mr. Majid and also Mr. Fauzi, for your very nice questions. Dr. Dean, I think your mic is still muted.
Thank you very much, Dr. Aziz, for the very nice answer for the three questions that mentioned by the audience. Basically, we have 10 minutes more for discussion, and I have already see the Q&A box, and we found two questions from the audience. The first question come from the Dr. Joko Waluyo from UGM. The question is, the challenge for the implementation hydrogen for the future is regarding to hydrogen technology as well as material science. Since it has high working temperature. The question is, any bridging approaches for solving this contrasted challenge? This is the first question. The second question is come from the YouTube from Mr. Sunario. He would like to send you a question regarding is there any technology that already have been capable to convert the biomass or waste to hydrogen, and which technology possible to develop in Indonesia? Dr. Aziz, we have two questions from the audience, and I think you can start your answer for the question.
Okay, thank you very much. For the first questions from Professor Joko, actually, it is, as I've mentioned before, also related to the hydrogen utilizations. Oxidations of hydrogens can be conducted at very high temperatures. Okay, theoretically, it is about 2,500, but practically, when we are dealing with any kind of lower heating value, water productions, or etc., the practical, the maximum practical temperatures for hydrogen combustion is about 2,200 degrees Celsius. But yes, when we combust the hydrogens directly, and we would like to use this kind of exhausted gases from the combustions, we are facing with the material problems, we are facing with any kind of other issues. Yeah. Okay, until now, so that's why any gas cycle technology it was proposed in this case. The gas cycles, okay, the combustions or the oxidations of hydrogens with pure oxygens can achieve about 2,200 degrees Celsius. In gas cycle, the principle is that they lower the temperatures to about 1,500 degrees Celsius, and then they expand the exhausted gas with using the turbine itself. But in the futures, when we are figuring out the turbine technology, like the G class of turbine itself, the G class of turbine technology now is operating at 1,700 degrees Celsius. So in the futures, when we can have or when we can adopt this kind of G class turbine technology, 1,700 degrees Celsius, I think the exergy loss from hydrogen combustions until it can be expanded at the turbines will be quite minimized. So from 2,200 degrees Celsius can be the gap, which is the conventional technology, the gap is about 700 degrees Celsius, can be minimized to about 500 degrees Celsius. But in our mind, it is very important that there is still any exergy loss or exergy loss from the combustions to the utilization itself. Okay, and the second question is from Mr. Sunario, related to the energy technology to convert the biomass or waste to the hydrogen. Yes, there are some technologies available today. Yeah, especially the gasification itself. The gasification itself is really quite established technology. So the problem is that what kind of gasification technology that we would like to adopt, whether we would like to adopt any kind of partially oxidized gasifications, or maybe any kind of steam gasifications, or etc. But basically, the products of the gasification itself is syngas, synthetic gas, including the methane, carbon monoxide, and also the hydrogen itself. When we can when we would like to improve the ratio of the hydrogens produced in the syngas itself, maybe we can adopt the steam gasifications in this case. But also, although we adopt the steam gasifications, there is also still part of carbon monoxide and also methane produced. So in this case, we need to adopt another technology after the gasification, which is the water safe technology. In this case, we would like to convert the carbon monoxide to the hydrogens by reacting the carbon monoxide with the steam. And then it produces the CO2 and also the hydrogen itself. And then hydrogens can be separated, whether the separations can be conducted via pressure swing adsorptions technology, or maybe any kind of membrane technology, or etc. And also, as I mentioned before, also chemical looping technology is also quite promising technology, whether this kind of chemical looping technology is paired or is coupled with the gasifications before the chemical looping itself, or the fuel itself can be directly fed to the chemical looping itself. So yes, I think there are some available technologies to convert the biomass from waste or any kind of low-grade fuels. Thank you very much.
Okay, thank you, Dr. Aziz, for the very nice explanation for the questions. basically we have 2 minutes for the left for discussion, and I found there are two important questions from the Q&A box, and then actually I would like to ask you something, but due to the time limited conditions, so finally I should choose one question to be discussed for this session. The questions come from Zulkarnain. Zulkarnain is the gas engineer from the National Gas Company in Indonesia. Basically, he would like to mention you that Assalamualaikum, Dr. Aziz. Thank you for your presentation on hydrogen technology. I would like to ask you about the future of hydrogen fuel usage. And then do hydrogen has a chance to compete with the electricity, especially hydrogen has many sources like such, especially the electricity has many resources from the renewable resources. That is the question from Mr. Zulkarnain. And then I let you, Dr. Aziz, to discuss about the topic.
Okay, thank you very much. And also, actually, there is another question. So I just would like to summarize all the questions together, actually. Related to the opportunity of hydrogens in the future, especially the competition with the electricity. Both of them, as I mentioned before, that both of them are basically the secondary energy sources. And although they are competing, but actually they are mutually converting or mutually supporting to each other. Because what? Okay, in terms of energy efficiency, in terms of convenience, we would like to adopt the electricity. But unfortunately, in terms of energy storage, in terms of also energy security, we cannot lay on the one energy form, which is the electricity itself. So in this term, actually, we would like to have any other kind of energy or secondary energy source in this case, actually, to support the electricity itself. And the problem with the electricity itself is that electricity cannot be stored directly. Okay, we can have any kind of battery, but actually storing the electricity in the forms of in the battery, it means that we convert the electricity to the chemical energy. And the problem with the battery is that it cannot it cannot be kept for long times, about 6 months or 3 months or etc. actually. So in this case, the role of the hydrogens and also the electricity in the futures, they are mutually collaborating to each other. They are mutually convertible to each other, actually. So they are not competitive to each other. In my opinion, this kind of options, I think that's the most the most feasible one for our futures, actually. Yeah, the applications of the hydrogens, the application of the electricity will be quite divided in the futures, including for the passenger cars, including for the large transportation sector, or etc. But I think we need to remap our utilization in the futures, whether we would like to have the hydrogen itself or the electricity. And finally, in the futures, maybe we can have more higher energy efficiency in our total energy systems in the futures. Thank you very much.
Okay, thank you very much, Dr. Aziz. Ladies and gentlemen, actually, I'm sure that we have a lot of questions regarding the hydrogen energy. For example, maybe we can discuss about the how can we handle the leakage problem also, and then the social acceptability will be increased from time to time, and then maybe there are some questions regarding the comparison between liquid hydrogen, MCH, and then also ammonia condition, and we should choose the best way to calculate and then how is the economic viewpoint for the production facility for hydrogen. Meanwhile, I would like to say the time is limited now, and then we should end up this session. And from the viewpoint of our organizing committee, and then on the name of the Thermofluid conference, I would like to provide our high appreciation for Dr. Aziz for the very nice presentation and then very good discussion also for for the Q&A sections. And thank you very much, Dr. Aziz, for your presentation. And let me provide a big applause for Dr. Aziz for the very nice discussion today also. And then hopefully we can meet each other in the other time, in other discussion topic also, even for the special topic for hydrogen presentation in the future. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you so much, Mr. Dendaryanto, as the moderator for the previous session. And of course, thank you as well to Professor Aziz for the amazingly insightful presentation on the possibilities of utilizing hydrogen as an energy source for the future. To Professor Aziz, perhaps if you would like to add more points to your answer, you have that option, and you're very welcome to write your answer in the Q&A section. So you have an option to write your answer if you feel like you need to add more to your points. But otherwise, thank you very much because your presentation, I find it very, very interesting. And for the next session, we will have a paper presentation. In this particular session, it will be around the topic of fluid dynamics. And before we start this session, I would like to welcome our moderator for this session, to Mr. Rian Anugrah. Are you already in the session?
Yes, I'm here, and could you hear my voice?
Right, I can hear you loud and clear, sir. So
okay, thank you.
The time is yours, and you're very welcome to start and guide the session.
Okay, thank you, ladies and gentlemen. Welcome to the next sessions. We will have paper presentations for several presenters. We have, I think, 5 presenters here within the topic of fluid dynamics. And I would like to remind for all presenters that you will have 8 minutes for presentations and also 4 minutes for question and answers. So the first one will be the presentation with the topic far field flow simulation of contra-rotating edge Darius vertical axis wind turbine. So and the presenter will be Mr. Ko. Is it right?
Yep.
Yes. Yes, if you are ready, then please proceed to your presentation. Thank you.
So I believe I've shared my screen.
Yes, it's clear.
So let's start. Hi, everyone. My name is Ben. I'm here on behalf of my team with Cian and Joe and our supervisors Bagus and Ray to present our study on far-field flow simulation of contra-rotating H-Darius vertical axis wind turbine. This presentation is divided into 4 sections, including background, turbine configuration, computational setup of the numerical study, and far-field behavior of the contra-rotating wind turbine. I'll start with background. Vertical axis wind turbine, unlike the horizontal one, has their rotating axis vertical to the ground, like the one in the red circle. It is characterized by this simple overall configuration, independent of wind direction, smaller dimension, and the generator is designed to be on the bottom close to the ground. On the other hand, contra-rotating consists two turbines that are rotating in the opposite direction in the same axis, shown by the back arrows over here. The recent study conducted by Dyden et al. Suggests that contra-rotating could increase the efficiency of the vertical axis wind turbine. They run an experiment with the setup shown in the figure on the right and match a simulation with a simplified structure. The structure is shown in the red circle. It's simplified to consist only turbine blades and PVC tubes, which are pointed from here. And the result is shown on the right. The blue line and the gray line represent power coefficient of bottom turbine and top turbine respectively. And the red line represents power coefficient of the contra-rotating wind turbine. It shows a significant increase in power coefficient, which could lead to a higher output power. This brings us interest as areas near equator often have unstable and slower wind, which makes horizontal axis wind turbine not feasible to deploy. And currently, there are many studies on the far-field behavior of a single vertical axis wind turbine. However, we would like to investigate further to see how contra-rotating is making a difference. Now let's go to turbine configuration. The model we use in our simulation is further simplified from Dyden et al., with PVC tubes being removed and only turbine blades left. The height is 0.5 meters and the radius is 0.4 meters for each turbine, while each blade uses NACA 0025 as airfoil with a chord length of 0.1 meters. The top turbine is rotating clockwise about the positive y-axis, and the bottom turbine is rotating anti-clockwise about the positive y-axis. The RPM data is adopted from Dighton et al., as the experiment is not available for us in the current situation. For the computational setup, I'll talk about the following aspects, include domain, mesh, and solver. Firstly, computation domain for this study is shown here. The inlet and outlet are to have fluid flowing into and out of the domain, a no-slip ground, and the rest being defined as slip walls to allow fluid flowing frictionlessly. While the capitalized R being the radius of the rotating zone highlighted by the magenta cylinder over here, and R being the radius of the wind turbine, the domain is defined large enough to minimize the possible blockage effect. By taking a slice at the top turbine, we could see the overall mesh of the domain. The dense blue region here is the refiner region that allows higher resolution on the far field. Zooming inside this red section, we can see the refiner region with the rotating zone highlighted by the magenta circle and 3 turbines inside. Again, zooming in, we could have a much closer look on the region. And finally, zooming into one of the blades, we could see the mesh refinement around blades with 1 layer added. The bottom turbine is similar to the top turbine, but in different orientation. The final mesh has 90 million cells in total. The refinement region has a mesh cell size of 0.02 meters, and the turbine has a mesh cell size of 0.002 meters. We perform simulation with OpenFOAM and use K omega SST as our turbulence model. The simulation is run on Spartan HPC to speed up. We have investigated the far field behavior of the contra-rotating turbine. As a result, we divided it into 2 parts. The first part is about the top and bottom turbine, which the slice is being made in the middle of each turbine. And the second part is the slice at the X and Y plane at the origin. For the first part, we will rotate it and look it from the top, or the positive y-axis. Here's the sample flow field of the turbine. And as you can see, the plots you're going to see later are the data being taken at different slices, at different distance from the wind turbine, like the black line shown over here. Now let's get started. The first one is taken at 5R, where again, R is the radius of the wind turbine. So we could see the flow speed is largely varied. Then to 10R, the variation started to reduce. The trend continues at 20R and started to slow down from 30R and 40R. And finally, the reduction tends to fade out at 55R and 60R, which is nearly no difference. And here's the collection of all figures that are shown in previous slides. Now let's go to the side view. We will rotate our view to the side of it. And again, here's the sample flow field of the wind turbine looking from the side. And data are taken at different distance from the turbine. And we will again start from 5R, where R is the radius of the wind turbine. The velocity is greatly varied. And the variation starting to reduce at 10R. Again, reduce. And the reduce starts slowing down from 40R, 50R, 55R. And finally, nearly no difference between 55R and 60R. And again, here's a collection of all the data I've presented previously. To conclude, we believe that if multiple contra-rotating turbine is being used in a closed manner, like in a wind farm, they should be placed 20R further from the direction of the flow and 5R span-wise, where R being the radius of the wind turbine, in order to eliminate the wake effect of each turbine. However, there are studies now suggest that for 2 vertical axis wind turbines without contra-rotating, there could be positive effects on efficiency if they are placed in counter-rotating order, where they are parallel to each other and rotating in opposite directions. Further study would include running the simulation with LES as a turbulent model in transient, having multiple contra-rotating vertical axis wind turbine being laid out in matrix form, similar to wind farm, and see how the behavior and efficiency changes. And that's all for my presentation. Thank you for listening.
Thank you very much for Mr. Ko for your nice presentations on these far field flow simulations. Ladies and gentlemen, feel free if you have any questions, just write down on the question and answer box.
My Zoom.
Is there any question? Okay, while we are waiting for the questions from the audience, maybe I would like to also discuss about this. You use 19 million cells for the CFD calculations. How long it takes for that?
19 million cells. Let me recall. It takes about a week, I believe. Yes, about a week, because we use the high performance computer provided by the university and run the simulation with it. I believe it's about a week.
And this is single phase calculation, right?
Yes.
Okay.
Only assuming like only air in it, and assuming all the properties are constant in an incompressible flow.
And what is actually the ideal arrangement for this wind turbine? I mean, what condition is the best for this arrangement?
So currently, if we want to eliminate the effect of each turbine, we will suggest that each turbine is placed 20 times of the rate of its radius from the in the distance of the flow direction, and also 5 radius apart in span wise, which is like right next to each other. Like if the turbine is here, 20 are over here, and then 5 are over here in matrix form. However, we did not take account about contour rotating in our study, which will require further study as well.
Okay, so does it mean that the wake generated by the turbine it will be diminished? So then we can place another wind turbine downstream of the flow.
Yes, like 20 times the radius, like downstream from the flow, and then we could assume that there will be a fresh air again, like no wake effects from the previous turbine.
Okay, and then in your future study that you have a plan to do LES, what is the motivation behind this?
The thing is with LES is actually to both increase the mesh cell size and also to see if using K omega SST will actually make a difference in the simulation result as well. Because even though the fact that we have seen many other literatures using K omega SST, we are not quite sure like this will be actually the best turbulence model we could use in this scenario.
Do you think the distance that is required for place another wind turbine will be different if you use LES then?
I'm not sure about this question, to be honest. I don't quite know yet. For the large eddy simulation I discussed here, I'm assuming it is going to be single turbine again for now, and if it, because it is still running, to be honest, it's running quite slow. I'll probably see how it goes with it, and then see how will it develop with the matrix form as well.
Maybe I can try to answer. Maybe I can help.
Thank you. Yes, please, Mr. Bagus, Dr. Bagus.
The advantage of using LES, it will be significantly much more accurate than the standard simulation like using RAMs. Because we still do not really understand how the effect, if we get two counter-rotating, there will be a lot of flow affecting each other. So basically LES will give us more answers about the flow around it, nearby it, but the far field flow, maybe not as much, maybe the RANs is already enough, but we just want to understand, but the reason we want to use LES, we just want to understand the physics of the fluids even better. And I think if we can use LES, the accuracy will be increased. I suspect will be, maybe about maybe about 3 or 2 more radius shorter. We're still unsure about it, but we know it will be increasing the accuracy significantly.
Okay, thank you for another additional comments, Dr. Bagus. Okay, thank you very much. I would like to appreciate so much about your nice presentations, and this is the end of these presentations. Thank you. And we are going to the next title of presentations is Application Computer Program to Design a Cross-Flow Water Turbine. I think the presenter is Mr. Wijaya. Are you here now?
Yes, sir. Can you hear me?
So if you are ready, then please proceed to your presentations. You have 8 minutes presentation and 4 minutes for question and answers. Thank you.
Okay. Okay, let me show my presentation file first. Good morning, everyone. My name is Ibrahim Hamicaya. Thank you for this big opportunity so that I can present my research with title Computer Program Applications to Design a Cross-Flow Water Turbine. To begin, we can continue to the next slide. For background from my paper, in Indonesia, mostly power plant using fossil fuel energy as the main energy resource. We know that the more we use the fossil energy, it will cause the source of fossil energy decreasing. So that to deal with this problem, we can increasing the role of based on the diagram on the left. Hydro energy in Indonesia reached 94.2 gigawatt, so that we can more using the hydro energy in Indonesia for power plant energy resources. But only a little potential of hydro energy in Indonesia that has been exploited, and many more. I think it's just 8 gigawatt in Indonesia that has been exploited. And Indonesian government have a program to increase capacity of micro hydro power plant in Indonesia. But in the research and development of the program of government in Indonesia, there is no producer of components of water turbine in Indonesia. And now we know that design process using software in this digitalization era, the role of software application has helped a lot in engineering sector, one of which is design process. The objective of this study are to help engineering designers. I want to facilitate the development of micro hydro power plants in Indonesia, especially in the design section, by developing a water turbine design calculation application that can help the designer for the design in water turbine, especially for cross-flow turbines. So the development of micro hydro power plant in Indonesia can be further developed. This is a scheme of cross-flow turbine that consists of 2 main components called runner and nozzle. For method in our research is this is the main flow chart of our research. Start, we have to data collection that is consist of turbine design parameter and parameters that we need to calculate the design of the turbine. Next is application development. Application is expected to do the turbine design calculation, and then we have to application testing. In this space, we can compare the calculation of in the application and the manual calculation if they have some value, and then the cross-flow turbine calculation has been successfully developed. This is for the main flow chart in the application development program. For the first, we start for parameter that we have declared first. That is like water density, gravitation, V, and another coefficient of the parameter. And then the user only input data that is gross head, effective head, flow rate, water angle of attack, and then turbine efficiency, and then arc nozzle entry. Application expect to do the turbine design main parameter calculation such as power, speed, and specific speed calculation, runner velocity component, runner dimension calculation, and then blade geometry, and then nozzle dimension. In the nozzle dimension calculation section, user can choose between two choices, yeah, that is want to calculate again or to next in the next section. If the user want to calculate again, and then the application will show the section in the input again. If the user choose no, and then the application will show the mechanical component calculation and then the turbine simulation section. This is the activity diagram. Activity diagram showing the interaction between user and application system. The application will respond according to what is done by the user. For example, in this application diagram, while the user open the application, first system will showing about cross-flow turbine in general. After that, the user given two choices to do next calculation or exit the application. If the user choose the calculation, then the application will show in the input calculation section. Otherwise, if the user choose the exit button, the system will close the application. And next, this is activity diagram for the main component turbine calculation. And then this is for turbine efficiency simulation section. Or for the result, this is the result of the manual calculation in the all parameters that we use to design the cross-flow turbines. I think next is still the result of manual calculation. For the application testing, we comparing the value of each main component of cross-flow turbines within the application and manual calculation. We use cross head 10 meters, head effective head 8.14 meters, and flow rate 0.4 metric per second. With angle of attack water 22 degree, turbine efficiency that we want 0.8, and nozzle entry arc about 90 degree. This is the result of the application user interface. This is the first application program open. And then in this section, user can choose to exit or next to the calculation section. This is on calculation section, user interface. User only have to input the data of gross head, effective head, flow rate, and design assumption like angle of attack water, turbine efficiency, and nozzle entry arc. Next, this is a section of runner component velocity, and then runner dimension, following blade geometry, and then nozzle dimension. Lalu this is for mechanical component calculation. In this section, user need to input the data that used to calculate the mechanical component like shaft, case, and penstock diameter. And then this is for turbine simulation process. In this section, the user have to input the.
Excuse me, Mr. Wijaya, your time's ends up. So
okay,
I will give just some seconds that you can finish. please just continue
Okay.
for just a couple of seconds.
Okay, thank you. Uh, and this is for conclusion of my research. In application program that we are developed, the application can be used to calculate turbine power, turbine speed, and the main component cross-flow turbine, such as runner dimension, bed geometry, and nozzle dimension, according to head and flow rate that user want. The application successfully developed, and the value of on the application has the same value with the manual calculation. And then on the simulation section, we use using flow rate variation, three flow rate variation, that is 0.5, 0.3, and 0.7. The result is the graph diagram between turbine the power changing based on flow rate variation and overall efficiency. The result is the overall efficiency will be increased along the increases of flow rate until it reaches the design flow rate. But in the above flow rate above the design, the efficiency will decrease, so that the power generator will be following the overall efficiency. But there is a problem with the application system, because in the application system, just connected between point and the graph maybe give a margin error, bit bigger margin error, like that.
Okay,
I
thank you,
think that's
Mr.
enough.
Wijaya.
Yes.
Thank you
Sure.
very much for your
Yeah.
interesting presentations. Ladies and gentlemen, I welcome you to if you have any something to discuss or you have any question for this topic, just write down on the question and answer box. Do not hesitate if you have any question. Okay, while waiting for the questions, if I'm not mistaken, that you develop the software by yourself, or
Yes.
okay, that's nice. And why did you choose this type of water turbine?
Why I choose cross flow turbines? This is suitable for micro hydro power plant in Indonesia, and then it has easy to manufacture and cheap to manufacture it. It is, so it's suitable for micro hydro power plant in Indonesia, especially in uh, pedestrian. Yeah, that it's suitable for micro hydro power plant in Indonesia. I think that is.
Okay, thank you, Mr. Wijaya.
Yes.
Ladies and gentlemen, if you have any question, just write down on the question and answer box. If it is not the case, then thank you very much again for Mr. Wijaya for your presentations. We are going to the
Thank you
next
very much.
presentation with the title Computer-Aided Investigation of Effect of Internal Surface Microgrooving for Enhanced Thermal Management of Heat Exchanger. So
Yes.
the presenter will be Mr. Muhammad Mustafa Abdul Halim Ahmed 8.
Yes.
So if you are ready, then you can start the presentation. Thank you.
All right. Thank you. So I'm Muhammad Mustafa, and I'm the presenter for the research on the effect of internal surface microgrooving. I'm from University of Malaya, and this is my research. So as an introduction, we all know what heat is and how it's an energy found in most mechanical systems. Now, heat affects the performance negatively, as we all know, and it causes precision errors as well as decreases efficiency. So the removal is very vital for us to make a very efficient system. Now, we all introduced heat exchangers as a system to transfer heat between two or more fluids. Now, they're found in most vehicles, machines, and other appliances. And Enhancing heat exchangers is vital to the system's cost, efficiency, functionality, and performance in whole. So my research objective today is to propose a novel strategy to enhance the heat dissipation of heat exchangers. And the approach is generating microgrooving pattern on the inside of a heat exchanger tube. Now the performance will be tested using CFD simulation, and we're going to be using ANSYS for this. Now for the microgrooving, we have a setup that incorporates a couple of permanent magnets on the inside and outside of the tube. The outside magnet pulls the internal magnet to the surface of the tube, and you have a cutting tool that is held together with strong magnets that performs the microgrooving. Now the tube is on a motor that rotates the tube, and we also have the external magnet is placed on a moving transitional jig that can move equivalent to the length of the tube. And therefore, we have a helical groove on the inside of our tube. Now, we've done this test on a copper tube, and we have a cross-section here view of the results of the setup. Now, we've done it for a 26 millimeter diameter tube that was 1 meter long. And we have a groove that is averaged in pitch of 490 micrometers and a width of 32.9 micrometers. Now, it's worthy to mention that the profile dimensions and groove specifications can be adjusting by manipulating the speed, strength of the magnet, and we can produce different groove shapes as well and sizes. So based on the results that we got, we decided to run simulations for 3 different variations. So for the square grooves, we made 200 microns, 500 microns, and 1000 microns. And we conducted it on a 25 millimeter diameter tube. And then that was pitched of 500 microns equally in all 3 designs. And it was done for a 1 meter long tube. Now, for the meshing, we used ANSYS as well for it. And we used an exponential meshing strategy. So it allows us a large number of elements and nodes to be concentrated at the wall. So all our details can be computed. We also performed regular aspect ratio quality checks and other checks that are available in the meshing software. As you can see, the meshing is exponential from a further view, but in a close-up, you can see how detailed it is when it comes to the walls. Now, for our boundary conditions, we use the K epsilon method, which is quite common in the industry and provides very good values that we're going to discuss later. And we have a heat equation that is turned on, and then we loaded our materials. And then we provided a constant heat flux of 5,092 watts per meter squared for all the designs. We used a simple solution method, and we ran it for 1,000 iterations. And then we also ran it for different velocity inlets, so we get different Reynolds numbers. So the way of validating is that we compared it with empirical correlations. And we calculated the results using these equations. So we have our entry length, our hydrodynamic length, thermal length, Nusselt number from Ditus, and then a friction factor from Darcy. And then we also calculated the Prandtl number. So the results for the smooth tube, at least, we can see that the K epsilon did not fail us. Very slight deviation of 5.59% at the highest Reynolds number. But from 16,000 Reynolds and below, we had a deviation less than 5%. The friction factor as well confirms that the calculations were done correctly using the simulation. Now for the velocity vector, we actually have very interesting results. So we can see that the grooves introduced a change in the flow pattern, and they caused swirl eddies that are generated in the void section of the groove. And this explains how the heat performance changes from groove tube in comparison to a normal tube. Now, it is observed that the sharp corner edge of the microgroove experiences more turbulence activity, and the effects of such flow conditions varies depending on the size of the group and the shape of the groove. And it can either benefit or downgrade the thermal performance. So we checked the temperature contour, and for the smooth tube, you can see that it's a very normal temperature contour. But for the grooved ones, we've realized that the flow affected directly the temperature change. And heat in the larger grooves were dissipated at a higher extent than the smaller grooves. Now, the source of the non-uniformity in the heat dissipation, as you can see, the left side is a bit hotter than the right side, is because of the lack of fluid motion at the vicinity of the inner corner of the groove. Now, basically, the fluid enters at the sharp angle, swirls, cooling the side that it enters at before it leaves. And I guess that's because of the sharp angle of entry. Now, we can see that the performance has changed a lot based on the 3 different changes. Actually, the Nusselt number compares it better. So we can see that the 1000 microns grooved tube performed the highest in comparison to the smooth tube, which is the blue line over here. And at the highest Reynolds number, it had a 95% efficiency increase, while the 200 and 500 microns actually downgraded the performance until the highest Reynolds number, where the 500 microns shows a trend of potential improvement beyond the Reynolds 24,000 Reynolds number.
I'm sorry, Mr. Mohammed, you have 1 minute left.
Okay. So yeah, we can see the inefficiencies attributed to the weak formation of recirculation flow that enables the heat to be transported via swirling motion. The friction factor also shows that the friction decreases as the Reynolds number increase. And the heat transfer effectiveness we used to compare the normal tube with the other tubes. And we can see that 1000 microns groove tube is the best so far. Now, it is observed that for the conclusion that the performance of the grooved tubes increases for the 1000 microns one especially. The 500 microns had 8% improvement at highest Reynolds number, and the 200 microns had a decrease of efficiency of 21%. And it is suggested that the groove depth to pitch ratio plays a significant role because we had the pitch ratio consistent for all 3 designs. Now, also the shape is significant to the performance, as the square shape is not the optimum shape. So I believe the future work will have different shapes and maybe a different aspect ratio, the pitch ratio. That will be all. I hope that you guys have some questions or would like.
Thank you very much for Mr. Ahmad Aid for the nice presentations. Ladies and gentlemen, if you have any question, just write down on the question and answer box. We will happy, or the presenter will be happy if you have any question, then we have discussions. Thank you.
Yes.
Do you have any questions? So, Mr. Ahmed,
yeah,
why the highest inlet velocity produce the best results?
Okay, so basically the grooving is expected to produce artificial wake, and we're trying to produce artificial wake by obstruction and expansion. And I believe the highest velocity allows also for the energy lost because of the turbulence to be moving. I believe it's just the way it operates, as in the water moves forward. So the faster the water moves, the more it is exposed to the surface. So you have a larger quantity of water exposed to the surface.
Okay.
Yeah.
Another question is, you use constant heat flux on the wall, right?
Yes.
Do you think it's just a first step, or in the application there will be variations in this heat flux, or you can?
So right now we just tested for constant heat flux, so we can compare the three tubes together and know which one is the most efficient. But we are planning on exploring transient effects of heat and see also how that affects the performance. Yeah.
Wow, thank you very much. Okay, if there is no more questions, thank you very much for Mr. Ahmad Aid for your nice presentations and information for us. Thank you.
All right. Thank you.
We are going to the next presentations, the fourth one in this sessions, with the title Effect Taper Ratio on V-tail Configurations of Unmanned Aerial Vehicle. Mr. Janitra.
Yes, you can hear me, sir?
Yes. If you're ready, you can start your presentations, please.
Okay, I'll start my presentation. Can you see my presentation, Mr.?
Yes, clearly.
Okay. Okay, good morning, ladies and gentlemen. My name is Egananda Arda Janitra. Thank you for opportunity given to me so that I can present my research, and the title is Effect Taper Ratio on Vital Configuration of Unmanned Aerial Vehicle. To begin with the concern, we can move to the next slide. As we know, in modern times, many tail geometries were developed for UAV, such as the tail configuration, wide tail, and conventional tail, and many more. And one of the most widely used of tail configuration is V-type tail. And one of the important parameter in tail design is taper ratio. Therefore, it needs to be done to research the effect of taper ratio on V-tail type V by simulation process. The objective of this research as follows. First, to determine the effect of the tail taper ratio on the overall performance of the air vehicle under study. And then the second, to determine the taper ratio value that gives the best performance for the tail. And now we move to geometrical dimension of the models. Dimension that used for vital on this research is based on UAV Langtaraka. In this research, we vary the vital taper ratio by revise the baseline models taper ratio to 0.2 and 1.0 by changing tip and root chord lengths while keeping wing area, tail area, and aspect ratio constant. The initial sizing of the tail are provided in this table. Autodesk Inventor Professional 2019 was used to design the computer-aided design models and also to vary the taper ratio of the V-tail with a tail taper ratio of 0.2. This is a top view of the UAV with a tail taper ratio of 0.4. And this is a top view of the UAV with a tail taper ratio of 0.5, the baseline model in this research. This is a top view of the UAV with a tail taper ratio of 0.6. This is a top view of the UAV with a tail taper ratio of 0.8. And for the last, this is a top view of the UAV with a tail taper ratio of 1.0. After the CAD design was done, CFD software used to calculate the force and coefficient. Fluid domain with symmetry function was designed inside the design modeler on ANSYS Workbench. And this is the illustration of the geometry and the fluid domains. After the fluid domain was done, unstructured mesh is created in CFD. With total of 1 million elements were created for its geometry. We use body sizing and two different phase sizing for fluid domain and UFE. The quality of the mesh is indicated by the skewness and the orthogonal quality. And the value is compared to the mesh quality spectrum. The average value for the skewness was 0.21, which is excellent, and orthogonal quality was 0.78, which is very good. And this is closer look of the mesh result. And this is the distribution of speed on fluid domain. The result from the calculation are compared to each other to find the best step ratio value for vital configuration. We compare the lift, drag, and also lift to drag ratio. The comparison was done on Microsoft Excel. The angle of attack that used in this simulation is 0 to 60 degrees. From the table lift force on various step ratio and angle of attack, it can be seen that step ratio 1.0 generates the highest lift in amongst all of step ratio variation, with the step ratio 0.4 is the lowest to generate lift. The existing data then convert into a graph to display simulation result at the angle of attack being tested. And this is the graph of lift force on variation of step ratio and angle of attack. From this graph, we can see that step ratio 0.4 generate lowest lift force. It's shown by orange line in the graph. And this is percentage comparison of lift force to step ratio 0.5. From this graph, we can see that step ratio 0.4 provides the lowest lifting force compared to the other step ratio. Step ratio 0.4 has decreased more than 2% compared to the step ratio 0.5. On the other hand, generates more lift means it generates more drag. Step ratio 0.5 generates the highest drag amongst all step ratio variation, and step ratio 0.2 is the lowest to generate drag. Tail with step ratio of 0.5 has the highest drag value compared to the other because the lift generated is also high. The higher drag will reduce aerodynamic efficiency and aircraft performance because the higher drag force that received by the aircraft. And this is graph of drag force on variation of step ratio and angle of attack. We can see from this graph that step ratio 0.5 generate the highest lift force that's shown by blue line on the graph. And this is percentage comparison average of drag force to step ratio 0.5 from 0 degree until 16 degree angle of attack. Step ratio 0.4 has increased lift force more than 3% compared to the step ratio 0.5, and step ratio 0.2 has decreased lift force.
Excuse me, Mr. Janitra, you have 1 minute left.
Okay. And vital performance is not determined by only looking at its lift or drag, but also from the lift to drag ratio. Lift to drag ratio can be obtained by dividing the lift force by the drag force or dividing the lift coefficient by the drag coefficient, since it will produce the same result. In this case, we divide the lift force and drag force to obtain the lift to drag ratio and compare them. We can see that step ratio 0.5 generate the highest lift to drag ratio than the other. The highest performance occur at 0 degree angle of attack on step ratio 0.5. But if we take all angle of attack into account, step ratio 0.2 is the most stable compared to the other. This is the average percentage comparison of lift to drag ratio to tap ratio 0.5. We can see from the graph that only tap ratio 0.2 generate higher lift to track ratio than tap ratio 0.5. And for the conclusion, from the simulation that has been run on unmanned aerial vehicle with various vital geometry, which are tap ratio 0.2, 0.4, 0.5, 0.6, and 0.8, and 1.0, we can conclude that tap ratio 0.2 of vital geometry produce the highest lift to track ratio that can give the better performance for unmanned aerial vehicle And for now, tap ratio 0.2 is the best value for vital configuration since it gives more lift and stability. Thank you. Maybe enough for me, Mr. Rian.
Thank you very much, Mr. Janitra, for your nice presentations. For audience, if you have any questions, just type in the Q&A feature, Q&A box. We are welcoming your questions or discussions. Okay, there is a question for you, Mr. Janitra, from Mr. Rahmat. The question is, I would like to ask out of curiosity, referring to graph of lift force and angle of attack. There exists saturation value of lift force. Is there any mechanisms that explain that phenomena?
Yes. Thank you for the question. For the graph lift force on tap ratio of angle of attack, there is saturation between angle of degree of about 8 degree to 16 degree. There is a highest increased lift force in this degree from 0 to 8. After this, the plane have steady increase of the lift force. So this phenomenon is happen in the other plane. So it's not a problem. And after every plane in subsonic speed, after about 15 degree angle of attack, it's the lift force of the plane was decreased after that. So it's like the other plane on the subsonic speed. I think it's my answer.
Okay, that is the answer, Mr. Ahmad. If you still have any question, just write it down. Is it sufficient for you, or is it satisfy the answer or not? You just write down again the other questions. So if there's no more questions, then thank you very much. Thank you again for Mr. Janitra.
Thank you, Mr. Rian.
We are going to the last presentations in this first paper presentation session. The last one is with the title Design and Analysis of Single Stage Axial Mini Turbine for UAV Jet Engines. I think the speaker will be Mr. Fadilah. Are you here? Mr. Fadilah?
Oh.
Okay.
Can you hear me?
Yes, I can clear you. I can hear you clearly.
Okay, thank
so
you.
Just start your presentation.
Okay, let me share screen my presentation. Can you see it now?
Yes, I can see it.
Okay. So let's start. Thank you for the time, Mr. Rian. Okay. Good afternoon, everyone. I welcome you to my paper presentation with title Design and Analysis of Single-Stage Axial Mini Turbine for UAV Jet Engine. That I work for my thesis on bachelor degree and I have taken it as my research. And my name is Adam Muhammad Fadilah and Mr. Agung Bramantia as my supervisor. So come to the introduction. The reason why I interest and choose this topic is because the development of the world of aviation every year is getting faster. It is also happening for the development of the world of UAV, and one of the development is the propulsion system. At the beginning of the development, creation of UAV, the UAV propulsion system using a propeller, but change in time, the UAVs began to develop to use jet engine system. And here's our objective, which is first, determine design of mini turbine. Second, knowing the effect of the size of the rotor clearance on the thrust value. Third, knowing the effect of staggered angle on the thrust value. Fourth, knowing the effect of using exhaust nozzle on the for the thrust value. And the last one is finding the optimal design for a turbine with a thrust value of 200 Newton. And so here's our stator design. With the outer diameter is 182 millimeter, and the inner diameter is 100 millimeter with 22.5 staggered angle degree. And for the rotor design, with the outer diameter is 180 millimeter, and the inner diameter is 100 millimeter, which means the turbine blade is 40 millimeter, with chord length is 30 millimeter, and 1 millimeter for the clearance from the throat. In this research, we are using ACCFX for the main tool for simulation and calculating the result. ACCFX was being used because its utility for simulating the rotating machinery is much easier compared to other programs in ANSYS. And this is the meshing result, with total is 453,000 nodes and 1.3 million elements. And as for the stator mesh, total nodes is 540,000 and 1.6 million elements. And this is RCCFX hub interface, where you can determine the domain, boundary layer, value of inlet, outlet, wall, and so on and so on. And for this case, this is my turbine after the assembly, where as you can see, there is inlet, outlet, and domain rotor, stator, interface, and wall. And come to the result. Here's the result of the simulation. And this is the contour of velocity and also pressure contour. As you all can see, the velocity is increasing from the inlet to the outlet. And as the pressure, the value is decreasing along the turbine. Because as you know, for turbine is using Brayton cycle, where after the turbine outlet, there is decreasing of pressure and increasing of velocity. In this research, we also made some variants, and one of it is their clearance. Clearance is, in this case, is the gap between the rotor tip to the throat of the turbine, or housing from the stator. And this figure is the result of 2 millimeter clearance, where the basic design used 1 millimeter clearance. As you can see from the velocity and pressure contour, the velocity and the pressure contour of the air at inlet is less than previous simulation. And for the 4 millimeter clearance, the velocity and pressure drop even more. And from the simulation above, here is the table and graph for the result. From the simulation with a clearance of 2 millimeter, the velocity is 140 meters per second. With that, we'll calculate the thrust is 147 Newton. This thrust value is smaller than 1 millimeter clearance. This shows that the size of the clearance will affect the speed and the pressure produced. The speed and the pressure that occurs at the outlet are smaller than the turbine with 1 millimeter clearance. So that is produce smaller thrust than the turbine with 1 millimeter clearance. It can be seen from figure above that the thrust and pressure will always go down with the addition of the clearance measure. The pressure between 1 millimeter and 2 millimeter clearance decrease dramatically. But from 2 millimeter clearance to 4 millimeter clearance, it's not too significant. This happened because the clearance size at this point is too large. So it's not as influential on 1 millimeter clearance. Tip clearance needs to be designed so that the desired turbine thrust is obtained. Ideally, the smaller the clearance, the greater the thrust that will be generated. However, the tip clearance distance that is too small causes the pressure increase in turbine inlet area. Besides, clearance sizes that are too small are difficult to manufacture, so they will cost a lot of money. The clearance that is too small can also cause damage to the rotor throat due to the expansion of the rotor blade because temperatures are too high, and also pure balancing process in manufacturing process of the turbine. There are two variables used in this study. That first is clearance, and now is stagger angle. Stagger angle is the angle between the stator's chord line and the axial axis of the turbine, where the axial of the turbine is considered as 0. In the previous analysis, the stagger angle was set at 22.5 degree, but in this analysis, the stagger angle was increased and reduced by 10 degrees. And here's the result of the simulation, the turbine with the decreased stagger angle. In the simulation performed with the stagger angle reduced by 10, the velocity and the pressure seems to decrease compared to the first simulation with 22.5 degree stagger angle, meaning resulting thrust value is smaller than the original angle. After the simulation with the stagger angle, we try to simulate the increased stagger angle. The resulting value is bigger than the original stagger angle. This shows that the angle of stagger also affect the amount of thrust produced. And here is a result graph and table. At the stagger angle of 32.5 degree, the resulting thrust value is 188 Newton, while at the stagger angle of 12.5 degree, the resulting thrust value is 188 Newton. While at the stagger angle at 12.5 degree, the thrust value achieved is 147 Newton. However, the addition of stagger angle certainly causes various kind of effects on the flow property. A comparison of thrust and pressure result in this variation can be seen from table and graph.
Excuse me, Mr. Padilla, you have 1 minute left.
Okay, that is a little bit. This is what caused the change in flow properties and the turbine. As can be seen figure there, that is a drastic increase in speed and trailing a stator. This is caused by very high pressure on the surface of the stator. After that, we calculate the thrust produced from the turbine outlet. We do a simulation where we give an exhaust nozzle after the turbine. Based on the result of the simulation, it can be seen that the thrust value increased by 37%. This happens because of the function nozzle is to increase velocity when exiting the turbine and become higher thrust. And come to the conclusion. Increasing the clearance size will reduce the thrust value resulting from the highest thrust value is owned by a turbine with a clearance of 1 millimeter with thrust 156 Newton. However, the clearance size cannot be too small considering the effect that will be experienced by the turbine. Second, the greater the stagger angle on the stator, the greater the thrust value produced by the turbine. In this research, the highest thrust value was achieved by in-turbine turbine with a stagger angle of 32.5 degree with 188 Newton. But the greater stagger angle, the speed spike on the trailing edge on the stator will increase and become irregular. And with the nozzle at the turbine outlet, the resulting thrust value will be much greater. In this study, the thrust value of the turbine increased by 37% from the previous 156 Newton to 214 Newton. This is because the nozzle function itself will increase the speed and thrust of the turbine. And the last, the best choice of all analysis variation to be used as turbine on a small scale engine is design turbine with a clearance of 1 millimeter and staggered angle of 22.5 degree, because this configuration has a thrust value of 214 Newton after exit the nozzle. And that's it for me. If you have any further question, you can call my number or you can email me and I will kindly answer that question.
Okay, thank you very much for your nice presentation, Mr. Padilla. You have one question here from Abdul Muiz. Did you check the relation between stagger angle with the chamber line of the blade? Both of them has quite strong relation with the performance of the turbine cascade.
Okay, thank you for the question. For stagger angle and axial chord line, I only check it on the simulation. Okay. And that's the result for the simulation. And maybe any other question?
Okay. Is there any questions again? If not, then we will close these sessions. No? If it is not the case, then thank you again, Mr. Fadila, for your presentations. And I would like to again thanks for all the presenters in the sessions. Then this is the end of this paper presentations. I will return back the session to the Mr. Gifari. Thank you.
Okay, thank you very much.
Okay.
I will stop. Sorry.
Thank you very much to all the presenters for the amazing presentations. And of course, I would also like to express my gratitude to Mr. Rian Anugrah as the moderator for the previous session. And without further ado, for the next session, we will have a keynote presentation from Professor Nicholas Hutchins, as well as Mr. Indro Pranoto in this session will be a moderator. So Mr. Indro Pranoto, if you're already here, could you hear my voice?
Yes, I can hear clearly.
All right. Whenever you're ready, Mr. Indro Pranoto, the time and platform is yours.
Okay, thank you, Mr. Gifari, for the time. And I would like to greet good morning for all presenters and attendants. And I think I would very great. I think it's good afternoon, Prof. Nicholas Hutchins in Melbourne University. I would like to check that whether you already hear our voice before we start the.
Yes, I can hear you. Can you hear me?
Thanks very much. Yeah, we can hear you very clearly. Yeah.
Oh, good.
Today we will continue the session, that interesting section that we already finished the first session for the keynote speaker from Prof. Aziz, and then we continue the session for parallel session, and then come to this session is the session for keynote speaker, second keynote speaker. That but before the start of the presentation, I would like to introduce our honorable speaker for this conference. Is a Professor Nicholas Hutchins. We call his Professor Nicholas is a professor in Department of Mechanical Engineering at the University of Melbourne. He's from a fluid mechanics group. Prof. Nicholas' research expertise are in the turbulent boundary layers, turbulent structure, turbulent drag reduction, turbulent wall, bounded flow over the rough or fault surfaces. And also he conduct many works in the advanced flow diagnostics using the particle image velocimetry or and hot wire anemometry. So it's Professor Nicholas is graduated for his PhD from University of Nottingham, UK, and his bachelor from the University of Manchester. Professor Nicholas already published many of his papers in top-tier journals, assembled in the Internal Journal of Heat and Fluid Flow, Journal of Fluid Mechanics, and also the several journals, and also attended the presenting on his work in the conference, and published in the many papers in this, mainly on the turbulent fluid mechanics and heat transfer. So I think if our Professor Nicholas already prepared and ready for the presentation, I would like to give the time and opportunity to the Prof. Nicholas to present your talk on the turbulent boundary layer developing over rough surface from the laboratory to full-scale time. Your time is about 30 minutes, and then we will continue for the question and answer. Thank you, Professor Nicholas. Time is yours, please.
Thank you very much. Can you see my slides okay?
Yeah, can see clearly.
Okay, thank you. So thank you for the introduction, and of course, thank you to the organizers for the invitation to present here today. So I'm going to be talking about rough wall turbulent boundary layers, and in particular, attempting to make predictions of drag over roughness on ship hulls. So this was really a collaborative effort involving a number of researchers from Melbourne University, and in particular, I highlight Bagus Nugroho, who's here today, who was really instrumental in putting together this collaboration. There was also a team of collaborators from Indonesia, from ITS and Universitas Jember, and I highlight Professor Ketut Utama, who again was instrumental in this collaboration. There was also a team from the UK, and we had industry collaborators also from Indonesia. So this includes BKI, the Indonesian Safety Classification Bureau, and also Dharma Lautan Utama, a ship owner and operator. And in particular here, we're grateful to Mr. Yusuf for granting us access to vessels for full-scale experiments. So in terms of the outline of my talk and key messages, I'm going to start with motivation, why rough wall turbulent boundary layers are important environmentally and economically, in particular to shipping. I'm going to talk briefly about full-scale predictions and what the roadblocks are to making those drag predictions. And as we'll see, the key to being able to predict drag on operating ships is really being able to access this quantity KS, which is very elusive, the equivalent sand grain roughness. And I'll talk a little bit about how we might be able to predict KS for given surfaces. And really for the second half of this talk, I want to talk about these collaborative measurements with our Indonesian partners, where we attempt to directly measure drag on an operating ship. Okay, so background, the shipping industry has a very large environmental and economic footprint. They're estimated to be 90,000 ships operating worldwide. Together, they consume about 8% of the world's oil production, and the oil that they burn is of an extremely low grade. Okay, so the emissions cause a number of deaths per year. In addition, from a turbulent boundary layer perspective, on a large ship, up to 90% of the drag can be skin friction drag resulting from turbulent boundary layers. So it's kind of an example of where turbulent boundary layers really has a large economic and environmental impact. So shipping also provides a very sobering example of rough wall turbulent boundary layers. And the reason for this really is biofouling. The longer that a ship remains in the water, the more that the marine organisms accumulate on the hull of that vessel, and this adds to the roughness of the surface, which increases the drag due to those turbulent boundary layers. Schultz has estimated that a heavily fouled vessel could have an 86% powering penalty, and in a subsequent economic analysis, considering just 56 of the US Naval's frigates, he was able to show that over the 15-year lifespan of those frigates, the cost of moderate fouling was over $1 billion. So when you consider that that $1 billion is for 56 ships out of the 90,000 that are estimated to be operating worldwide, you get a strong sense that rough wall turbulent boundary layers, biofouling and shipping have a very large environmental and economic impact. So based on that, that kind of dictates the overarching aim of this project, which is actually very simple. We want to be able to accurately quantify the drag penalty on a ship due to a given hull roughness. And the belief here is that if we can accurately quantify the drag, we can make compelling economic and environmental arguments to operators and regulatory bodies, which would lead to more efficient and informed ship operations. Okay, so let me start with this brief overview of full-scale predictions of skin friction drag. And this is very much my perspective from coming from a turbulent boundary layer background. If I were going to model the skin friction drag on this operating ship, then I'd model the wetted surface area of that vessel as a flat plate. And then I'd use classical turbulent boundary layer theory, which would enable me to predict the evolution of those boundary layers over that plate and extract a drag coefficient for that vessel, okay? And this is a very established technique going all the way back to Prandtl and Schlichting. And the reason that we're able to make this prediction is because we know what the mean velocity profile for a turbulent boundary layer looks like. So I'm plotting here the turbulent mean velocity profile for a turbulent boundary layer. Z on the x-axis is wall normal or hull normal distance. U is the mean velocity. And this profile has this self-similar form. So this is the smooth wall velocity profile in the boundary layer. If the flat plate was covered with a roughness, that mean profile would be shifted downwards by some amount, excuse me, delta U plus. And the magnitude of that downward shift, delta U plus, provides a measure of the drag penalty due to that surface roughness. So that downward shift itself, delta U plus, is a function of this new variable, Ks, which is the equivalent sand grain roughness. So if we consider that rough surface, and if we that mean profile for that rough surface, if we ignore all known empirical constants, that profile is just a function of boundary layer thickness and Ks, okay? So provided we know Ks, provided we know the equivalent sand grain roughness, which is a very big proviso, provided we know that, we can make use of von Karman's momentum integral equation, and we can predict how those rough wall turbulent boundary layers will evolve along the length of that roughened plate, okay? And from that predicted evolution, we can get a drag coefficient on that plate as a function of Reynolds number. And by looking up on that prediction for the Reynolds number of whatever engineering system we're interested in, and in this case, we're most interested in ships, we can work out what the drag penalty would be to that engineering system under that particular roughness condition. Okay, but the problem or the roadblock here is that we need to know Ks. We need to know the equivalent sand grain roughness. And the problem with Ks is it's not some geometrically observable quantity of the hull roughness, okay? I can't just go to that ship in dry dock with a ruler and measure equivalent sand grain roughness. It's a flow property. It's a measure of how much effect the surface roughness has on the flow. And the only way that we can measure Ks is to expose the roughness to the flow and make fluid measurements, okay? So this is a major roadblock. If we have Ks, we can make accurate predictions of drag, but we don't usually have Ks a priori. So because of that, the current practice in the marine coatings industry is really to use simpler equations that bypass the need for Ks. And the problem here is that in bypassing Ks, these predictions can be at times wildly inaccurate, okay? So, anyway, I hope what's clear from this is that to make accurate predictions, we need to be able to predict or measure Ks, the equivalent sand grain roughness of the surface. So let's talk a little bit about how we would go about determining Ks based on current technology. So as I've said, Ks isn't something that we can just observe from the hull. It's a flow measurement, right? It's really a measure of how much effect the surface roughness is having on the turbulent boundary layers. And there's a few options that are open for us to measure Ks. Route 1, and really the gold standard for determining Ks, is experiments or CFD, okay? And in particular here, I mean that if we observe some roughness in application, we can scan and replicate that roughness, and we could expose it to a flow in a laboratory wind tunnel or in a numerical simulation. And then by measuring the flow over that rough surface, we can determine the equivalent sand grain roughness, Ks. The advantages here is that the answer that it gets is accurate and correct. The disadvantage is it's very expensive. For each rough surface we want to consider, we basically have to make another measurement, experiment or simulation. At the other end of the scale, what I'm going to propose in a moment is that we could kind of bypass this roadblock by directly making measurements on operating ships. The advantage here is that it's fully realistic. We're measuring exactly on the engineering system that we're trying to predict. So there's less assumptions. Disadvantages are that this will be a field measurement, and often, obviously that comes with some loss of accuracy. And then we come to correlations, which really should be our aim in roughness research. I think these are the holy grail of what we're aiming towards. By correlation, I mean that we want to come up with some empirical relationship where we can predict KS as a function of something that we can measure, okay? So some readily measurable topographical properties of that rough surface. And the advantage of correlations are that they're cheap. The disadvantage of them at the moment is that they often lack accuracy. So before we move on, as an example of those correlations, let me highlight some recent research that was performed at the University of Melbourne. So these were measurements by Leon Chan, and he performed direct numerical simulations of a fully turbulent rough-walled pipe flow. So the inner surface of that pipe was covered with a three-dimensional egg carton type roughness, and he varied the geometry of that roughness in numerous different ways. And I'm going to show a few results from Leon Chan's research here. So again, on this slide, I'm plotting the mean velocity profile in the turbulent boundary layer formed over that rough surface. On the x-axis, we've got Z, which is the wall normal direction in the pipe. On the y-axis, we've got mean velocity. And the first curve that I'm showing here is for the smooth wall pipe. And then when we add roughness to that pipe, we can see that that mean velocity profile becomes shifted downwards by this quantity delta U plus, which I've already told you that downward shift delta U plus is proportional to the drag penalty due to that surface roughness. On the inset of this figure, I'm plotting delta U plus as a function of lambda, where lambda is the wavelength of that roughness, okay? So it's a measure of the steepness of the roughness. And you can see that as I keep the roughness height the same, but reduce that roughness wavelength lambda, that mean velocity profile continues to shift downwards, okay? And you can see that in the inset. So that means that the drag penalty, even for roughness with a fixed roughness height, the drag penalty increases as the steepness of that roughness increases, or as the wavelength is reduced. Okay, so Leon did many systematic DNS simulations. And what he did was he took all of his data and all the data that he could find in the literature, and he threw it onto this plot. And this is a plot that shows average roughness height, Ka, versus that downward shift delta U plus, which is proportional to drag penalty. And when he put all of this data onto this figure, initially it was disappointing. It was a kind of terrible mess, and there was a lot of scatter on this figure. However, when he realized that he could plot this three-dimensionally, now this time against Ka, average roughness height, and Es, which is effective slope, a measure of the wavelength or the roughness steepness, what he could see is that all of the data collapsed down pretty well onto this simple surface. And by writing out the functional form for that simple surface, we basically get to the desired form of this correlation. You can repose that surface so that we get exactly what we want, okay? We get the equivalent sand grain roughness Ks predicted as a function of things that we can measure, okay? And in this case, Ks is a function of Ka, which is the average roughness height, and Es, which is the steepness or the slope of that surface. So those are things that we could directly determine from a scan or an observation of the roughness on the hull during dry dock, or from a dive inspection. Okay, so that's an example of a correlation, but what I should say is it's an imperfect correlation, okay? It considers that Ks is merely a function of Ka, an effective slope. In reality, we know that other roughness properties must be taken into account. Over the last decade or so, there's been a growing amount of research that shows that the skewness of the rough surface is also important in determining the drag coefficient. So plainly, we need to update this correlation to improve skewness. What I'd like to highlight is that really to improve the correlation, I've got to add more data points onto this plot, okay? And what I'd also like to highlight is that each of the points on this plot is a very painstaking and laborious experiment or direct numerical simulation. So each point is very expensive, okay? So what we'd like, in order to come up with better correlations, we need more data, and we'd like a way of being able to get more data quickly, okay? And this is where we initially proposed this collaborative experiment between us and Indonesia for making direct measurements on a operating ship, okay? So this is, the fact that we were able to do this is entirely down to our collaborators at ITS, Professor Utama, and also our industry collaborator, Mr. Yusuf at Dharma Lautan Utama. They were able to gain us access to an operating roll-on, roll-off ferry, and more specifically, they permitted us to modify that ship in a very small way. So the premise of the experiment was simple. There's a turbulent boundary layer formed over the underside of this ship. We wanted to add a small window or optical access, and then by peering outwards through that window on the underside of the ship with a laser Doppler anemometer, we'd be able to measure the velocity in the turbulent boundary layer. And by traversing that LDA in the whole normal direction, we could measure the velocity gradient in the boundary layer over that ship. And from the velocity gradient, we could determine the local drag coefficient acting on that vessel. So the ship is 70 meters in length, and the LDA measurement was made 25.5 meters downstream from the front of the ship. So this is an image of the vessel in dry dock. I'm highlighting here for a sense of scale. This is Bagus Nugroho, who again was instrumental in making most of these measurements and making this experiment happen. He's stood at a location on the ship where the window was added to the flat underside of this vessel. And this is a photograph of the window when it was being added to the ship in dry dock in Indonesia. And this is a photo taken from the inside of the ship with the LDA, which is here, safely installed on its traverse, peering outwards through that window that's been added onto the underside of the hull of the ship. And again, just to give kudos to Bagus, this is him making measurements in this very hot and confined space between the hulls of that ship, making measurements with that LDA while that ship was sailing. Okay, so I'll come on to measurements in a moment, but it's no good us measuring the drag on this operating ship if we don't retain a record of the state of the roughness on the hull of the ship. So we've also been developing an underwater image-based surface scanner. It's a quite simple device designed by master's students. It's an enclosure, which unfortunately is only occasionally waterproof. And within that enclosure, we basically got a 3x3 array of 9 cameras. And the diver presses this device against the hull of the ship, presses a button, and all 9 cameras simultaneously acquire an image. So these are actual photographs of the hull of the ship taken during a dive inspection by an Indonesian diver. And then once we've got those 9 images, using standard tomographic reconstruction techniques, we can build up a 3D topographical map of the hull of the ship. So we have a record of the biofouling or the roughness on the ship hull. So while we were developing that roughness scanner, which still has teething problems, we supplemented this with imprints taken of the hull of the ship during dry dock. And really from one of these imprints came the first major result from this collaborative study. So what I'm showing here on this slide is an imprint taken from the hull of the ship just after dry dock, okay? So this is in the unfouled state when the ship has just been cleaned and repainted, okay? So this is as good as it gets. This is the smoothest the hull ever is. Now, and what you can see from this imprint is that there's this texture, orange peel texture, due to the way that the anti-fouling coating has been spray applied onto the hull of the ship. So what we could do, and this is an example of directly determining KS via wind tunnel experiments, what we could do is take that imprint back to our lab in Melbourne. We scanned that surface, and then we scaled and replicated that surface to form a test surface within a boundary layer wind tunnel. Okay, so we machined tiles of that roughness, and we used many tiles to construct the aerodynamic surface. We exposed it to a flow, and we made detailed hot wire measurements in the turbulent boundary layer that formed over that replicated orange peel surface. Okay, and I can show some results of that here. So again, as always, I'm just plotting mean velocity profiles from the turbulent boundary layer. Z is the distance normal to the wall, U is the mean velocity, and this initial black curve shows the velocity profile for the smooth surface, and then these colored dots, filled symbols, show the mean velocity profile for the rough surface. And starting at a low free stream velocity, you can see that there's a small downward shift due to that surface roughness, and as we increase the mean velocity, that downward shift increases as expected. So by plotting that downward shift, delta U plus versus the viscous scaled roughness height from these experiments, and then fitting this to Nicorazzi's polyrough asymptote, the details of this aren't very important, okay? But just suffice to say, by making those measurements and fitting to an expected form, we're then able to extract the equivalent Sanggrain roughness for this surface, okay? So in this case, something we couldn't measure in dry dock, but we can measure from the wind tunnel experiments, we know that the equivalent Sanggrain roughness is 100 microns, okay? So I've rushed through this study very quickly, but really in 2 or 3 minutes, but this would have been 2 or 3 months of arduous work for Bagas Nugroho. And basically those 3 months of work boil down to this single result, 100 microns, okay? So it's very laborious, but once we have that KS, once we know it's 100 microns, we can plug that into our full-scale predictions, and it can predict the drag penalty on this operating ship due to that orange peel surface. And surprisingly, what we found was that this small-scale roughness due to the paint application had a drag penalty of almost 20%, okay? So even in the best case scenario, when the ship is perfectly clean, the moment that ship re-enters the water, there's already a 20% skin friction drag penalty due to the surface finish from the application of that coating. So this was an interesting result, and there's been several collaborative, fundamental and applied publications that have resulted from this side study between Australian and Indonesian collaborators. Okay, so back to those LDA measurements, which was the real purpose of these experiments. So remember that LDA was measuring 25.5 meters from the front of that vessel. And after many years of heartache, we, or Bagas, finally managed to get a mean velocity profile in the turbulent boundary layer over that ship while it was operating, okay? And that's what I'm plotting here, a mean velocity profile. You can plainly see the boundary layer forming over that vessel with lower velocities close to the surface and higher velocities in the free stream. So once we have that mean velocity profile, we can actually now go away and do what we wanted to do. From that mean velocity profile, we can predict the local drag coefficient at that location on the ship. And the way that we do this is by fitting the profile to the assumed logarithmic law that we know exists for the smooth and rough wall turbulent boundary layer. So this is really a Clauser fit for any of you who've done this on turbulent boundary layers. It's very, very simple. You guess a value for skin friction coefficient CF. This enables you to plot our experimental LDA data on this graph. We then look at the gradient of that data plotted in this way in the logarithmic region. And if that gradient does not equal 1 on kappa, our guess for CF wasn't good, and we need to reiterate. So as an example, in this case, our guess for CF yielded a value for kappa that was 0.21, which is much too low. We're looking for values of around about 0.4, as shown by that horizontal dash line in the inset. So we need to guess again, okay? And eventually, when you go through this iterative technique, you come up with a value for CF that exactly gives you the required gradient in that logarithmic region. And then this is the assumed value for the skin friction coefficient at this position on this rough hulled ship. So these results were very confronting for us. We thought everything looked correct, but the delta U plus, the downward shift in that profile was very, very large, a delta U plus of 19, almost twice as large as anything that we've seen in a laboratory. This would mean that the drag penalty acting on this ship would be in excess of 200%, or in other words, the equivalent sand grain roughness KS, the roughness height on this ship would be about 30 millimeters. So this was surprising, and we were didn't really trust it because of known inaccuracies from that Clauser fit technique. So fortunately, there were other ways that we could sanity check this result. From that mean velocity profile that we measured, we can also measure the momentum deficit, and we can use that to compute a value for the momentum thickness theta in the turbulent boundary layer at the location where we made our measurements. And then we can compare our measurements with the momentum thickness that would be that we would get from predictions. So what I'm plotting here is X, distance from the front of the vessel in meters versus the momentum thickness in meters. The black curve here shows the predicted momentum thickness if we presume our result was correct and KS was really 30 millimeters. We really had a roughness height of 30 millimeters. And in comparison, the blue curve here shows the expected evolution of momentum thickness for smooth, if the hull of the ship were perfectly smooth. And onto this, at the appropriate X location, 25.5 meters, I can plot the momentum thickness that we measured with that laser Doppler anemometer. And you can see that it matches up very well with that prediction, which again indicates that KS really is close to 30 millimeters. And as a final check, we can compare the predicted mean velocity profile at X equals 25 meters, which is the black curve here. If KS were equal to 30 millimeters, we can predict that, we can compare that with our LDA measured profile, which are the gray symbols. And you can see that the match is almost perfect, okay? So again, we have very high confidence in that measurement of KS of 30 millimeters. So what this was telling us, just from a velocity measurement on the hull of this ship, is that the hull was extremely rough. So in an ideal world, the scanner would have been working, but it was flooded at this time. But when that vessel dry docked, which was a few days after the measurements were made, we could photograph the state of the hull. And what we saw was that it was extremely rough indeed. We had a very, very badly fouled ship hull. There was patches of biofouling on that hull that were far in excess of 30 millimeters. I'm not an expert on marine fouling, but I recognize some of these species growing on the ship from my dinner plate, okay? There are mussels growing vertically outwards from the ship, which would have had a roughness height far in excess of 30 millimeters. So my final slide, right? This was the mean velocity profile we measured in 2018. And this was the mean velocity profile in pink here that we measured in 2016, okay? An enormous difference in boundary layer profiles and drag. This is the same ship, same operating conditions. The only difference being that in 2016, the anti-fouling coating was doing its job and the hull remained clean. While in 2018, we had this catastrophic fouling of the hull, which caused this enormous drag penalty from the hull. Okay, so I'm going to stop there, but just to conclude, if we want to make accurate drag predictions, there's this roadblock in terms of KS. We need to know KS to make drag predictions. DNS and experiments providing increasing opportunities to accurately determine KS, and this will eventually improve correlations. Full-scale shipboard experiments could rapidly expand the available data for formulating correlations. Our initial experiments on the ship look extremely promising, and one conclusion from this is that the drag penalties on poorly managed hulls are extremely large. In the case of that ship we were investigating, greater than 200%. And as a final conclusion, I would say that the project really illustrates the great potential for collaboration between Indonesian and Australian researchers and industry. This research just wouldn't have been possible without everybody in this collaboration. So with that, I'll say thank you, or I hope I'm saying thank you, and take any questions.
Yeah, thanks very much for the very good presentation, for the very interesting and challenging topics in the lesson. I think is very, very expensive and difficult measurement on this issue. And Prof. Nicholas and his team also already collaborate with our university in Indonesia, ITS and others university. So in the future, we can further collaborate with the other topic in the specific area. So I checked in the question from the panel. That's okay. They have one question from Dr. Kasani. So, dear Prof. Nicholas, after obtaining the measure velocity profile, what we can do then with this data? Is it the question for you, Prof. Nicholas? Is it clear?
Yes, it's very clear. Yeah, thank you for the question. So yeah, once we can measure the mean velocity profile over the hull of the ship, we can then use that mean velocity profile to extract an estimate for the local drag coefficient of the hull of that ship. Okay, so basically by just using the laser-based device to measure the velocity while the ship is in operation, we can effectively measure drag, and we can therefore actually on the fly determine whether the hull of the ship is operating in the smooth or the rough condition. In addition to that, having a record of that mean profile is very, very interesting to me, right? Because I've always studied turbulent boundary layers only in the laboratory. And one of the things that one of the things that I didn't highlight in my presentation was the Reynolds number is extremely high on this operating ship, friction Reynolds number of 400,000, much higher than we could ever get in a laboratory and definitely in a simulation. So it's also very reassuring to see that the predictive techniques, which were proposed by Prantl, Schlichting, and Granville, all the way back, starting almost 90 or 100 years ago, it's very reassuring to see that those predictive techniques work well at high Reynolds numbers. And then finally, that measurement will give us a KS for that surface. So without any of the expensive laboratory measurements, once we get the hull scanner working properly, once it doesn't flood when the diver takes it underwater, once the scanner's working correctly, we can then match the measured KS from that mean velocity profile to the topographical scan that the diver obtains. And then we can very, very rapidly build up a database of topographies versus KS. And we can use that as training data to come up with improved correlations. And I think from all of this, we'll be able, in just a couple of years' time, I hope, we'll be able to really give industry a solution where they can make very accurate predictions of drag on their operating ships. And my aim would be really that nobody in the future will operate a ship with a 200% skin friction drag penalty. This probably isn't good, definitely not good for the environment, and economically it's probably not very good for the ship operator. Thank you for the question.
Yes, thank you for the answer. I hope that is meet the Dr. Khasani question. They have still another 2 questions that in the chat for Prof. Nicholas from Dr. Anugrah, Rian Anugrah, that I think is also that I wonder about this, how about the effect of some environment. For example, the question is how about the environment condition, different sea giving different falling condition, and also of course will give also different roughness of the whole ship. So what the yeah, I think this one is the question. Yeah.
I'm sorry, could you just repeat the question? Oh, I can see the question now. How about the different the environment condition?
Yes.
Is that correct?
Yes, correct.
Yeah, so I think that's a good question. The extent of the fouling on the hull is dependent on many factors, right? I mean, this particular ferry had an unusual duty cycle where it operates for a few days and then it sits at anchor for a few days. And the problem, most fouling occurs on vessels when they're stationary, okay? And then in particular, you know, fouling is usually much worse in tropical waters, okay? Which is why Indonesia for us is such a great place to do these experiments, because fouling occurs very rapidly and we want to have some kind of longitudinal study. So we start when the ship is clean and then we continually monitor the ship over a period of 1 year as the ship becomes progressively more and more fouled. So yeah, environmental conditions impact how much fouling is going to grow on the hull. But that's exactly what we want, actually, okay? Because through our LDA, through our velocity measurements, and through the surface scanner, we can have a precise record of how the fouling builds up on the hull of the ship and how that affects the flow, how that affects the turbulent boundary layers formed over the hull when the ship is sailing. So yeah, really good question. You know, the fouling would be very different in Northern European waters than it would be in Indonesia or Australia. But for us, Indonesia is a very attractive destination, not just because we like coming to Indonesia, but because the fouling occurs very rapidly there.
And I think, Nick, we should tell the audience, the ship is on Merak Bakahuni route, so it's the busiest route in Indonesia. Yes.
Oh,
so it's
Bakahuni, eh? Thanks.
Yes,
thanks for the explanation. Okay. Yes, thank you, Prof. Nicholas and Prof. Budi for the explanation. I think it's already answered the question from Mr. Rian. And then another question from Yosefus, yeah, Mr. Yosefus. I think it's about the LDA measurement. Prof. Nicholas, thank you very much for your great presentation. If I'm not mistaken, the correlation you found was developed firstly based on the experimental or CFD you did. And then you improve it by conducting the full-scale experiment, considering the other parameters such as the velocity, as mentioned by previously by Mr. Hassani. The question is, since this LDA was mounted in the specific distance in the hull, does it has a significant effect on the sand grain roughness in the position near the nose and to the nose of the ship? Then how we could improve the correlation? Thank you.
Yeah, this is also, I mean, I guess 2 questions here, but also really, really, also really, really good questions. Things that I should have mentioned, actually. So yeah, you're correct. The correlation was developed based on existing experimental data and DNS data from Leon Cham's pipe flow simulations. Now, certainly the idea would be to further refine and improve that correlation based on data that we obtain on the ship. At the moment, we're in quite an early stage still with these measurements. You know, we really need to continue with this project, getting more and more measurements over that hull. That needs to happen while the surface scanner is working so that we have a measure of the whole topography. You know, so you appreciate for that correlation, we also need to know things about the roughness. So we needed to know the average roughness height and the effective slope. And when the scanner's not working, when the scanner's flooded, we can't obtain those values. So yeah, that's a work in progress, but that's certainly something, the reason we designed these shipboard experiments was exactly that, so we can improve that correlation. And then the second question is also very, very insightful. It's that since the LDA is mounted in a specific point, what about if the roughness on the ship, I think this is a question asking, what if the roughness isn't homogeneous, right? And this is a very, very important point. All of those predictive techniques assume that there's a homogeneous coverage of roughness on the ship or on the flat plate. And obviously from those photographs that I showed you, biofouling is patchy, it's heterogeneous, okay? So this is certainly something that we have to deal with. You know, in reality, it's not a single scan on the hull of that ship. It has to be many, many tens of scans all the way over the hull of that vessel from which we need to obtain average statistics. And I think this is another big problem, the way that the marine industry at the moment deals with heterogeneity, you know, has proven problems in terms of accuracy, okay? So this is another thing that Bagus, myself and this collaborative team are working on, together with Akzo Nobel, who are a marine coatings manufacturer. We're trying to address this problem of heterogeneity. But the question here is really good. Roughness at the nose of the ship is known to have a bigger effect than roughness at the bow of the ship. And we have to, if we want to, it's not as important as getting KS, but if we want really accurate predictions, we have to be able to deal with that as well. So yeah, thank you for the question.
Yeah, thank you for the answer. Is it Mr. Josephus? Is it you have a further question or about a response from the Prof. Nicholas? Because I think it's three questions, so I need to.
Yes, thank you very much.
Opportunity to.
Thank you very much for the question.
Okay, thanks. So I check in the chat. There's no more question in the chat. Is it? Please help the organizer. I think I cannot find another question, but still we still have about 5 minutes to. Please check. There's no more question. So, Prof. Nicholas, would you please maybe have another conclusion for the topics based on the response from the audience, and if you have some explanation to add in this topic, I would give you a 5-minute time for this.
Yeah, sure. You know, I don't really have too much to. I don't really have too much to add, other than that this, you know, this project's been very, very nice for me. I usually work in fundamental fluid mechanics in turbulent boundary layers. It's usually quite a esoteric area to study, but this project has been very nice because I feel like, you know, this team that we put together with our Indonesian collaborators, I think we're tackling a really important problem, which is, you know, one that the world needs to address. As you saw, shipping has this very big economic and environmental footprint. And I guess the argument that we're starting to see is that a good deal of the emissions from shipping doesn't need to happen, okay? And it's really, you know, for me, I'm really hopeful that in the next couple of years, we can answer this question, give accurate drag predictions, and then we can take this data either to ship operators, or if ship operators won't listen, then we go to governments or regulatory bodies, and we can make a case that, hey, here's a number of percent of the daily oil production being needlessly burned to overcome drag due to rough surfaces, where, with proper management, we could probably mitigate some of these emissions. So I guess I sound like I'm preaching, but for me, it's just, I'm very happy, really, that this collaboration came together, and I hope that this team can, continue to make a difference.
Yeah, thanks very much for Prof. Nicholas. Actually, I have one question that, if you don't mind, that because your team is also monitoring the whole states of the samples, and then you examine the roughness of the samples. It is the measurement is for the rough, or is it online monitoring during the operation? Could you please clarify this, Prof?
Sorry, can you just repeat the question one more time?
So I think what he asked, Nick, is about
you hear, Prof?
Yeah.
He asked whether we monitor it online with with the scanner, or we do it once in a while, like doing a dive.
Oh yes. Yeah. Once in a while. So that the diver goes down regularly when the ship isn't stationary, and then we can kind of reacquire this set of measurements. And actually, all the device does is take images, and then back in the laboratory we compile those into the reconstruction of the surface of the hull. But again, the question's interesting, right? The LDA, on the other hand, does offer, the laser Doppler anemometer does offer opportunities for online monitoring. So by in the future, if ships would monitor the velocity at a single point on the hull towards the back of the ship, you'd have an online measurement of the hull state that, with some calibration, could give a measure of how bad the hull fouling was, and could alert the operator or the captain that it was time to dry dock or get the ship cleaned.
Okay, thanks very much. Yeah.
Thank you.
I think the time is. Thank you very much. So, Prof. Nicholas and all the panelists and attendants, we come to the end of the session, because already close to the end of the session. So, on behalf of the committee, Thermofluid, International Conference of Thermofluid in Mechanical Engineering, Gajah Mada University, I would like to thanks very much to your valuable sharing, Prof. Nicholas Hachin, and also the collaborator from Dr. Bagus Nugroho. And even though we cannot give you the big applause, but we thanks again for your time and for your valuable presentation. And we hope you would like to share another topics in the next future. Thank you very much. And then I give the time to the MC for the conference. Thank you very much.
Thank you very much. Thank you very much for the invitation.
Thanks very much.
Okay. Thank you very much, Mr. Indro Pranoto, as the moderator for the previous session. And of course, we express our utmost gratitude for Professor Nicholas Hutchins after delivering a very insightful and interesting presentation, especially in the sense that it is a multinational collaborative effort, and it yielded interesting results for the marine industry. And also thank you to Mr. Bagus Nugroho, who contributed to the research and is apparently here with us right now. So on the next session, we will have a break until 12:30 p.m. Western Indonesian time. So that's about 40-ish minutes. And so thank you very much for your attention on the previous sessions. We hope you enjoy your break, and we will see you again on 12:30 p.m. Western Indonesian time. Thank you.
Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology. Over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever.
Hi there. Can you hear my voice clearly?
Yeah, I can hear you loud and clear.
Okay, thanks a lot. I just want to check that my mic have not problem during my presentation.
Okay.
Okay, thank you so much.
Okay.
Sorry. Hi there.
Yeah.
Anyone still there? Can I also check that my share screen still in
Oh yeah.
good perform? So
Okay. Yeah. Yeah. You can share your screen right now.
okay, thank you. Is that clear? Hello?
You have it. Your
Is that fit enough?
I think your share screen isn't turned on yet.
Okay, sorry.
Bây giờ, cái gì vậy?
Okay. So is that fit enough the monitors? Hello? Hello there.
Hello, sorry, pardon.
Is that fit enough with the monitor?
Yeah, yeah.
Okay, so
It's very clear. It's very clear and perfect.
Okay, so thank you very much.
Okay, thank you.
I
Success
will
for your
stop.
presentation, sir.
Oh, thank you very much. Thanks a lot.
Okay.
Located in Jogjakarta, Universitas Gadjah Mada. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology, over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 is one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program
Okay, welcome back to the 11th International Conference on Thermofluid. We hope you had a wonderful break so that you are refreshed and ready for our next round of exciting presentations. Next, we're moving to the heat transfer and phase change, combustion and automotive engineering and thermodynamics and energy conversion paper presentation. Please welcome the moderator for this session, Mr. Agung Bramantia. Mr. Bramantia, are you already here with us?
Yes, okay. Can you hear me, Mr. Fahri?
Yes, your voice is loud and clear, sir. So if you're ready, you can, I welcome you to please guide the next session. Thank you very much.
Okay, thank you very much for the time for me to deliver the moderation for this session. So, ladies and gentlemen, welcome back to the 11th International Seminar of Thermofluids, which we hold by University of Gadjah Mada. Now we move to the paper session. We have 7 serial paper which is on the field of heat transfer and phase change, combustion and automotive engineering, and thermodynamics and energy conversion. I would like to introduce myself. My name is Agung Bramantia. I would be very pleasure to be your moderator in this session. So I would like to check the first presenter, which is Mr. Yosefus Ardian Kurnianto Prayitno.
Yes, Pak Agung.
Okay, I think now it's time on my side is 12:35. So, are you ready to present it?
Yes, Pak.
Okay, please, the time is yours. Please.
Okay, thank you very much. So, first of all, let me share my screen. Could you see my screen, Pak Agung?
Yes, yes.
Okay, so.
Very clear.
Okay, let me start my presentation. Okay.
Okay. Yeah.
Okay. Thank you very much. Good afternoon, everyone. It's a great honor for me to present my presentation entitled "A Simulation and Experimental Study on Particle Volume Fraction of PMMA Suspension in Centrifugal Fields." Me myself, Yosefus Ardian Kurnianto Prayitno, currently a PhD student in Chiba University. We are sending our gratitude to all of my lecturer in the Gadjah Mada University and also for all the participants. So today's presentation it will be divided into 4 sections. So the first one is the background and goals, and then we will talk about the method setup and condition, and then let's go through to the result discussion, and lastly the conclusions. So as the break,
could you move
yes.
to the full screen of your presentation?
I'm sorry. So let me swap.
Yeah.
Okay. Is it now okay?
Yeah. Okay.
Okay. So thank you very much. Yeah. So as the research background in the industrial processes, so mixtures mostly applied as a suspension transport. So also as the product of the industrial processes. So in this research, we want to discuss about how the separation will be conducted or will be measured based on the industrial case. So industrial suspension, for example, in these parts, and then when we want to separate it into the solid and liquid phase, then we found current problems such as conventional techniques The conventional techniques here mostly analyzed by the output of the centrifuge in the centrifugation process. For example, considering the feed rate, rotational speed, and then also the field level. And all of those conventional techniques leads to the indirect measurements. But one of our approach here, we have the direct measurement in terms of wireless electrical resistance detectors. This approach is based on the electrical resistance thermography techniques, which has high temporal resolution to detect the separation inside the industrial centrifugation. But the challenge is still there, and one of the challenges is the suspension behavior inside the centrifugal fields. So so we divide the goals into two. First one is the simulation study, and then the second one is the experimental study. So there is the three kind of goals. The first one is how we can see the suspension behavior under the particle concentration dependent, and then how we can see the in situ particle volume fraction from the WERT, and then how we can make the models from the continuum constitutive, and then we can see the correlation between the WERT. Now let's talk about the method, setup, and condition. And from the numerical model, basically we have the density difference between two phases. So in this part, we have a particle concentration dependent in the momentum equation and then viscous model. But the most important thing is the particle concentration dependent is also considering the non-Newtonian viscosity. So from here, we consider the particle flux, which consists of diffusion coefficient, shear tensor, and then Hindred-Selting function, and also the settling velocity. And from all of the numerical models, then we have the mixture viscosity, the mixture model, transfer model, and then slip velocity for the particle flux. Then we can get the result for the suspension behavior. And for the fitting model, for the particle volume fraction, we develop this kind of fitting as a function of time and the radial position from the numerical methods, and we evaluate based on the standard deviation. With respect to the WERT measurement, we consider the Maxwell-Wagner equation to get the measurement principle of the WERT, which is related to the measurement domain of our device. So basically, we only, how can I say, measure the conductivity inside the measurement domain, and then based on the effective medium theory, then we can get the correlation between the physical and electrical, so in terms of the conductivity and the resistance. And for the simulation setup here, as we can see, the two-dimensional geometry, considering the radius of the pool and then radius of the pole, and then we do the meshing structure. And in this case, we use the COMSOL. So in COMSOL, when we want to evaluate the mesh, we use the growth rate and the skewness. And as we can see in this one, in the key points, the growth rates and the skewness averaging from 0.8087 and 0.91, which has close to the best possible value. So it's acceptable to continue this simulation study. And then for the boundary, as the initial value, of course, we have the velocity field, pressure, and the particle volume fraction, and both of the properties of density and viscosity. And then we have the assumption or the simplification that our two-dimensional simulation only simplified as a closed flow. And then in this case, we do simulation in the two kind of centrifugal force, high and low. And then talking about the experimental setup, this is our experimental setup. So we have the WERT mounted in the real centrifuge. So we have the electrodes in here, and then we have the WERT, and basically we have the wireless communication to send the data. So basically this is the in situ particle volume fraction we have from WERT. So how about the results and discussion? As we can see in this part, so yes, under the high centrifugal force, we can see the mechanism of particle migration from mixture or initial condition to settling and settle very clearly, and it's very fast sedimentation, ranging from 0 to 5 seconds. And then compared to the lesser centrifugal force, it can be seen that in the 2 seconds we can still see the settling velocity, which is lower than the maximum particle volume fraction we can get. And for the settling zone, we can get from the results. So we can see the distribution for the lesser centrifugal force. The distribution is lean, so we can see lean compared to the higher centrifugal force, which is giving a shock from T1 to T2 seconds to T3 seconds. And if we interpret it into the mixture, interpret it into the settling zone, so we have the mixture zone, settling zone, and the settled zone, and then we compare these two force, and then we can get this one. So yeah, I think it's acceptable for the lower force, giving us the linear distribution. And lastly, for the for the prediction of particle volume fraction based on the numerical results, so we have the radial position here, 0, and then 5 millimeters, and then 10 millimeters. So based on our fitting model, which is refers to the average particle volume fraction, we can get a good agreement for a radius of 10 millimeters. And when we apply this one in the real condition of the experimental, which is an initial particle volume fraction in 0.1, we have this kind of tendencies, which is it's quite different with the experimental setup because it gives us lean tendency. But it has a different condition actually. But in under 5 seconds, we can see the range is quite acceptable. So as a conclusion, so first of all, the numerical model has a limitation to provide a good result. Yes, because in the experimental we compare to the continuous flow, and then in the numerical model we do in the closed flow, and then the higher value of maximum volume fraction could not be reached due to the segregation process in the AVM as a viscous suspension mechanism, and then the fitting model giving us a good agreement only in the very first condition of the experiment phenomenon. So in order to enhance this kind of fitting models, we would like to improve our the boundary. So we adding some to the summation for the particle concentration related to the continuous flow. So that's all for my presentation. Thank you for listening.
Yeah, thank you very much for your very good presentation, Mr. Ardian. So now it's time for question and answer or comment from the panelists or attendees. So please, if you have a question or comment, the panelists or attendees, you could drop to the question and answer box. Okay, I have a short question, Mr. Ardian.
Yes.
You use two methods, which is simulation and experimental.
Yes.
How you make a validation? Yeah.
Okay. Yeah. Yes. Thank you very much, Kun, for the great question. So basically, the WRT itself, so the experimental setup already has the validation based on the this one. So this part, we have the validation for we have the validation of the WERT based on the experimental study with the manual manual measurement on the outflow of the particle volume fraction from the centrifuge. So from that we averaging particle volume fraction between the centrate and the sludge we measured in situ, and then we compare with the WERD measurement, and then we have the good agreement which is published in this 4 publication. So that's why in this study, we want to see how about the suspension behavior by doing the approach by COMSOL. So we in the first thinking, we hope to get kind of a same tendency and good relation, but since in the COMSOL itself has the a limitation due to the closed flow, so the result is slightly different. Thank you.
Okay, kind of validation. Okay, is there any question from the audience or the attendees or panelists? So please give any question if you have. We have one minute left, I think. So how about your particle diameter
Yeah, I forgot to put in. Yeah, so in this study we use 10 micron millimeters. So basically it's a colloidal suspension. Yeah, it's a in the term of suspension. Yeah, so we put in inside the due to our measurement with electrical measurement. Our how can I say, like, experimental setup is based on the sodium chloride 1.5 weight%, and then the PMMA is about 0.1 weight%.
Okay, yeah. Do you consider about the Brownian motion or Brownian equation in this?
Yeah, that's a good input, Pak Akun. So yeah, so we are now in the currently we try to get this kind of a correlation with the Brownian motion, but we haven't get the result yet. So thank you.
Okay. Yeah, thank you very much for Mr. Arden. Actually, we have one question from Mr. Indro Pranoto about the how to measure the volume fraction. But the time is finished, so you could answer by the texting. Yeah, texting. Type the answer in the box.
Yes,
okay.
We'll do it.
Thank you very much for
Thank you very
Mr.
much.
Yusuf Adrian. Give applause to your good research and presentation. So next, we would like to move to the next presenter, which is Mr. Yaya Triastian. Please prepare your PowerPoint. Mr. Yaya Triastian and his colleague Nur Busairi, Muhammad Muflihun, and Halomon Parningotan would be like to present their research titled Failure Analysis of Water Wall Tube in Circulating Fluidized Bed Boiler. So, Mr. Yaya, are you ready for your presentation?
Yes, Pak, I'm ready.
Okay. So,
can I share my slideshow?
Yeah. So the time is yours. Please have a good presentation.
Okay. Thank you, Pak. Can you see my slideshow?
Yeah,
Mr. Ramantia?
Yeah, very clear.
Okay. Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen, the Honorable Thermofluid Committee, academician, and all participants. Let me introduce my name as the presenter for today. My name is Yaya Triastian, and other author, including Mr. Nur Ahmad Busairi, Mr. Halomon Parningotan, and also Mr. Muhammad Asin Muflihun. Today, we will share some information regarding our boiler operation with a title, Failure Analysis of Water Wall Tube in Circulating Fluidized Bed Boiler. The background of the research. We have some case that was happened in the last 2 years. The first one that we can look at the picture in the slides. So the first one that was happened in 2018 happened in around secondary airport, and the second one happened in Lucille outlet, and both of them have a similar area of damage. And the most important thing, erosion, such as tube failure, as the main cause of non-productive time around in the CFB boiler. For the material and experimental methods, we use material SA210A1 for leak case in 2019 with a thickness tube of about 5 mm. That material operates in the combustion temperature of about 960 degrees Celsius. And we use some different methods to approach the root cause of analysis. The first one, we use scanning electron microscope, EDX, in situ metallography, thickness, visual observation, and spectrometry. For the first visual inspection analysis, these tubes are having a similar location damage that was placed near the feeding board that we can look at the left and the right picture. The feeding board has an angle of collision than other place surfaces in the water wall area. It has an important role in the tube erosion process. The wear increases if the angle is increased. For the second visual inspection result and analysis, after we clean up the surface of the failed tube, we can look so many spots that are attacked by pitting corrosion. In this type of hot corrosion, low metal boiling, a tactic mixture of natrium sulfate and cobalt sulfate causes pitting characteristic in the confinement. This limited nature corrosion is related to local damage due to erosion, thermal cycling, and chemical reaction. For the third visual inspection result and analysis, in this case, the failed tube may be affected by fallen refractory. The strength of refractory is a critical aspect to withstand complex operation in the furnace. The CFB boiler itself has a different working condition with a PC boiler. The distribution of material, coal size, and recirculation of material in the furnace may lead to the severity of abrasion and erosion. The higher gas velocity, the higher the abrasion effect which can attack in some area equipped by the refractory as shown at the right figure. We can look at the right figure. We have a thick line that equipped by the refractory. The refractory itself has a function to avoid the direct contact between the water wall tube and the material of the combustion. For the thickness analysis based on the thickness measurement, as shown at the right table, the tube had lost 42% of the thickness tube due to lifetime operation. However, under impact speed, concentration, and angle of impact, the dimension of the particle has substantial effect on the wear. For the in situ metallography analysis, if we compare to the ASM reference, we still have the microstructural still looks similar. With 200 times magnification at the cross-section observation, the field sample shows the existence of stress corrosion cracking with 174 micrometer of length. We can look at the right picture. There is a road of cracking that's visible and may trigger the failure. A stress corrosion cracking that was found on this tube by referring to the Srikan study that the failure in the water wall tube can be credited to stress corrosion leak that induced by sodium and iron phosphate. For the same EDX result and analysis, the corrosion product is present on the failed tube. In more detail, we use EDX to analyze. It revealed an internal deposit formed from the water element, like calcium, silica, magnesium, are general pollutants that persist in the makeup water or feed water even after filtering has occurred. Moreover, oxygen scavengers that are used to deaerate water may have a sulfur content. Regular treatment and analysis of the feed water are essential to prevent deposits. The removal of the inner scale has periodically been important to ensure better heat transfer and avoid overheating on the premise. For the last analysis, we use spectrometry. This was conducted for detecting suitability material from the leaking tube with as-received material referred to as SME SE 210A1. The right table shows the phosphor element that show differences from the standard as the maximum value that should be less or equal from the 0.035, and the other elements revealed equivalent. It may cause by an imperfection in the preparation test or manufacturing effect and becoming a negligible aspect in the root cause of failure analysis. For the conclusions, number one, visual examination of tube showed abrasive rupture near to the feeding port that means to have a bigger angle of collision than other positions in the water wall tube area. Moreover, it can cause by fallen refractory. Number two, same EDX results revealed if the internal deposit from the water element that was a common contaminant that remains during feed water treatment in the boiler. Calcium, silica, and magnesium are general pollutants that persist in the makeup water or feed water. And number three, spectrometry observation revealed the phosphor element with differences from the standard value, but it may cause by an imperfection in the preparation test or manufacturing effect. Thank you for your attention.
Okay, thank you very much for your presentation. Very good presentation, Mr. Yaya Tirasdian. Now it's time for us to have a discussion session for your presentation. So please, for the panelists and the attendees, you could drop the question in the question answer box, or you can text in the chat box. Is there any question? Yeah. We have a question from Mr. Agus P. Nuryadi. And the question is, have you predict hydrogen attack? for the failure analysis, have you predict for the hydrogen attack, Mr. Yaya? Please unmute yourself.
Okay. Okay. For this case, I don't have yet to predict the hydrogen attack. But for this research, we just use 5 methods that as I mentioned before, we use just like visual observation, SIM-EDX, and the others. But maybe
Okay.
that is the further our research interest. Thank you, Pak.
Okay. And is there any other question? Okay, if there is no from the audience, I would like to give a question, a short question. You mentioned for the failure, it is caused by erosion and corrosion. Yeah. So which one is the give the most impact, corrosion or erosion?
Okay, Pak. Thank you, Pak, for the question. For myself, for the most impact that caused by the erosion, the first thing, because the abrasion, it comes from the velocity from the bed material. So it can impact the refractory to fall, and it can give access to direct contact between the water wall tube and the material of the combustion. But for the corrosion, also have an impact. Like like from the EDX observation, the corrosion product can lead to the overheating. That's all, Pak.
Okay. Is there any other question? We have 3 minutes left for the discussion. Okay, Mr. Yaya, you use spectrometry, right? For the measurement, do you use a spectrometry?
We use.
Do you have a limitation to use this kind of measurement in your case? The limitation. Limitation, keterbatasan atau kesulitan yang didapatkan.
Oh, yeah. No, but we don't have a limitation for the observation using the spectrometry, but we have to comply the manual, because if we did a wrong observation, like we use one sandpaper to sample for 2 sample, it cannot absurd, it cannot confuse the results. For example, like that. And we have to use a proper electrode to get the best result for the spectroscopy.
Okay. Yeah, I think it is enough for the discussion of your research and presentation. So give the applause for Mr. Raya Trasdian and the colleagues for his good presentation and very good research. We hope you can expand your research and collaboration with other academicians in this university and around the international. Okay, thank you very much, Mr. Trestian.
You're welcome.
Next, we would like to call the next presenter, which is Mr. Nivetana Kumar and Vasudevan Raghavan. Are you ready for your presentation?
Yes, sir, I'm ready.
Okay, so please prepare your PowerPoint and time is yours.
So is it my PPT is visible?
Yes, very clear and visible.
Okay, sir. Let me introduce myself. I am Nivetana Kumar, doing MS Mechanical Engineering in Indian Institute of Technology, Madras, India. So I am here to present a paper titled Numerical Simulation of Biogas Flame using OpenFOAM. So let us start the presentation. Outline of presentation, introduction, scope of study, computational domain, boundary condition, solution methodology, validation, results and discussion, conclusion, references. So introduction, in recent times, due to the depletion of fossil fuel and the environmental aspect, there is a tremendous rise in the usage of renewable resources. So biogas is one such renewable resource which has huge potential to replace the fossil fuels in several applications. But the main drawback of using biogas is the presence of carbon dioxide in the biogas. So the adverse effect of carbon dioxide in biogas is discussed in detail in the presentation. Usually biogas contains carbon dioxide ranging from 30% to 45% by volume. In my study, I have used 3 different biogas composition with 30%, 37.5% and 45% of carbon dioxide by volume, and rest is methane. So scope of study is to conduct numerical simulation using OpenFOAM. OpenFOAM is a free open source software, and the reacting foam solver I have used as a base solver for solving a reactive flow module, in which I have made some modification like inclusion of fixed diffusion, Soret diffusion, radiation submodel to account for accurate diffusion dominant flows. And next thing is to validate the numerical results with the experimental data and find the flame temperature, field, species, mass fraction, and etc. to study the behavior of the flame. Next is computational domain. The right side is the computational domain. Here it is obtained, the domain is obtained from the experimental study of Makov et al. It is a co-flow burner used for simulating methane flames in diluted with nitrogen. So here we can see that the fuel enters here and the co-flow air enters in the annular space. The fuel and air is separated by the fuel tube. Fuel tube is made of stainless steel which have outer diameter of 10 mm and inner diameter of 7 mm. And in radial direction, domain is extended up to 47.5 millimeter, and in axial direction it is 200 mm. And 35 mm inside diameter is considered because to consider the fully developed flow. So this is the computational domain. Basically, it is a 2-dimensional axis symmetric boundary. And coming to boundary conditions, the main boundary presents are fuel inlet, co-flow air inlet, outlet, and right side boundaries, burner tube, and axis. So let me explain in the diagram. At fuel inlet, you have to specify velocity, which is calculated from the power rating of the burner, and the fuel species mass fractions are specified along with the temperature of the fuel. And in co-flow air inlet, we have to specify the velocity, which is calculated from the stoichiometric mass flow rate, and velocity and species mass fraction of nitrogen and oxygen are specified here with temperature of 300 Kelvin. Since it is an unconfined burner, outlet and right side have given atmospheric pressure, where velocity and temperature are interpolated from the neighbor cell using a Newman boundary condition. And since it is an axis symmetry problem, axis is given a condition of symmetry boundary condition. And this fuel tube forms a solid region in the domain. It is coupled with the gas region. So these are the basic boundary conditions in the domain. Next, in solution methodology, initialization of data is carried out using the suitable values at the internal nodes of the domain, like zero velocity, temperature of 300 Kelvin, and the corresponding mass fraction of oxygen and nitrogen. It is nothing but the non-flow atmospheric condition is used as initialization. And chemical kinetics mechanism of GRI MEC 2.11 is used, which consists of 25 species and 121 element reactions. So initially, fuel and air are allowed to mix properly, and after some iterations, they are ignited to a temperature of 1500 Kelvin to obtain a small flame. And since it is a steady state solution, the convergence criteria used here is 10 power minus 6 for all the governing equations. So coming to validations, the numerical results are validated along with the experimental data obtained from the Makov et al. Here, 3 meshes are considered for the grid independent study, with coarse mesh consists of 16,245 cells with minimum cell size of 0.5 millimeter in both the direction, and intermediate grid consists of 32,775 cells with 0.25 mm cell in radial direction and 0.5 mm in axial direction, and fine grid consists of 56,350 cells with 0.25 millimeter cell size in both the direction. So seeing this plot, we can find that this box represents the experimental data, and these 3 lines represent the coarse, fine mesh and intermediate mesh. It is very clear that fine and intermediate are very close to each other and also close to the experimental data. Hence, this intermediate fine grid size are used for the parametric study. So coming to results, these are the plot tells us temperature profile along with stoichiometric equivalence ratio. It is very clear from the 400 Kelvin and 1000 Kelvin that with increase in the carbon dioxide in biogas, flame length increases, and also it is observed that stoichiometric equivalence ratio exactly lies at the maximum temperature, and also the temperature keeps on reducing with increasing carbon dioxide. So second observation is it's a plot of oxygen mass fraction with velocity vector. Here it is clear that consumption of oxygen decreases with increase in carbon dioxide. So which also shows that flame lift off from the burner with increase in the carbon dioxide in the biogas. Also, velocity vector increases near to the axis because of the buoyancy effect. Since the mixture gets heated up, due to the buoyancy effect, the velocity near to the axis will rise up. This plot shows the oxygen production rate with OH mass fraction. OH species helps in the formation of both CO2 as well as H2O species through the elementary reaction given below. CO plus OH gives CO2 plus H, and H plus OH gives H2O. Here also we can see that reaction zone itself moves away from the burner with increase in the carbon dioxide. This plot shows HO2 mass fraction with H2O production rate. It's very interesting phenomenon that HO2 is a species which forms in the low temperature exothermic reaction. So it acts like an indicator or a boundary for the reaction zone. Here it is very clear that H react with O2 forms HO2. We have seen in the oxygen contour, this consumption of oxygen increases with decrease in the carbon dioxide. The reason is the oxygen react with the hydrogen to form HO2. It is observed here. The preheat region is very close to the burner rim, so it consumes more oxygen. That's the reason we get consumption of oxygen near to the burner rim in case of low carbon dioxide, which means it increases the stability of flame. So with increase in carbon dioxide, the flame stability basically decreases. Next is, this shows that the mass fraction of CO and OH, both the maximum value of CO and OH get decreased with increase in carbon dioxide. So basically, with the rise in carbon dioxide in biogas, the radicals like HOH decreases, which decreases the flame temperature and also the overall reaction rate of the mechanism. This is the most adverse condition of presence of carbon dioxide in biogas. Next thing is, the carbon dioxide is formed little away from the fuel compared to H2O. This is because of the presence of hydrogen which have high diffusivity. And coming to conclusions, the numerical model includes multi-step chemistry, variable thermophysical properties, fit diffusion, Soret diffusion, and radiation submodel. And I have just developed a solver using all this, including these parameters. Then this solver is used for simulating the results and validated against the experimental data from the Markov et al. Paper. And regarding this biogas flame, the flame temperature decreases with increase in CO2 content, and also flame lift off from the burner with increase in carbon dioxide. OH species helps in the formation of CO2 as well as H2O, but H2O forms closer to fuel tube, and the CO2 forms closer to the airflow because of the high diffusivity of hydrogen. And the most important thing is, with increase in the carbon dioxide, the radicals like hydrogen and OH decreases, which in turn causes the flame temperature to fall, and as well as the overall reaction rate of the mechanism decreases. This is the most undesirable phenomena of carbon dioxide in biogas. So like this, understanding the flame structure and the characteristics of biogas with varying carbon dioxide is essential for fuel in several applications. So CFD simulation is able to provide a physical insight like flow fields, temperature, species, reaction zone, which are very difficult to using a normal measurement techniques. And also validated numerical model can be used as a design criteria for burner to get optimized design solutions. With this, I conclude the presentation, and these are the references, and thank you.
Okay, thank you very much for your presentation, Mr. Kumar.
Yes, sir.
Very punctual time, yeah. Okay, now the next is for the next 4 minutes. We would like to use this time for discussion. Is there any question or comments from the panelists or the attendees for this very good presentation? Please. Okay, I just wondering about your meshing.
Yes, sir.
Mesh, yeah. Do you do the mesh independency test?
Yes, sir. I did my independency test.
So how you divide it from the, I think, 16,000 to the 30,000?
Yes, sir. Basically, what I did is I just fixed the cell size. Like for coarse mesh, the cell size will be 0.5 mm. So correspondingly, I get equal number of cells in my domain.
Okay.
So I initially fixed the cell size of 0.5 mm. Then I simulated the case. I got the result. Then I find the cell size to 0.25 in the radial direction. I get much closer results to experimental data. Then again, I just fine-tuned my grid size to 0.25 in both the direction. So I can just see little increase in the accuracy.
Okay. So in this mesh, do you consider about boundary condition?
Yes, sir.
Yeah. So Yeah, that one. So on the wall, it should be very small size of mesh, right?
Yes, sir. It's a solid region. It's like a conjugate heat transfer. Actually, I don't have time to explain that. That's the thing I didn't explain. This burner fuel tube forms a solid region which is coupled to the gas region. The boundary condition will be like at the interface, the temperature will be same, and the heat flux leaving the gas phase will be equal to the heat flux entering the solid domain. That's the conjugate heat transfer boundary condition between solid and the gas phase.
Okay. So yeah, we have a question from Mr. Adrian Kurnianto. Yeah. So he have a question: how we could use CFD result to predict the experimental data since you have a good insight of physical phenomenon. It is appear in the chat.
Sir, can you tell me the question again?
Yeah. How we could use CFD result to predict the experimental data since you have a good insight of physical phenomenon.
The reason is if you're going for experimental study, it will require a lot of advanced instrument to study the reaction rates, like such a few phenomena like reaction rate and elementary reactions. What are the species involved in the reaction? Such things will be very difficult in experimental study. But compared to experimental study, numerical study can give a proper insight on this each elementary reactions. Like I have used 25 species, 121 reactions, so that I can just go and study the properties of each reaction, what is the reaction rate of each reaction, and also the production rate of each species, which is very possible in CFD simulations compared to experimentals.
Okay, I think he is referred to your last conclusion, I think. Yeah.
Yes.
Yeah, the last conclusion. You make simulation in 2 dimensions, right?
Yes, sir. It is 2-dimensional axis symmetric.
So do you have
axis
a plan
symmetric.
to? Yeah. Do you have a plan to do in the 3-dimensional?
Yes, sir. Next, my plan is to, so far I've explained the adverse effect of carbon dioxide. Now my future plan will be to how to tackle this adverse effect to improve the efficiency of the biogas fuel so that we can use the biogas in several applications. Next thing will be to enhance the turbulence property, which I have to go for 3D simulations. So in my future, I may do that, but up to now, I didn't proceed with that. My next step will be how to tackle the adverse effect.
Okay, yeah. Okay, yeah, I think the time is up for us for discussion. So thank you very much again for your nice and good presentation, Mr. Kumar.
Thank
I
you,
hope
sir.
you can have a good result for your next research. Okay, good afternoon. So we move to the next presenter, which is Mr. Fauzun and Adipurna Firman Satriangga.
Yes, sir.
So are you ready, Mr. Firman?
Yes. Wait,
okay.
I will show my slide.
Okay.
Test.
Yeah. So the time is yours.
Can you see my slide, Mr.
Yeah.
Ram?
Yeah. This is the last slide. Okay.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Today I will present about numerical analysis of the effect of flip-ups configuration variations on the aerodynamic performance of rear wheel of student formula car Bima Sakti UGM. So my name is Adipura Firman Satriangga, and the other author is Mr. Fauzan ST MT PhD. So wheel aerodynamics are quite important in the field of car aerodynamics, especially in open wheel type cars like Formula One, because the wheels that are exposed to air directly can contribute a lot of drag value received by the car as well, and the wheels are also able to create positive values, which can reduce the aerodynamic performance of wheels and cars. The lift generated by the wheels is caused by this stagnation point, which is located in intersection of wheels and the road. When the air flows through that part, the air will be trapped and there is no way to escape the air, so that the air is in a very low velocity condition or even become static. Due to the low aerosol velocity, it creates a high pressure area in that section, whereas on the top surface of the wheels, the air can accelerate quickly, creating a low pressure area in that section. This pressure difference causes the wheels to produce lift values. So the first is the research will look for areas of optimization in line of the flip-ups component. The purpose of this research is to improve aerodynamic performance, coefficient of lift divided by coefficient of drag of the rear wheel of the Bima Sakti car. The fluid will flow through either the top of the or the side of the rear wheel. Thus, the flip-ups component will be placed on the front of the rear wheel. And this is a base geometry airfoil for the student formula. In this research, the flip-ups component will use a Epler E423 airfoil geometry. Epler E423 is used in a student formula cars because in other FSA team journals, it is stated that this airfoil is have high lift characteristics and easy to manufacture. And considering the many variables that can affect the design of the flip-ups component, some limitations are needed so that it will be easier to analyze the effect of this component on the performance of the rear aerodynamic of this car. The limitations are placement of the flip-ups component, flip-ups geometry, distance between the main airfoil, element 1 and the floor, the position between the airfoil element 1 and element 2 and the angle of the two airfoils. Variation in the number of airfoils element is limited from one element to two elements, and variation of the angle of attack is limited to 35, 40, 45, 50, and 55 degrees. And so here is the flip-ups component design using one and two element with angle of attack of 45. Given that the purpose of this component is to flow air over the wheel to reduce drag, theoretically, the angle of attack of the component should be about 45 degrees, even though the airfoil angle to maximum the value of downforce against drag is between 5 to 10 degrees. Therefore, the simulation is carried out by varying the angle of attack. And here's the component of the flip-up using two elements with a various angles of attack. And then making simulation models based on the actual 8th generation Bima Sakti car. However, because this car uses many components and so complex, so it requires a simplification of the simulation model in form of a solid body, but still refers to the original shape of the car. Then the next is making the enclosure and a body of influence. In this study, the determination of the enclosure dimensions will use reference to the LIP FSA, where the velocity inlet has a distance of 1 time car length from the front point of the car, and then 3 time length of the car for the pressure outlet, and the bottom, top, and the side is designed as a moving wall. And the body influence is useful for producing a more detailed mesh in order to get a more accurate simulation result and can see more detailed flow pattern. And next, aerodynamic validation. The validation of the simulation method is to simulate model according to predetermined reference journal. In this study, I use research by Rafi et al. In 2030, namely simulating airfoil NACA 4412, and will be compared with the experimental results in the theory of wing section that written by Abbott. And for air properties is equated with the journal. And Rafi et al. Performed simulation in 2 dimensions, while the researchers performed simulation in 3 dimensions. The validation result of the simulation method show that there are similarities in the aerodynamic characteristic of the NACA 4412 airfoil when compared between the simulation result by Rafi and the experimental result by the Abbott. Airfoil NACA 4412 began to have a pre-stall condition at angle of attack between 12 and 14, and began to stall at angle of attack of 14 degree. Because of that, we can predict the aerodynamic phenomena that happen so that this method can be used to analyze further research. And this is a massing independency. We can see that in the graph in front that the greater the number of mass element, the smaller the coefficient of lift value, and a small change in value when we add the number of element. Using mass around 9,900,000, we'll get a very small error value, which is below 1% and more efficient time. So this is a model with a variety of simulation model configuration that will be limited to only the flip-ups component with a maximum of 2 elements. And in the simulation, we use a pressure-based software, steady state. Then we use K omega SST model because it gives accurately predict the boundary layer and separation. We used couple scheme for faster convergence, and we use second order upwind for accurate result. And this is the result for the simulation without flip-ups. In the simulation model without flip-ups, there are still many areas of high pressure on the front of the rear wheels. This happened because there is still a lot of air hitting the rear wheel directly. At the bottom of the rear wheel, there is a red area, and that is the stagnation point where the airflow cannot get out from that part. This caused the area to become an area with high pressure. And we can see on the streamline visualization that the airflow is still very much hitting the rear wheel directly and causing the drag received by the rear wheel to the car to get bigger.
Your turn.
Then when for the one element flip ups, we can see that the wheel this component can reduce drag received by the front of the rear wheel. And then there's the 2 element flip ups. We can see that the red area on the top of the tire has disappeared too. The use of the flip ups component with 2 elements can flow more air over the wheels when compared to using flip ups component with 1 element. This can be clarified by looking at the fluid visualization streamline around the rear wheel. Thus, the use of the flip ups component with 2 elements can reduce the drag value received by the rear wheel when we compare to using the flip ups component only 1 element. But unfortunately, the use of flip ups component can increase the lift on the rear wheel of the car because there is a lot of low pressure area between the rear wheel and the flip ups. The increased low pressure area between the rear wheel and the rear of the flip ups further increase the lift of the rear wheel, increase the pressure difference with respect to the pressure at the stagnation point. However, the use of the flip ups component can improve the aerodynamic efficiency of the car overall. This component can increase the downforce of the car. On the other hand, this component can significantly reduce the drag on the rear wheel of the car. And this is the coefficient of lift divided by, sorry?
Can you make it faster?
Okay, so this is the result. We can see that 2 element flip ups can give a better aerodynamic performance. Then next we continue by varying the angle of attack. And as you can see, more angle of attack, it can reduce more drag in the rear wheel. And this is the visualization of the pressure contour of the rear wheel with 2 elements. If we have a greater angle of attack, the less the drag value received by the front of the car's rear wheel. But if you pay attention to the drag value of the simulation result in the previous slide at the angle of attack 50 degrees, it's actually increased drag value received by the rear wheel of the car because due to the flow of air that rotates on the side of the rear wheel, so that the drag value on the rear wheel of the car increase. And this is the table shows that the coefficient of lift divided by coefficient of drag of all simulation model of variation of angle of attack on a model flip ups component with 2 elements. From the simulation result of the 5 models, the aerodynamic performance is obtained in the configuration of the flip-ups component with 2 elements with an angle of attack 45 degrees. So the conclusion is the use of flip-ups component can reduce aerodynamic performance of the rear wheel of the Bima Sakti generation 8 car because the more low pressure area between the rear wheel and the flip-ups, so that the lift rear wheel to be greater, but can increase the overall aerodynamic performance of the car due to the flip-ups can increase the downforce while reducing the drag of the rear wheel of the Bima Sakti 8 car. Okay. I think that's all. Thank you.
Okay, I think the time is already up. Yeah. So if you have any question from the audience and panelists, you can type on the question and answer, but the answer would be not in the live session, but maybe in the text, yeah, texting, I mean. Okay, because of the time is enough, so give the applause for the good presentation for Mr. Adiputra Satriangga. I think you have a good presentation and good research.
Thank you, Mr.
Thank you very much for Adiputra Satriangga.
Thank you, sir.
Next, we move to the next presentation and next research, which is the entitled "The Effect of Camshaft Modification on Engine Performance in Automatic Transmission Motorcycle." So, who will be the presenter? Sorry for the title of the committee for the next presenter. Are they ready?
Sorry, Mr. Bram, I don't think the next presenter is here. Perhaps you could move to the next order.
Okay. So we move forward to the next presenter, which is the entitled "Thermal and Thermodynamics Optimization of a Porous Double-Layered Microchannel Heatsink," which is the author is Mr. Sahid Adiwali Adio, Mr. Ridwan Olawale Olagoke, and then Timothy Adefeni Alo, Ade Dotun Emmanuel Olalare, and Adam Olatunji Muritala. So, Mr. Ridwan, sorry for the time because of the previous presenter is not in this session, so we move forward to your session. Are you ready for your presentation, Mr. Ridwan?
Hello, can you hear me?
Yeah, very clear.
Hello.
Your voice. Hello. Can you hear us, Mr. Ridwan?
Yeah, am I? Can you hear me, please?
Okay, you can share your presentation PowerPoint.
Can you hear me, please? Hello?
Hello?
Can you hear me? Can you hear me?
Yeah, I can hear you. I can hear your voice. So time is yours, Mr. Ridwan.
All right, thank you very much. Okay, let me share my screen, please. Okay, can you see my screen?
Yes, very clear your slide.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Good afternoon, everyone. So I'm Ridwan Olawale Olagoke. I'm presenting a paper titled "Thermal and Thermodynamics of Optimization of a Porous Double-Layer Microchannel Heatsink." My co-authors are Dr. Said Adewale Adio, myself, Ridwan Olawale Olagoke, Mr. Adidotun Emmanuel Olalere, Mr. Timothy Adefemi Alo, and Dr. Adam Muritala. Yeah, the content of the presentation here is we have introduction, we have methodology, we have aims and objectives, we have literature review, result and discussion, and the conclusion. Introduction. Microchannel heat sink is usually a rectangular channel which comprises of substrates, that is the solid parts, and fluid parts, which will be the cooling or working fluid. The substrate conveys the generated heat. As we can see from this side, this is the example of the microchannel heat sink. We have this base, the portion where my cursor is moving around now is the substrate. This hollow part is the coolant pump, the coolant surface, which is the fluid. So this base, the base of the substrate will be mounted on an electronic device, and it will convey it from the device. The heat generated in the device is conveyed through conduction, and the fluid flowing through the hollow channels conveys the heat generated by convection. So the problem statement: the more sophisticated and compact modern electronic devices are, the more the need for compact cooling systems to improve performance of the devices and prevent continuous thermal throttling that might lead to equipment damage and irreparable loss. There have been numerous researches regarding that, and more of such research are still pivotal to adequately get rid of the thermal problem. So the aim of the research, the aim of the study is to optimize thermal and thermodynamic performance of a porous double-layer microchannel heat sink. And the objectives are to determine the effect of porosity on thermal and thermodynamic performance of microchannel heat sink for varying porosity, and also to investigate aluminum oxide water nanofluid. The aluminum oxide is the nanoparticle, while the water is the base fluid. So to investigate that, the effect of that on thermal performance of microchannel heat sink, and also to optimize the orientation of pin inserts in the microchannel heat sink. So we have, like I said, there are numerous researches. A few of them is that we have Tuckerman in 1981, where he carried out a research on high performance heat sinking for VLCI, and he concluded that based on the result that the novel microchannel heat sink can effectively solve its situation problem in electronics. So now also we have Mohammadi and Thurger in 2018. They carried out the research on thermal performance improvements of the double-layer microchannel heat sink by introducing aluminum oxide nanoparticles into water. And they concluded that their result revealed that optimization of nanofluid as the working coolant for double-layer microchannel heat sink while optimizing physical and geometrical parameters give an excellent design for the double-layer microchannel heat sink. Also, we have Sen et al. In 2017. They carried out research on computational optimization of counterflow double-layer microchannel heat sink subjected to thermal resistance and pumping power. So they concluded that thermal performance of microchannel heat sink can be achieved via optimization algorithm. So the methodology used in the research, this is the whole system, which is the microchannel heat sink, the double-layer microchannel heat sink. So because of how heavy it is for us to simulate and investigate the whole system, the system was assumed to be symmetric. So this portion was taken out of the system just instead of the 70 channels we have, only a single channel, that is a single one below and up. That will be two channels from both the low bottom and the upper layer. So we simulated that using Hansen split. This function is the enlarged view of the domain, the computational domain. So, and as I said, we are investigating repeating sets as well. As you can see here, we have 4 different geometry of repeating sets. The blue arrow is showing us the cold coolant as it is moving in, and as it's getting across to the channel, it conveys the heat from the substrate, and the fluid becomes hotter. This is the inlet for the bottom layer, and this is the inlet for the upper layer. So we have 4 different brick geometries, which is the all front. If you can see from here, this one, the fluid is entering through here, and all the roofs are towards the entrance. That's all front. The second one is all center. We can see, but for both bottom and the upper layer, all the ribs are positioned at the center position. And the third one is we have all back. If the fluid is entering from this side and we have all the ribs around here, that means all the ribs are all back, and also have even distribution, as you can see here. So we have this governing equation governing the channel itself, we have the one governing the porous fin, and also the boundary conditions, you can say. So in order to be sure that what we are doing is actually correct, there is a need for verification and validation with regards to the existing work on this. So we took a look at work of 1 Director 2018, and we verified our setup with this, and with this we use barothermal resistance and also pumping power to validate that, and we could see that the results are very close, and that gave us assurance that we are doing well. So to discuss about the results, like I said, we actually carried on the research on ordinary WDR microchannel using the nanofluid without the rib inside. So this is the result for the first observation, that is without the ribs. So if you can see here, we have AB to E diagram, and we took this for the porosity of 0.2. Why 0.2? Because after taking everything, we concluded that okay, this 0.2 has the best result, and instead of us having a lot of results here to be discussed, we just picked out 0.2 while varying the volume fraction of the particle. For the first one here, this is the volume fraction 0, that is ordinary water. If you can see the base of the substrate, the thing is very hot, and the fluid is not actually conveying much heat. So we can see that this portion is not actually as red as the other side, and the substrate is very hot, even if you see this middle part and the top part. But moving to the porosity volume fraction 0.5, we could see that the substrate is getting more cold. That is, the fluid is dissipating, is carrying along the heat generated and the one conveyed by the substrate across the fluid. And if you move down, you see that the substrate is getting cold. If you see this one, that is at volume fraction 4%. The substrate is getting cold, and while the fluid is getting hotter. That shows us that the fluid is actually taking away the heat while the substrate is getting colder. And as the substrate is getting colder, that means the electronic device which the substrate is being mounted on will be also getting cold. And we see that the fluid with nanoparticle conveys the heat more than ordinary water. Now we have thermal and aerodynamic performances here. Whenever you are doing this, of course, you know that when you are having hello.
Can you move faster for your presentation?
Yes.
Faster.
Okay, I will try to. Okay, so here we have the pumping power. We have the pressure drop, which will be the what we use in determining pumping power. You see, as from here, when it is ordinary water, there is a very drastic reduction in the pressure drop, and that was due to the split effect of coolant on porous fins, and we have the increment across the porosity, and that was due to the flow resistance produced by large porous volume. We have the Nusselt number here, which is used to determine the heat transfer, and we have the PEC, which that's performance to compare the heat transfer and the pressure drop, which is the pumping power. So we have the effect of drift here. As you can see, the earth center is getting the optimal result, and we have this is the thermodynamics, which is the entropy generation. We have this one showing for the frictional and thermal entropy generation, and we could see that earth center also has the best results, while only even distribution is having the worst. So in conclusion, aluminum oxide-based water nanofluid enhances heat transfer and has enhanced environmental performance directly proportional to the volume fraction of nanoparticles up to 4%. And also, porous media enhance overall performance of double-layer microchannel heat sink up to porosity 0.6 and has optimal performance at porosity 0.2. Rib double-layer microchannel heat sink improve performances compared to unribbed system, and all configurations are thermodynamically advantageous, except even distribution, and most effective configuration is earth center. Thank you very much for listening.
Okay, thank you very much for your good presentation and very good research, Mr. Ridwan and the colleagues. So we have 2 minutes for discussion. 2 minutes for discussion left. So please, if you have a question or comment, the panelists or the attendees or the audience, you could texting on the Q and answer box. Okay, Mr. Ridwan, I'm interested with your nanofluid.
What is it?
So how to optimize? We have a question from Mr. Indo Pranoto. How to optimize the enhancement of porous media and nanofluid and pumping power? The
That was what I was. Okay, that was what I was trying to explain. To enhance that, they cause something. You look for the porosity. You do different research. You investigate the effect of different porosity, and you assume or you take use of the one where you have the best result. That was why I was explaining that we have best results at porosity 0.2, because the pumping power, to have your best performance, you have to compare the heat transfer to the pumping power. So the best pumping power, there is improving heat transfer across the porosity, but comparing that to the pressure drop, we see that at higher porosity we have more pressure drop, which was due to the flow resistance produced as a result of large porous volume. So that's how to optimize that. And also for pumping power, I have in some researches, pumping power above 4% up to like 10%, they have due to the required energy to push along the fluid along the channel. So they used to have issues with that. So their overall performance used to drop. So it's advisable you don't use a large amount of nanoparticle in your nanofluid, because it will require more energy to drive the coolants across the system.
Okay, yeah, Mr. Ridwan, I think your answer already clear for us.
Yeah, thank you very much.
But unfortunately, the time is already up. So we good to your good presentation. Please give applause to Mr. Ridwan and his colleagues. So
thank you very much.
The next presenter, which is the last for our session in this afternoon. But I have information from the committee that the presenter, which is missed in this session, will be presented in the last session, which is will be moderated by Mr. Arif Widyatama. So the next presenter, which is the last for this session, is Mr. Dedi Permana. Are you ready for your presentation?
Okay, let me share my presentation.
So the time is yours, 8 minutes from now.
Okay, thank you very much. Bismillahirrahmanirrahim. Good afternoon, ladies and gentlemen. My name is Dedi Permana. I'm from Badak LNG Bontang. I'm also alumni from Mechanical Engineering, Gajah Mada University. Today, allow me to present a topic on a feasibility study of gas turbine power augmentation, which I have conducted on a gas turbine installed in Badak LNG facility. So this is part of our company culture to deliver a CQ moment in every presentation, basically. So looking at this picture, our company is surrounded by natural forests. Approximately 56% of total area in Badak LNG is dedicated as green area, where many of rare species such as bekantan and orangutan live near to our facility. So the message here is compliance to environmental regulation has been one of our company main concern in operating the LNG plant. So this is the outline of my presentation. I will skip to the next one. This is an overview of our facility, just to give you a sense of location of our facility. So our plant is located in a city called Bontang in East Kalimantan region of Indonesia. Looking at this picture, this is an aerial view of our facility, which consists of LNG production facility and one LPG production facility. We also have LPG tank, LNG tanks, and 3 loading docks. And in supporting our production, we also produce our own electricity with total capacity of 180 megawatt. This include 1 unit gas turbine, which will be discussed in this presentation. So as a background to my presentation, we all know that on a gas turbine, the thermodynamic characteristic is influenced by the component efficiency, the pressure ratio, and the ambient condition. And if we're talking about the ambient conditions, there are 3 factors affecting the performance of gas turbine, which are ambient air pressures, the air temperature, and the relative humidity. So basically, if we increase the ambient air pressure, it will give increased power. And if we increase the ambient air temperature, it will give decrease in power. And an increase in ambient air relative humidity will give increase of power. So when we buy a gas turbine, the manufacturer will measure the performance of a gas turbine in a controlled environment where the ambient air is set at 14.7 psi absolute and the temperature is set at 15 degrees Celsius, while the relative humidity is at 60%. So if we're looking at this typical performance curve, when the gas turbine is installed in our facility, we have 34 degrees Celsius ambient air temperature. Therefore, the performance of the gas turbine, which was initially at 16.4 megawatt, will be reduced to 13.4 megawatt. So one of the main methods employed to increase the gas turbine efficiency is the cooling of compressor intake air by installing a technology called turbine inlet air cooling system. So this technology, basically we can control the temperature of the air entering the compressor at 15 degrees Celsius at all the time. So there are 2 TIAC technology available in the market. This is the biggest technology available. The first one is called evaporative cooling system, which is suitable for high temperatures and low humidity climates, and maximum relative humidity is just well over 90%. This is a typical condition in Middle East. And the second technology is called chiller cooling system, which is basically using a simple refrigeration technology, same as in our household air conditioning system. And considering the climate condition in Bontang City, where our plant is located, where the characteristic of ambient condition is very low differential bulb temperature and high humidity, we consider that the second technology, which is the mechanical chiller system, is technically suitable to be installed in our gas turbine. So this is the equipment design data, basically the technical information of the gas turbine from the gas turbine manufacturer, which is used as the basis of the analysis. We can see here several information such as power rating, the air temperature, including important information such as heat rate, fuel gas flow rates, and efficiency, which will be used in the analysis. So another technical basis involved in the analysis is the ambient temperature and relative humidity data, which was taken from a local meteorological authority. So the data was available starting from 2010 until 2017. Basically, this is 7 years return period of the climate, and the extreme high temperature condition was occurred in 2016, which will be used as the basis of analysis, where during these years, the maximum temperature was recorded at 34 degrees Celsius, and the relative humidity was recorded at 85%. So using those data, we can basically estimate the power gain on the gas turbine as shown in this graphic here, where this blue line here, this is the installation without TIAC system, where the ambient air temperature is at 34 degrees Celsius. The gas turbine can only deliver maximum of 13.4 megawatt, while if using TIAC chiller system represented by this orange color line here, the inlet air entering the compressor can be reduced down to 15 degrees Celsius, resulting in an increase of power from 13.4 to 16.4 megawatt, or equal to 3 megawatt gain of power. Okay, thank you.
Could you move
And the next
faster?
step is we.
Could
Okay,
you move
thank
faster?
you very much. Oh, yeah. The next step is evaluating the specific fuel consumption. So basically, this table presents the result. We can obtain reduction in fuel consumption from 1.153 to 1.090 fuel reduction, or equal to 5.8% fuel saving. So the next step is also calculating the estimated cooling load. So using this formula, we obtain 1,700 kilowatt of cooling load. And another important aspect of the evaluation is, of course, the economic parameter. Several bases is used in the analysis versus the capital investment, which estimated at 1.5 million, and the operating cost at 45,000 per year. And of course, the last important aspect is the gas price itself at 5.68 US dollar per MMBTU, which will be used in 3 operational case analysis at 13.4 and 16.4 megawatt in calculating the fuel saving. So this is the economic parameter result. We can see here, if we operate at 7 and 13.4 megawatt, the economic parameter shows us that it will not feasible. However, if we can maintain to operate at 16.4 megawatt all time, it will have better economic parameter. And the economic parameter itself, of course, depends on the gas price, which is very fluctuative nowadays. Therefore, sensitivity analysis of the gas price also calculated, and the result indicates that the gas price should be at least at 12.8 US dollar and 7.8 US dollar per MMBTU for 7 and 13.4 megawatt operating condition. So to conclude my presentations, in terms of fuel saving, installing TIAC chiller system for gas turbine in Badak LNG, if operated at 16.4 megawatt, will reduce the fuel consumption up to 5.8% or equal to 92,000 MMBTU per year. And in terms of project economic, this system is not economically justified. It's not operated at a maximum base load of 16.4 megawatt, while sensitivity analysis indicates that the LNG price should be at least 12.8 and 7.8 US dollar per MMBTU for power output of 7 and 13.4 megawatt respectively. That will be all from me. Thank you very much for your attention.
Okay, thank you very much for your presentation, Mr. Dedi Permana. I think this is a good result for your company if you use TIAC technology. Yeah. Is there any question or comment from the audience or panelists for our last presentation in this session? How about the time? Oh, the time is already, we still have 20 seconds. Okay, Mr. Dedi Permana, I think the time is up. I think you have a good presentation for today. So we give applause to Mr. Dedi and his colleague in Badak and LNG. So thank you very much, Mr. Dedi, and all
Thank you
of
very much.
presenters in this session. So I believe you have a very good discussion and also very good for the new inspiration, new data, and new result. So I think this is end of my job to be a moderator. So we would like to give applause for us, and the time will be come back to the MC, Master of Ceremony, Mr. Fahri Rifari. Thank you very much.
Thank you very much. Thank you, Mr. Bramantya, as the moderator for the previous session. And I was just informed by the committee to Mr. Dedi Permana, you have one question on the chat column. So if you want to answer it, feel free by writing down or typing down your answer in that column. But otherwise, thank you so much for all the outstanding presenters, researchers, and contributors for their presentation. And now we are going to swiftly move to the multi-phase flow and fluid dynamics paper presentation. For this particular session, please welcome our moderator, Mr. Arif Widyatama. Are you already here with us? Okay, if you're ready, Mr. Widyatama, please continue, and the time is yours. Thank you very much. Your voice is very small, Mr. Okay.
Is it better?
Okay, it's
Still lower.
still slightly small, but better than before.
Test.
Okay, much better, Mr. Arif Widyatama.
So, okay, thank you, Mr. Fahri, for who have guided us to this session. So, good afternoon for all of participants and the honorable presenter. It's a pleasure for me to meet you in the last session of the oral presentation of the Thermofluid 2020. In this session, I think we have around 8 presenters, and in general, its presentation will be conducted in 8 minutes, and it is followed by Q&A session. For the attendant, the question can be written in the Q&A session, and for the panelists, you can write it in the chat. I'll try my best to cover both of the feature. Okay, let's move to the first presentation. Now we have Mr. Chatra Wedharma. Are you ready? Is Mr. Chatra Wedharma already here?
Yes, I'm ready. So,
okay. So Mr. Chatra Wedharma will present the paper entitled Two-Phase Flow Regime Assignment based on wavelet feature of pressure signal in the airlift pump wavelet generator. Okay, Mr. Chatra Wedharma, the floor is yours.
okay, thank you very much, Mr. Arif Widyatama, for the time to me. I want to present about the flow regime segment based on wavelet feature of the pressure signal in airlift pump bubble generator. In the first, I want to share about the information from the title of my paper is from three keyword. The first is early pump bubble generator. What is that? And then
Sorry, Mr. Chatrawardama, can you make it bigger, the
Hello?
presentation?
Yes.
So can you make it full screen, the presentation?
Yes, full screen.
I think it's not really.
Sorry, Mr. Chatrawardama, I think you should swap your display.
Swap extend, swap or duplicate the display because.
Where is that?
It's on the display settings, I believe. It's on the top left corner of your screen.
Yeah, this
If you
display
could see-
setting.
Slideshow.
Yeah.
If you could see on the top left corner of your screen, there's this display settings menu, and if you press that, there'd be a drop down to swap the display.
Yeah, you click the display setting.
I'm sorry. Display setting. Where is that?
In the top left corner. Sorry.
Left corner.
Beside the show taskbar, we have show taskbar, display setting, and the end slideshow. In the middle, we have display setting. See it?
I think already slideshow in my.
Oh, in your view, it's already
Yes,
slideshow.
I think he can go ahead to shorten the time, I think.
Okay. Yeah, you can continue, Mr. Chatrawardama.
Okay. So, Mr. Arif?
Yeah, I think it's very clear now. Thank you.
Okay, and the first I want to, what is the airlift pump bubble generator? Airlift pump bubble generator is one of the development of conventional airlift pump. The principal working of the airlift pump is like this image in this slide. The first, I compress it, this flow to the injector, and then produce about several bubble. The several bubble will leave the water in the reservoir and flow out in the outlet. The basic concept of the airlift pump, conventional airlift pump, is the inject the compressed air and then leave the water to the outlet. And then the pressure signal, why we choose the pressure signal as the flow regime segment in the airlift pump bubble generator. The pressure signal has advantage in inspecting and non-intrusive, require minor modification to existing piping system, suitable for laboratory and industrial setting. And the important point is the measuring the local pressure. This is the difference of differential pressure signal. If the differential signal will measuring the global pressure in this reservoir pipe. And then wavelet feature. Wavelet feature is some advantage provide overall local information from signal, can decompose the signal in detail, and then suitable for non-stationary transient signal, nonlinear and fuse a large number of frequencies, and has a good RAM resolution at high frequency and good reference frequency resolution at low frequency. The wavelet feature is different with the fast Fourier transform. The fast Fourier transform only can process the signal in the linear signal, not a non-linear and non-stationary signal cannot do the Fourier transform. And the next slide, this is my apparatus schematic of the airlift pump bubble generator. Airlift pump bubble generator, and the first we can set the level or the height of the air overflow tank, and then flow the water in this line, and then set up the submersion ratio. The setup of the submersion ratio based on the level of the water surface in the reservoir, and then turn on the water pump. The water pump flow to the micro bubble generator. The micro bubble generator like this figure, or in this paper we call as the bubble generator, like this figure. The concept of bubble generator is produce a bubble by the pressurized water and atmospheric air flow naturally in this area. Why the naturally flow in this area? Because the pressure of this area is lower than the atmospheric pressure. So the bubble is produced, and bubble meet the water in the reservoir, can produce the interface friction of air bubble and water, and then when the buoyancy force of the air bubble higher than the wave force of the water will lift to the water will lift to the outlet or the separator, and then back flowing to the in section. This is the concept of the airlift pump bubble generator. And then where we measuring the pressure in this position is I think the fully developed region, because from the Zineng Wang result, the fully developed of the airlift pump bubble generator, airlift pump conventional is about the 40 times D of 40 times diameter of reservoir pipe. This is the experiment from the visual image. I think we get the 6 flow pattern. They are the clustered bubble, homogeneous bubble, cap bubble, bubbly stable slug, bubbly unstable slug, and slug churns. The rank of the data experiment, all the flow rate of gas is from 0 to 3 meter cubic per hours. And the first clustered bubble is as the indicated of the bubble tend to flow upward and grouping in the certain region like this. And then the pressure time series or time domain pressure of the clustered bubble is like this. The noise is dominant in this pressure signal, like the homogeneous bubble. When the flow rate of air is increased, the homogeneous bubble is produced. The homogeneous bubble is indicated by bubble are evenly distributed in the water, like this image. And then the cap bubble is the noise is decreased. The noise is decreased. The noise of the pressure signal is decreased. In the cap bubble, the start to coalescence of the bubble. The coalescence of bubble will increase the buoyancy force, and then the bubble will movement strongly. The interface friction frequency is more dominant than the noise frequency. So the noise in this cap bubble is decreased. And then in the bubbling stable slug, and the slug churn, I think noise is not dominant in the pressure signal. The slug began to form, but the considerable amount of bubble. Okay, in this flow regimes, the bubble is enveloping the body slug because the bubble is produced from the bubble generator is very high, or large amount of bubble production from the bubble generator. From the figure of signal pressure or time domain signal, the higher the air flow rate, the lower the noise frequency, and the higher the fluctuation of pressure frequency in this time series domain. This is a wavelet analysis of the pressure signal. The figure 4 is result of the composition of the original signal. This is original signal, and this is approximation signal, and the D notation is the tail signal. The wavelet signal, I use the toolbox in the MATLAB software to decompose the signal, and then I choose.
Excuse me, Mr. Chatrawardama. Yeah. The time is almost over, so you can make it faster.
Okay. Thank you, Mr. Arif. Okay, wavelet analysis, and I go to the result of wavelet analysis. This is indicator as the Wi-Fi interface, and then the Wi-Fi interface will, the fluctuation of the Wi-Fi interface is higher when the flow regime from bubble to the slug churn bubble. This is the frequency, the fluctuation of moving bubble in the reservoir, and then this is the energy of fluctuation. The energy of fluctuation as the clustering the flow regime in the airlift pump bubble generator. This is as a method from the wavelet energy is get from the variant of the tail, and approximation signal is wavelet like this. Okay, the cluster bubble and homogeneous bubble is identified by the tend to have some trend with the fixed value at approximation x. The peak value of the wavelet energy is in this approximation x, and then the cap bubble, the peak of the energy fluctuation tend to shift toward the large scale low frequency in the tail 7. This is the indication of the cap bubble is as the transition from the bubble to the slug, or cap bubble is indication as early slug formation. And then when the slug is occur in the reservoir, the peaks of the energy fluctuation at the tail of 7, and when the slug churns, the peak will move to the approximation x. Slug churn is a combine of the slug and the churns. Slug and churns flow. When the slug is flow in the reservoir, and then in the certain point the buoyancy force of the slug cannot resist the weight of the water.
Excuse me, Mr. Chatrawardama, the time is almost over. Can you?
Okay. Thank you.
Okay.
This is conclusions. Thank you, Mr. Arif. I'm sorry.
Okay, thank you very much for Mr. Chatrawardama that have enlighten us and explain us a new method to assess the flow regime in the topic of airlift pump based on wavelet analysis. So we have one question from Mr. Josephus. Dear Mr. Chatrawardama, thank you for your presentation. Could you explain again about selecting the effective frequency for detecting the bubble and diminish the noise? Thank you very much. So
okay, selecting the effective frequency for
yeah, detecting the bubbles
bubble and diminish
the noise.
Thank you. Okay, the frequency of the data, the recording data from my experimental is about the 400 hertz. The frequency, I think, from the previous result, previous result experimental about the 400 hertz, because this frequency I think can effective frequency for the minimize noise, and then when the frequency is higher than the 400 hertz, I think the noise will record in this experimental result. I think like that.
Okay, thank you. Actually, there is one more question from Mr. Akmal Irfan Majid, but unfortunately the time is over. So Mr. Chatrawardama, please, if you want to answer the question, you can use the chat feature. Okay, thank you very much, Mr. Chatrawardama, for the very good presentation and very good research. Now we...
Thank you, Mr. Arif.
So we will have Mr. Astianto that will present the paper entitled Time Series Differential Pressure Fluctuation of a Floating Regime, a Preliminary Experimental Research Investigation on a 1/30 downscale PWR hot leg geometry. Mr. Astianto, are you ready? Hello, Mr. Astianto.
Good afternoon.
Okay. Okay, Mr. Astianto, the time is yours.
Thanks a lot, Pak Arif, my favorite young lecturer. Let me first share my screen. Yep. Can everybody hear my voice and see the PPT clearly?
Yes, the voice is very clear. The PPT is also very clear. Thank you, Mr. Astianto.
Yep. Good afternoon, all the honorable presenters, participants, and also audiences. On this valuable moment, allow me to deliver our experimental research paper presentation entitled Time Series Differential Pressure Fluctuations of a Flooding Regime, a preliminary experimental research investigation on a 1/30 downset PWR hot leg geometry. I am Achilius Hermawan Astianto on behalf as the speaker of the authors. This presentation contains 4 main sections. So the introduction, some previous works, the methodology, data, and analysis. Several concluding remarks will also be delivered as the findings of this present work. So as an introduction, let us consider an accidental scenario in the primary circuit of a pressurized water reactor or PWR, namely loss of cooling accident or lockup. So as a result of a small break in the reactor primary circuit, there will be a suddenly pressure drop causing a phase change and results on a counter current flow along the hot leg a part in the primary circuit which contain horizontal elbow and an elbow and also inclined parts, namely the riser. Once the steam flow rate increase, a limit of the counter current flow might be reached. It is called counter current flow limitation, or CCFL. So the CCFL initiates a flooding regime in which the particular or total fluid flows currently with the gas along the hot leg. This phenomenon, of course, give disadvantage for the emergency cooling process. So furthermore, it is very common to assess the pressure drops characteristics during CCFL research. The fluctuation of this particular parameter may indicate inception of the flow regime transition from a counter to a co-current flow. Hence, several statistics tools such as the probability density functions and also the power spectral density give opportunity to investigate the characteristic of a time series pressure fluctuations. So the research questions may be what like the differential pressure fluctuations during flooding regime are, and based on those statistical tools, do the fluctuations deliver certain meanings. This part of section describes several previous works on counter current flow limitation in hot leg parts. So this all in the hot leg parts, hot leg geometry. It contains such working parameters investigated, and they correspond to some results obtained. And we consider several of these parameters in our in the present works also. So the experimental apparatus scheme, or the schematic, is shown in the figure on the slide. The test section, the main test section, were a complex geometry representing the convoy PWR hot leg in a 1-30 downset. The supporting components includes the RPV simulators and also the steam generator simulators. The other system contain also the water and the air supply systems, and also the measurement and also the data acquisition systems. The data tabulation were carried out as follows. So water from the bottom container was pumped into the upper container, and as a result of the gravitational force, the water later flowed along these parallel channels. And to manage the water flow rate, several water flow meters were installed and controlled by several valves. Then the water filled the SD simulator and flowed along the hot leg and go to the RPV simulators. On the other hand, meanwhile, air from a compressor in a constant pressure controlled by a pressure regulator through the flow meter, the air flow meter, and enter the RPV simulators, flowed along the hot leg countercurrently with the water, and entered the SG simulator and released to the atmosphere. On the other hand, the measurement systems used in the data tabulation consist of a differential pressure transducer to obtain the time series pressure differential voltage signals fluctuation between the SG simulators and also the RPV simulator, and to obtain other information regarding the water level in the RPV simulator, we also assess a visual observation through a measuring line, and it's validated by a static pressure transducer. Both pressure transducer were connected to a 12-volt power supply and a data logger interconnected to an analog digital converter and also signal amplifier and a personal computer. So the slide shows the result obtained. The left picture shows that the onset of flooding, or CCFL curve, can be divided into 3 regions based on the relationship between the water and the air to the CCFL. The first region shows that the air flow rate that initiates the flooding decreases with the increase of the liquid flow rate. The second region gave opposite trend. The air flow rate that initiates the flooding increases with the increase of the water flow rate. Furthermore, in the third region, the increase of water flow rate tends to fasten. This is FL again, almost similar with the first region, but it rather fluctuates. And in some comparisons, in agreement to those several previous works data, we do obtain also linear graph as proposed. We do not obtain also a linear graph that proposed by the Wally CCFL correlation. However, there is still agreement with those results regarding that certain trends. We obtain similar trends to Wong-Weiss, and also Badarudin and co-workers data in which the flooding curve were divided into 3 regions also based on the effect of the water flow rate on the CCFL. So in dimensionless liquid superficial velocity range or certain range, 0.07 to 0.2, there is an agreement with all previous data comparison. In this range, the air flow rate that initiates the flooding tends to decrease with the increase of the water flow rates. So in the next small range, 0.2 to 0.25, there is still similar trends to Wong-Weiss's data, even though it underpredicts the data. This is our data. This might
Excuse
be
me, Mr. Astainto. The time is almost over. You can make it faster, please.
So the next slide is the pressure differential fluctuations between the SG simulator and the RPV simulators. So it can be seen from the graph that for a given liquid superficial velocity with several gas superficial velocity, the PDF obtains shows that there is a fluctuation trends on the mean data. But for the standard deviation, there is a decrease trends. Furthermore, but when we continue to assess to certain other values representing its regions respectively, the graphs obtained do not show the uniform trends. The means and standard deviation comes with fluctuation trends. Meanwhile, when we observe the gas superficial velocity on the such dominant frequency, from the pictures, it can be inferred that the maximum spectrum decreases with the increase of the gas superficial velocity for a liquid superficial velocity given. But however, for several liquid superficial others velocities, the results look different. Even the trend still saw an increase in dominant frequencies with the increase of the gas superficial velocity. The maximum spectrum tend to decrease with the increase of the gas superficial velocity. So this is the other comparison that we make from we want the effect of the liquid superficial velocity. Overall, the trend is a little bit different. And furthermore, for several other gas superficial velocities, the results look a little bit different. The trend still shows a fluctuation trends for both the dominant frequencies and the maximum spectrum with the increase of liquid superficial velocity. The rest gas superficial velocity is taken from such region that we divided before. So according to the results above, the results we obtained above, we notify some concluding remarks as follows. Firstly, some agreements in the CCFL curves with the previous works data imply an advisable research methodology on the present work. Secondly, the second region on the CCFL curve gives advantage on the LOCA scenario. And the third, the pressure drop tends to increase with the increase of the liquid superficial velocity during a flooding regime. So thank you for your attention, and allow me to return the time and the platform back to the honorable moderator. Please, Pak Arif.
Okay, thank you very much, Mr. Astianto. It is a very interesting preliminary research that reveal the pressure characteristic of CCFL. I think the result is very solid, and surely it will be a good basis to conduct the further research. We have one question. Let me read it. When you do a reactor downscale, what parameters should be considered? Does the scaling parameter influence the value of parameters in large-scale reactor? Are there dimensionless number that to represent the scaling factor?
So,
I think it's
yep.
Yeah.
Okay.
Please answer it.
Yeah. Thank you, Pak Arif. Of course, some previous work obtained, some previous data work obtained becomes the specific consideration for the scaling parameters. For example, Badarudin et al. Deliver a parameter 1 to 30, and some other authors also made the same scaling. But overall, the scaling factor is also fit with some research data from those previous works data.
Okay, thank you very much for the answer, Mr. Astianto. Now we move to the third presentation. So we will have a paper entitled CFD Study of the Damage Split Effect on the Gas Turbine Meter Performance. This paper will be presented by Mr. Zulkarnain. Mr. Zulkarnain, are you ready? Mr. Zulkarnain, are you ready?
Yes, I'm ready. Thank you.
Okay, so
is my
the floor is
presentation
yours.
Show already show or?
Yeah, it's already show, but I think you should make it the full screen.
Okay, thank you. Yeah.
Okay, it's great. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Hopefully, we are all healthy, and we hope all the corona pandemic is over soon, and so that this interesting conference can be held offline, and we can talk each other about the interesting research. Okay. Okay, my name is Zulkarnain. I am from currently I am a student of University of Gadjah Mada Mechanical Engineering. Here's my research, and Dr. Din and Prof. Indarto is my supervisor, and I'm daily right now working at perusahaan gas negara, National Gas Company, which is now already merged with Pertamina, become the only subholding gas in Indonesia. So this topic is a CFD analysis of the damage effect on the gas turbine meter performance. Why I choose this topic? Because in gas industry in Indonesia mostly use gas turbine meter as a custody transfer measurement tools. Like we are buying some fruits, we have the scale to measure how much we are buying. The turbine meter is the one we are using to measure how much the gas we deliver to the customer. The working principle of gas turbine meter is based on the kinetic energy of the rotative fluids of the rotor of the fluid can be measured by the angular speed of the rotating rotor. So the case is we found in the 2018 some of our industry face a very critical problem here, and here their gas turbine meter blades fell apart. This is because of their stopping their production from Idul Fitri in 2018, and then when they're starting again in the July of 2019, 2018, the flow rate is suddenly dropped by 50%. Normally, we are thinking that this is changes of the consumption profile of the industry, but when we check to the calibration the next period, we found that the rotor blades of the turbine meter is already gone. So here the topics I currently researching is to the inaccurate measurement and gas turbine decrease performance due to damaged rotor blades. So we already know with the real case, the performance is decreasing by 50%. But in the academic on the research purpose, we should know how much the decreased performance is affected by the damage of the rotor blades. Here, the scope of problem we are conducted by CFD study, and the fluid is compressible, isothermal, and the steady state. Why steady state? Because the steady state is reflecting the industrial customer demand profile. So we are choosing the steady state one. And then the fluid studied was air and methane with the temperature of 30 degrees of Celsius. And the gas turbine meter used as test specimen is G400 with 16 rotor blades. Yeah, this is the objective. Yeah, we are to the point is we are now knowing that how the damage or rotor blades is affecting the meter turbine performance. Here is the previous study. The meter turbine is rarely to be studied by previous researchers because of the technology is quite old, but into the practical side, this is still be used to the industrial. So the latest I found, the researchers study this topic is 2015. The topic is kind of similar with the S. Hariri et al., but the fluid he used is crude oil. And here I introduce the research for the natural gas. Okay, from the theoretical basis, as I mentioned before, gas turbine meter or turbine meter are talking about the torque equilibrium formula, which is the torque here will be subscribed by the bearing friction of torque. And then when we look at the triangle velocity triangle, and this is the theoretical basis. So the point is we are now facing with the damaged blades is the A here. A is the actual main cross-sectional area of effective angular flow. When the blades is fall apart, so the A become bigger, and so theoretically the performance is decreasing. But how about we are looking this for the CFD study? Okay, this is the research methodology. So we are conducting the literative study, and then we comparing the simulation result with the calibration measurement data. Luckily, we have here in the calendar Jakarta we have some calibration laboratory for meter turbine, and then we already compare the result of a simulation to the calibration data to validate our model. So as I mentioned before, we working with air because of the calibration facility in the calendar using air, and then we compare it with the methane. So the analysis here is, are there any effect using different fluid to measure the performance between the fluid air and the methane? And secondly, are there any effect to measure performance with the variated flow regimes? When the regime flow rate become higher, as the decrease of performance is higher or not? And the last one is, are the effect make some specific pattern and can be generalized? Okay, next we are talking about the model building and mesh generation. So in this case, we are generated over 1,200,000 mesh with the turbine blades here, and here is the curve of the convergence. We can see here is the signs of convergence. And then the assumption here is use the turbulence model realizable K epsilon with scalable wall function, because this turbulent model is assume a stable boundary layer profile because it is in accordance to characteristic of the extracted fluid such as turbine matter. Realizable K epsilon is more better than the other model. Okay, so we are validating our model with the calibration result data. This is the picture of our calibration laboratory in Klender. And here the matter turbine. Turbine matter here, the counter is connected to the blades by the gear here. So to find the correlation about the rotating rotor to the counter here, we are conducting the test, converting the rotor rotation to fluid flow rate, resulting that 1 meter cubic of fluids equal to 115 rotation of turbine meter rotor. And we can see in the calibration graphic here, this is almost same, except for the 320 meter cubic per hour. This is 3.12% of error here. So this is the simulation
Excuse me,
result.
Mr. Zulkarnain, the time is almost over. Maybe you can make it faster.
Okay, yeah.
Thank you.
Okay, when we comparing air to the methane, we can see here the discrepancy is not very different, about 1.42 and 1.66. So we can conclude that regarding the fluid, it doesn't matter about the methane or the air we are using to the simulation here. So when we simulate the one broken blade of rotor in the gas turbine matter here, the discrepancy is slightly increased, but it is within the range of the meteorological rule in Indonesia, which is plus minus 2%. So we can clearly see whether if the turbine matter is already failed or already broke when the only one broken blade in the rotor. But if we further see the increase the broken blade here, there are an increasing pattern of the discrepancy. When we choose all the rotor blade is broke, there are no sign of measurement, so we can conclude and no fluid can be measured. But the closest one, we are conducted for the 15 broken blade. We are having almost 35% of the error coming from the broken blade. So there is still 15% of the discrepancy from the industrial here to be fine in the next, probably further future studies. Okay, this is a conclusion. So there is no substantial difference in terms of result of rotor rotating speed between air and methane. And then when we compare the model to the result of the calibration in the lab, we find the average difference if 0.48%. So this is very close to the real case. And then when the radius deviation is come to the middle of the range of measurement in 320 meter cubic per hour. So the almost all broken gas turbine motor is contributing 35% of decreases measurement performance in the consumer. But the other losses, as I mentioned before, probably can be affected by the other factor, such as load factor to the profile of demand. So to detect broken blades of gas turbine matter, the rapid decrease measurement of true broken blades is already considered. So when only one blade is broken, we still don't know whether the turbine matter is broken or not. Probably this is my conclusion of this research. Yeah, I'm sure the research can be further improved to the next of researcher, and I hope this is give you some more explanation about the gas matter turbine or gas industry in the general. Thank you.
Okay, thank you very much, Mr. Zulkarnain, that have comprehensively explained to us the effect of damage plate on the turbine performance. What is called bubbling movement due to the imbalance of damage plate, because when the number of plates is not balanced, so the movement of the turbine will be affected, and I think it will trigger another performance losses.
Yes, probably the next research is to be research this topic for the transient model. Probably we can find find more factors contributing to the losses of the measurement to the customer.
Oh yes, because this is in steady state. Yes.
Yes,
Okay,
it is in steady state.
So this is one more question. Have you correlated their CFD result with key operational cost of PGN? How that can impact the production process and cost?
Okay, yeah. Since our experiment here conducting in the distribution pipeline, which is in the distribution pipeline, we cannot implement some like pipeline cleaning, like pigging to the distribution pipeline. So we can do almost nothing to the distribution pipeline. So when this operational cost of PGN here, actually in the PGN now, the measurement process is doing by the electronical volume corrector. So the normal matter turbine cannot be directly be recorded because it is measured in the real temperature and pressure. When we are trading the gas, we are in our gas supply agreement. There are some conversion to the standard process. Standard condition is 1 atmosphere and 60 degree Fahrenheit. So we need to convert it to that. So the question here, have you correlated to your CFD result with key operational cost of PGN and how that can impact the production process and the cost? Okay, this is a new finding actually in this new case, and we are now further continue to study the effect of the sudden stop of the industry, because we suspect that there are some debris from the distribution pipeline. When the industrial start to take the gas, the velocity is very high, so that the debris is go with the flow, and then the debris is damaging the rotor blades. Probably when we find this kind of case in the next future, we are attempting to more great filter atau more better filter to before the matter, so it can be stopped before it reach the matter. Probably
okay,
that.
Okay, thank you very much, Mr. Zulkarnain, for the answer. Please give a big applause for Mr. Zulkarnain. So we are moving to the, I think, fourth paper. Yeah, the next paper is experimental study of swirl microbubble generator with 1.2 millimeter diameter of gas nozzle and 1 millimeter distance to the outlet. This paper will be presented by Ms. Mawarni. Are you ready? I think you still mute your mic.
Assalamualaikum, Mr. Arif. Can
Okay,
you
okay.
hear my
Yeah.
voice?
Yeah, your voice is very clear. Okay, so
Okay,
the
thank
floor
you.
is yours.
Yeah. Thank you, Mr. Arif.
Yes.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay.
Okay, great.
Yeah. Okay, maybe I am the last presenter, Mr. Arif.
No, no, we still have plenty of presenter after you.
Amin. Bismillah. Uh, okay. On this occasion, please, my name is Rajat Indah Mawarni, which will present my paper with a title Experimental Study of Swirl Microbubble Generator with diameter of gas nozzle 1.2 and distance to the outlet of 1 millimeter. Here is a simple overview of the presentation that I will give, which will begin with delivery of background and will end with the delivery of conclusion and suggestion. As a background, water is an important parameter for human survival because the current pure water quality will have an impact on human health itself. This is further compounded by an increase in population and industry, which has an impact on increasing waste production, where pure water quality is one of the causes of diarrhea. We can know 15 until 22 children in Indonesia die from diarrhea every hour. So to overcome this, it is very necessary that effective and efficient waste treatment technology. So one of the most popular waste treatment technology today is MBG or microbubble generator. Because microbubble generator have a simple design and then inexpensive and effective than other waste treatment technology. In my research purpose, I am analyzing microbubble form from MBK swirl type, consists of microbubble diameter distribution produced, and then hydraulic power absorbed by microbubble generator, and then pressure drop that occur on the microbubble generator. As the literature review, previous researchers, among others, like Recovery et al. At 1985, and then Yun et al. At 1991, Ohnari, and then Sadatomi, has been developed microbubble generator technology. This is my research methods, the schematic diagram of the experimental apparatus. The schematic diagram of the experimental setup is shown in this slide. The test section was a rectangular transparent glass box. The long is 2.x meter, and then the width is 0.6 meter, and then the height is 0.6 meter. The glass box was filled with tap water of 40 centimeter deep. And then MBG was aligned horizontally and placed 20 centimeter from the bottom of the test tank. In the present study, the range of the air and water flow rate were set at 0.1 until 1.0 LPM and 30 until 50 LPM respectively. And then the water flow rate was controlled by variable speed drive installed on the water pump while the airflow was installed to obtain. And then airflow rate, flow meter installed to obtain the desired airflow rate. To see the performa of MBK, to see the performa of MBK is pressure drop and hydraulic power. We are using pressure transducer to recording. Pressure transducer is connected with the data logger is used to acquire pressure data that occur. The pressure data occur on the microbubble generator is read by the computer, and then the measurement of hydraulic power in inlet side of the microbubble generator is connected using a hose filled with water with a pressure transducer to get pressure on the inlet side. And then the inlet pressure obtained become the calculation data in the hydraulic power equation. So for the pressure drop measurement, in the inlet and outlet side of the microbubble generator are connected using a hose filled with water with a pressure transducer to get the pressure drop that appear between the inlet and outlet side. Next, the bubble shooting scheme to get the diameter bubble distribution data that is formed. And then bubble shooting is done using a high-speed camera. High-speed camera Phantom Miro M310 was used to record microbubble generator. To record the microbubble phenomena. The maximum resolution of the camera was 1,200.800. All measurements were conducted at the frame speed of 3,000 frames per second. The spatial resolution and frame rate used in the present work allowed the microbubbles behavior to be absorbed in detail.
Ms.
And
Marwani,
then
maybe you can make it faster because the time is almost over.
Okay, thank you, Mr. Arif. And then we processing the recording with image processing using software MATLAB, and then we get a graphic between probability density function to bubble diameter using software Excel. Result and discuss. We can know that to grab that the change in the airflow is enough to affect the probability of the formation of the bubble, where the greater the value of the air discharge, the small of probability value and the greater the diameter of the bubble formed. This decrease in probability value occur due to the increase in the collision rate that's occurred in the bubble, that the collision rate will increase with the increasing ratio between air discharge and water discharge. And then for the hydraulic power, uh, hydraulic power is cube proportional to fluid debit. And pressure drop too. Pressure drop is square proportional to the fluid debit. As debit of water increase, pressure drop and hydraulic power is significantly increasing, vice versa. Meanwhile, when debit of air increase, there is an insignificant increase of pressure drop and hydraulic power and vice versa. Conclusion, first, the increase in water flow rate and decrease in air flow result in an increase in the high probability value ranging from 90 until 150 micrometer. And then the increase in water flow rate and air flow rate result in an increase in hydraulic power, but the effect of gas flow rate is insignificant when compared to the effect of water flow rate. The increase in water flow rate and air flow rate result in an increase in pressure drop, but the effect of air flow rate is insignificant when compared to the effect of water flow rate. The increase in water flow rate causes the bubble diameter to form smaller, while an increase in a flow rate causes a large bubble diameter to form. I think that's all, Mr. Arif. Thank you.
Okay, thank you very much, Ms. Mawarni, that have present a very good research about microbubble generator. So does anyone have questions? I think I have one question. What is the frame rate that used in this research? I mean the frame rate of the high-speed camera. And is it possible to use the smaller frame rate? Is there an effect if we use the smaller frame rate?
I'm sorry. Maybe you can.
Okay. What is the frame rate of the camera that used to record the data?
Oh, when I record the video, it's using 3,000 frame rate per second. 3,000
FPS.
frame rate per second. Yes.
Oh yeah. Okay. Thank you. So it's quite fast. Okay, thank you very much, Mr. Mawarni, for the presentation. Actually, there's one additional question, but I think you can answer it in chat feature. So now we will go to the next presenter, I think the fifth paper. So we will have Mr. Rahmat Waluyo. Are you ready? Mr. Rahmat Waluyo?
Yeah.
Okay, Mr. Rahmat Waluyo will present a paper entitled Performance Comparison of Centrifugal Pump in Variation of Impeller Blade Number through Numerical Simulation. Please, Mr. Rahmat Waluyo, the floor is yours.
Okay, thank you, Mr. Arif. Could you hear my voice?
Yes, it's very clear.
Let me share my slide. Share screen. Okay. Could you see my slide?
Yeah, I can see. You just need to make it a full screen.
Okay. I'm sorry, my computer is a bit slow.
It's okay. Quit.
Wait.
Okay, I think it's good, Mr. Ahmad.
Is it good?
Okay, yeah.
Okay.
You can see it clearly.
Good afternoon, everyone. My name is Rahmat Waluyo, and in this occasion, I would like to present you our study with title Performance Comparison of Centrifugal Pump in Variation of Impeller Plate Number through Numerical Simulation. This presentation will be divided into 4 parts. The first is introduction, methodology, results and discussion, and conclusion. We will start with the introduction. As we know, centrifugal pumps have been used in various applications, ranging from petrochemical, oil and gas, and agriculture. The pump performance, the study of pump performance is usually described by its head and efficiency curve, which we aim to describe the relation between head and efficiency at various flow rate. One of the motivations that allow us to research this study stems from the common difficulty encountered when assessing pump performance. Well, despite its wide use, the pump performance is rather hard to predict due to the complex nature of flow within the pump. Hence, the performance is usually referred to manufacturer data or direct measurement during pump operation. However, the advance of computational fluid dynamics or CFD open up possibility to predict pump performance before manufacture stage, which is the objective of this paper. It is a fact that geometry of pump component influence pump performance. Several studies have been carried out through experiment and simulation to investigate the topic. One of them tried to elaborate the effect of multi-fluid casing on radial thrust and efficiency, while the other tried to explain the effect of plate outlet angle on pump performance. One previous study elaborate the effects of impeller plate number on pump performance in small experimental pump. Its present study, however, is aimed to investigate numerically the performance of industrial centrifugal pump with variation of plate number. The methodology in this paper could be outlined by the following diagram. We start with specifying the pump dimension and operating condition, and after that we make the 3D modeling of pump fluid domain. After that we generate mesh and set up simulation, which respectively check to ensure the mesh quality and convergence. After that we conduct grid independency test and validation to eliminate the spatial discretization error and eliminate uncertainty between the real and simulated flow. After the simulation validated, we introduce a variation of plate number into 3 plate number 5, 7, and 9, 3 cases, and simulated in various flow rates. The result will be discussed and concluded. Okay, the study of centrifugal pump is partitioned into 3 cell zones of fluid domain. The first is suction zone, impeller zone, and fluid zone. The both suction and fluid zone employs stationary wall boundary condition, while the impeller zone is using moving wall because it is rotating. Other boundary conditions such as inlet and outlet are shown in the figure. And the suction and discharge side are connected to pipe network by circular flange, which is common in industrial application. The table on the right also lists some dimension of the pump components such as plate and flame. Entering the results and discussion. Here it is the detail of numerical simulation setup. The software used in this research is ANSYS Fluent. The fluid is water, and the mesh consists of a mixture of structured and unstructured mesh. The inlet boundary condition is specified by entering the mesh flow rate, while the outlet boundary condition specified by entering the exit pressure value. The turbulence model that used in this paper is K epsilon RNG, and the cell domain consists of 3 domain, which is previously explained. The reference frame, using multi-reference frame to accommodate the difference between the velocity in rotating and stationary zone. The solver used in this paper use simple algorithm. Here the scale residual of numerical simulation for up to 1,000 iteration, and we can see that the residual are decreasing monotonously. So we can say that the simulated result is convergent. Further, we see that the parameters that being used to assess the mesh quality are orthogonal quality and skewness. In general, we can say that the higher orthogonal quality, the better the mesh, and the lower the skewness is the better the mesh also. The value of parameter for 3 cases are given in the table below. We can see that the skewness for all cases is below 0.25 and the orthogonal quality is above 0.75, which is fall within acceptable range of mesh quality. Then we conduct the grid independency test. The diagram below show result for grid independency test, which conducted to minimize error due to spatial discretization. Hence, the acquired solution would be independent of number of cells used in simulation. The test was carried out in 2 grid refinement steps. Considering the closeness of the simulation result between second and third grid and available computation resource, it is decided that to use intermediate number of cells for further simulation, the middle one. And then the validation is conducted to eliminate the uncertainty that we might make difference between the real and simulated flow by comparing simulation results with experimental data. The following charts show the comparison, and we could see that the experimental and simulated result differ only less than 10%, thus considered within acceptable range of validity. The results of numerical simulation also could be presented in visual form, such as pressure contour and velocity field. The figure below shows the simulation result in pressure contour form. We can see the fewer plate number produce non-uniform pressure along the impeller periphery, as highlighted by the blue circle in the figure below. You can see that the impeller periphery is more red rather than the other one, than the other two for the fewer number for the 5 plate case.
Mr. Waluyo, please make it faster because the time is almost over. Thank you.
Okay, thank you. Further observation on velocity field will reveal flow mechanism inside centrifugal pump. Lack of flow agents in lower plate number case will produce circulation flow, which in turn will form vortices along plate passage. The following figure will show the occurrence of such vortices, which are highlighted by the red circle. You can see that there are 2 vortices in 5 plate case, and 1 vortice in 7 plate case, and virtually no vortice in 9 plate case. The pump performance are generally presented as pump characteristic curve. You can see that here is head versus key curve. It is shown that H versus key curve with 9 plate produce higher head than the other two up until certain flow rate. On the other hand, pump with 5 plate produce lower head at all simulated flow rate. The inspection on efficiency versus key curve revealed that there is tendency of efficiency drop for pump with 9 plates at high flow rate. This result could be explained by considering the friction losses along impeller plate passage. Losses to friction is proportional to quadratic value of velocity, which in 9 plate case increase both because high flow rate and lower cross flow area. The case of 5 plate also don't perform better, especially at design flow rate and higher. It is due to the lack of flow guidance, which help vortice formation and dissipate the energy through the rotational motion of vortice. And in conclusion, the observation gathered from simulation results indicate that there is an optimum number of plates for centrifugal pump, which could provide adequate flow guidance, while at the same time minimizing the friction losses. In this study, the intermediate number of plates with 7 plates performed with highest efficiency at design point. Therefore, it's concluded that pump with 7 plates perform better, followed by 9 and 5 plate case. This ranks based on the pump efficiency at design point. Okay, I think it's all. Thank you for your attention. Now the Q&A session. Mr. Arif.
Okay, thank you very much, Mr. Ahmad Waluya, for a very good and clear presentation that have give us understanding on how the number of blade affecting the pump performance. So does anybody have any questions?
Let me see the Q&A answer.
Let me check it. I think there is still no question. Maybe one question from me, Mr. Ahmad Waluya. I saw the message of the model is not homogeneous. Can you explain to us how to determine which part is critical? So we need to make it more dense. Can you explain us how to determine the critical area of the model?
Okay. It's basically that it is stated before that the mesh used in this study use both structured and unstructured, which is tetrahedral. And in tetrahedral mesh, we can see that the density of the cell will be increased in complex geometry. But in this study, the density and the value of density, number of cells is automatically decided by the software when we input the mesh value.
Okay, thank you very much, Mr. Rahmat Walia, for the answer. So move to the sixth presenter. We have Mr. Ridwan P. Putra. Are you ready? Mr.
Yes, I'm ready.
Putra. Okay, Mr. Ridwan Putra will present a paper entitled Characteristic of Fluid Flow in Fixed Bed Reactor Models Composed of Spherical and Porous Tubular Milli-sized Particles. So, Mr. Putra, the floor is yours.
Okay. Thank you very much, Mr. Arif, for the time, and good afternoon, everyone. Today, I would like to. I am Ridwan Rana Putra from the Chemical Engineering Department of Institute Technology Bandung, and today I would like to present about our project regarding the characteristics of fluid flow in fixed bed reactor models composed of spherical and porous tubular milli-sized particles. So mainly in this project, we will discuss about the potential of artificial composts that can be applied in next generation agricultural technology. So let me start it. So as we know that plants are considered as one of the most important natural resources that can be processed into foods, clothing, and also shelters. As food crops, plants offer us with several key nutrients such as minerals and vitamins that are essential for our body, and high content of cellulose and hemicellulose in number of plants also triggers the utilization of plants as raw materials of plant-based textiles and also fabrics. And some plants, including the sandalwood and also cedar, have been widely used to construct housings due to their strong wood texture. Recently, land clearing, which includes forest burning, and also illegal logging, have been extensively reported. And this phenomena emerge as results of both natural disasters and also human activities. And the decline in the area of cultivation leads to the reduction in the crop yields that can cause higher food prices and a sharp rise in the global hunger. Thus, these issues motivate researchers to develop an innovative method that can boost plant productivity in the limited arable lands. And in search of techniques to improve the plant production, soil amendment by employing compost demonstrates improved macronutrient retention and plant growth in degraded tropical soils. And the study shows that compost appears to be a pertinent alternative which can simultaneously improve the soil quality and also decrease the nutrient leaching. And recently, our groups also showed that the addition of compost to the soil could mend the structure of the soil, as well as improve the water motion from the soil to the plants. However, despite of its promising potential as a way to improve the plant productivity, poor mechanical properties of compost hinders its application as a long-lasting fertilizer. So in 2005, Sita et al. Proposed a new method to escalate plant productivity by utilizing polymer materials to retain calcium and magnesium ions in the soil. And Farnes et al. Also found that the addition of polyacrylate polymers to the soil compost mixture can promote growth of native vegetation, which inhabit the mining areas. And from the studies, we found that the unique features of polymer materials from the development of synthetic macromolecules, which can act as artificial compost. So in this study, we propose to use a porous polymer membrane pipe, or we call it the PPMP, as the model of the artificial compost. It has 5 millimeter diameter and 7 millimeter length with 7 1 millimeter size channels. And for the normal compost, it was modeled using glass resin rings, or we call it the GRR, with 7 to 7 size, and it has 5 millimeter size channels. And for the soil particles, we use the glass beads with a diameter of 10 millimeter. And for the modular fluid that flows through the bed particles, we use potable water. And we arrange several beds composed of different ratios of spherical and tubular particles. And for the tubular particles, we use the PPMP and the GRR. As for the spherical particles, they are the glass beads. And for the ratio of the particles are shown on the slide. It can be seen, it ranges from 0 to 1. And after we arrange the bed, we investigated the bed hydrodynamics parameters, including the bed porosity, water holding capacity, and also the permeability. And the bed permeability measurements were measured using a falling head method. So it mainly composed of 2 columns, namely column A and column B, which are connected by a T-valve. And in the column A, we put the bed particles until it reaches a height of like 10 centimeter. And after that, we add the water, and we measured the relationship between the height and the time required for the water to flow down the bed. And using the relationships between the minus L and H per H0 versus the T, we can calculate the permeability of the bed, the B, using the derived Darcy's equation as shown on the slide. And on this slide, the porosity of the bed composed of the GR and the PPMP particles are shown. It can be seen that the addition of the tubular particles tend to increase the porosity of the bed. And the porosity increase is expected due to the enlarged interparticle spaces after the addition of the tubular particles as shown on this scheme. And another probability is that the tubular particles also contribute to the extra additional spaces, which due to the presence of the milli-sized channels inside the tubular particles. And on this slide, the water holding capacities of the beds composed of the GRR and also the PPMP beds are shown. It can be seen that the addition of the tubular particles into the bed tends to increase also the water holding capacity. However, from the PPMP particles, it can be seen that the increase is like 5-fold higher than the GR particles. The reason is because it's likely due to the smaller channels of the PPMP particles, which is around 1 millimeter size compared to the 5 millimeter size in the GR particle. And also, there are higher number of channels in a single PPMP particle. So it contributes to the higher water holding capacity. And on this slide, the permeability of the GRR beds are shown. It can be seen that the addition of the tubular particles in the bed tends to decrease the permeability of the bed. And it's likely that the decrease is due to the existence of the extra milli-sized channels. Thus, water will require longer to flow through the additional milli-sized channels in the bed with higher GR particles. And on this slide, the permeability of the PPMP beds are shown. And it can be seen that the trend of the permeability is almost the same with the one with GRR bed. And however, the beds with PPMP particles tend to show higher permeability values. This is due to after after the water penetrates into the PPME particle, the water tends to clog, partially clog the milli-size channels, and thus, and after that, the water will decide to go through the interparticle spaces instead of through the tubular particles. So in summary, we have investigated the effects on the addition of artificial compost into the soil towards the hydrodynamics of the mixtures. And also we have obtained that the bed composed of artificial compost as the tubular particles exhibits comparable porosity to the corresponding GRR beds. And the bed reactor models consist of artificial compost show excellent water holding capacities and slightly higher permeability, which suggests enhanced liquid mass transfer. So at last, we would like to thank the Directorate General of Higher Education through Student Creative Program for the financial support. And would like also thank Professor Ike Dewanten from ITB for the provision of polymer membranes. And at last, I'd like to thank all of you for the attention. Thank you.
Okay, thank you very much, Mr. Putra, an outstanding presentation that stressed out the potential of artificial compost to improve our productivity in agricultural or maybe forestry sector. Okay, does anybody have questions? Wait, let me check in the. Okay, maybe I have one question, Mr. Putra. Is this artificial compost has been widely used in the agricultural sector? Or is it still research space?
This one is still a research base. So this one is still big. The size is quite big. In the future, we would like to obtain the micro-size pipes, which are really hard to obtain. I mean, to design. But we are designing. But actually, we can use the hollow fiber membranes as one of the source. We gently cut the hollow fiber membranes, and we can also try that to investigate the effects of to use that as the artificial compost, I guess.
Of course. Yeah. Okay. Yes. Okay. Thank you very much, Mr. Putra, for the answer. And once again, it's very good presentation. Let's give some applause. Okay. Now we go to the next presenter. We'll have Mr. Pilian. Are you ready? Mr. Pilian. Wait, I think the person is already here, but excuse me, Mr. Brilliant. Okay, hello. Okay, I think he has answered me from the chat. Okay, are you ready for the presentation? Okay, I'm ready. Okay, so Mr. Brilliant will present a paper entitled "The Effect of Measurement Result Flue Gas Emission with and Without Using Flow Straightener on Stack." Okay, Mr. Brilliant, the time is yours. Oh, wait. I think the committee should change the role of Brilliant Saputra still in the attendant, I think. No, it's different account. Brilliant Saputra. In attendant, I found Brilliant Saputra. Okay. Thank you. Okay, Brilliant Saputra.
My voice clear?
Okay. It's very clear. So the floor is yours, Mr. Brilliant Saputra.
All right. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. My name is Brilliant Saputra. I'm from Mechanical Engineering Department of Sriwijaya University. On this special opportunity, I would like to present you about Hello? The effect of measurement result flue gas emission with and without using flow straightener on stack. All right, let's get started.
Sorry, Mr. Brilliant Saputra, I found a little feedback from your sound.
Test. Test.
The other feels same problem.
Wait.
Okay, yeah, I still find the echo.
Okay, let me continue. As we know, fossil fuels play a dominant role in global energy system. There are three types of fossil fuels, such as coal, oil, and gas. But coal is quite abundant compared to the other fossil fuels, especially in Indonesia. The use of coal is growing rapidly since the power plant sector is dominated by steam power plant. When fossil fuels are burned, they release carbon dioxide and also other greenhouse gases. These gases are really harmful to environment and cause air pollution and also global warming. So it is really important to monitor the flue gas and particulates emission on industry stack. Next, in order to overcome air pollution problem, Indonesian government established the regulation of standard quality of flue gas emission that comes from stationary sources through Keputusan Menteri Lingkungan Hidup number 13 of 1995, so that the number of gas emission will not run over its threshold limit value. And then, flue gas and particulates are measured isokinetically based on US EPA method 1 until 5 or in SNE number 7117.13 until 17 of 2009. But the common problem when measuring is the occurrence of cyclonic and less uniform flue gas flow. The cyclonic flow makes the measurement results less precise. So how to reduce the cyclonic flow? The solution is by installing a flow conditioner or a flow straightener inside the stack. So the flue gas flow could be more uniform until it reaches sampling point. And for the objective for this research is to analyze the difference of flue gas measurement results between the stack without using flow straightener and the stack using flow straightener. Next, for research method, here is a schematic picture of the experiment stack. The stack has 6 inches of diameter and also 36 inches of height. The flow straightener also has 2 sampling points here. Now, look at here. The flow straightener is installed at 3 different positions. First at 0.75D, and then 1D, and then 1.25D. Here, D is for the stack's diameter. So 0.75D is equal to 4.5 inch from the bottom interference. And then here we have an upward 45-degree conical flow straightener based on the previous research. So there are 4 measurement conditions in total, including the stack without using flow straightener. Next, for sampling and traverse point. Sampling point is a location for measuring or sampling. These sampling points are located at 24 inch from the bottom interference and then 12 inch from the top interference. And then for traverse point is a minimum number for cross point sampling. Next, flue gas concentration is measured by using flue gas analyzer. Since we use coal as fuel, we only measure these 5 gases such as sulfur dioxide, nitrogen dioxide, carbon monoxide, carbon dioxide, and oxygen. Each gas is measured 10 times in 10 minutes of interval time. After having concentration, next we do calculation. We calculate the average standard deviation and relative standard deviation. Relative standard deviation, or RSD, is a parameter used to express the accuracy and the precision in the measurement. The lower RSD, the more precise the measurement results. And on the other side, for particulate sampling, we use a measuring instrument called Method 5 sampling train. This train has probe and filter to collect the dust or particles. And then the particulate concentration could be determined gravimetrically. After having concentration, next we calculate the isokinetic percent. So here is the isokinetic percent formula. Next, for result and discussion, here are the RSD charts of each gas for all measurement conditions. Now, compare the RSD value between the stack without using flow straightener and the stack using flow straightener for each gas. Sulfur dioxide, nitrogen dioxide, carbon monoxide, carbon dioxide, and oxygen. Overall, the RSD from the stack without using flow straightener has higher relative standard deviation rather than the stack using flow straightener. Next, we could find which position of flow straightener installation that has the lowest RSD number by calculating the average of RSD itself. Look at this table. So the lowest RSD number is at flow straightener 1D with 2.7%. So this is the best position for installation. And then we have particulate concentration chart here. The stack without using flow straightener has the highest particulate concentration, and the concentration decreases with the increasing of installation distance. This happens because, you know, if gas streamline is suddenly turns or the disturbance modify the gas streamline, the particles may not be able to follow the same direction as gas streamline. So flow straightener obstruct the particles. Next, for isokinetic percent, based on SNE number 7117.17 of 2009, the acceptable range for isokinetic percent is 100% plus minus 10% of tolerance. So these numbers from the stack using flow straightener exceed the isokinetic percent. It happens because the linear velocity is getting smaller. Now I show you the linear velocity chart. So the linear velocity chart, the further flow straightener installation, the smaller linear velocity, because flow straightener slow down the velocity, and there is also a pressure drop. And for the conclusion, the use of flow straightener inside the stack can reduce the relative standard deviation rather than the stack without using flow straightener. And the second, the effective flow straightener installation position is at the distance of 1D from the bottom interference of the stack. And last, the use of flow straightener can produce higher isokinetic percent. The farther the flow straightener installation from the bottom interference of the stack, the higher isokinetic percent. Okay, I think that's all. I'll give it back to the moderator.
Okay, thank you, Mr. Brilian Saputra, for the presentation. It's very good presentation explaining how to improve the flow measurement in terms of flue gas emission. Okay, does anybody have questions? Let me check in the Q&A. Is there any? There is one question from Dimas Adinugroho. Can your flow straightener reduce the emission level? Could you please tell me why did you choose this position of installation? And then are there any reference? And then why didn't you put the flow straightener more than 1.25D, for example, at 3D? I think it's about the position. Please, Mr. Brilian.
Okay, thank you for the question, Mr. Dimas. That's a good question, actually. All right, a flow conditioner or flow straightener is used to reduce or eliminate the cyclonic flow and then to keep the velocity distribution as uniform as possible. Because the cyclonic flow occurs when flue gases passes through the disturbance, for example, like elbow, suctions, discharge. Here we use elbow as our disturbance or our interference. So in this area, there is a huge cyclonic and turbulence level. we have to lower that turbulence level in order to reach the good measurement results. So the answer is no. No, it cannot. The flow straightener has no deal with emission level reduction. So by keeping the flue gas flow uniform until it reaches sampling point, it is only dealing with the precision level. And then for the next question, why do we choose these three positions? All right, actually, this is the first study in using three different positions for knowing whether there are any effects for flue gas flow or not. Let me go back to the previous research. So the first research was conducted by Scarabino. He did a computational fluid dynamic analysis and focusing on flow configuration and flow inclination. In his research, there are three conditions. First, the stack with free inlet, and then the stack partially blocked, and then the stack with free inlet but using flow straightener. And the flow straightener is installed at the distance of 1.15 D. And then here is the model of his flow straightener. And for the results, the stack using flow straightener has the lowest inclination degree level. And the next research by Dewi Puspitasari and Ramadoni, they investigate the effect of flow straightener inclination on the distribution of flue gas flow. And then by using the same flow straightener model as Scarabino, they modify the angle, started from 0, 15, 30, and 45 degree. And then the flow straightener is installed at 1D from the bottom interference. And then the best model from the research is the 45 degree flow straightener. I'm sorry, I forgot to put the point of view from the research. And then the next research by Dewi Puspitasari and Reski Sihombing, they investigate the 45 degree flow straightener effect of positions on flow uniformity in sampling point. Basically, I'm gonna say that those previous research are only dealing with flow configuration, velocity distribution, and inclination level, but not immediately discuss about the measurement result, flue gas measurement results. So that's why this is the best opportunity to try the experiment research. So yeah, those three different positions came from the previous research by Dewi Puspitasari and Reski Sihombing. And then there are two reasons why we chose these three positions. First, if we put the flow straightener at 0D, it means that the flow straightener is completely close to the bottom disturbance or interference. Then the gas has no space to condition its flow uniformly by itself because there is a fluid character called fully developed flow. And then on the other side, if we put the flow straightener is really close to the sampling point, let's say we put it at 3D, there is a pressure drop. It will affect the velocity because there is a major loss when the flue gas flow friction the stack wall. The velocity could be really small. We don't want that high pressure drop. So yeah, the ideal position of installation are not really close to the bottom interference and not really close to the sampling point. And then it would be great if there are new studies or research about this topic. I mean, the research using another different positions. All right, I think that's all. If you're still curious about this previous research, I'll share it later after this presentation. Thank you.
Okay, thank you very much for Mr. Pilihan Saputra. So now we are moving to the next presentation. We will have Mr. Rinasa Agistya Anugrah. Mr. Anugrah, are you ready?
Yes, I'm ready.
Okay. So Mr. Anugrah will present a paper entitled "The Effect of Camshaft Modification on Engine Performance in Automatic Transmission Motorcycle." So, Mr. Anugrah, the floor is yours.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Now, I'm going to explain my research with the title "The Effects of Camshaft Modification on Engine Performance in Automatic Transmission Motorcycle." I am Rinasa Agustianugrah and my partner Akmal Irfan Majid. I am from Department Mechanical Technology, Universitas Muhammadiyah Yogyakarta, and Akmal Irfan Majid from Universitas Gadjah Mada. First, we are going to introduction. The one of the most well-known and interest products of motorcycle is automatic transmission scooters. And these automatic transmission scooters can be modification to get performance improvements. And camshaft modification is often done to improve the engine performance. And so the study was aimed to compare the engine performance after the using of modified camshaft and standard camshaft in automatic transmission motorcycle. And the result of the present work are expected to be an insight in mechanical design of automotive component in the future. Next, we are going to methodology. This is the table of engine specification of the automatic motorcycle. You can read in this table, and the diagram is valve diagram. In this valve diagram, we can know when the timing of valve it can open and close in the timing of the mechanism of valve, and the camshaft affect the timing of valve to open and close. And we can modification of the lobe separation angle, or LHA. LHA is the angle between the intake lobe and the exhaust lobe. Through lobe separation angle, LHA modification will affect volumetric efficiency, and the volumetric efficiency affect the performance of the engines. Because a lot and least mixture of fuel and air entering into the combustion chamber. This is the equation to get and calculation the result of LSA. Next, we go to the table comparison of measurement result and the total measurement result. This as you can see these two tables. In brief, we get the modified camshaft is smaller than standard camshaft. So it make the timing of the inlet valve and the this exhaust valve make a change with the small subtracting of the standard camshaft to modify the camshaft. And the result, we can get the torque and power
with the testing with the dyno test. And if we see in the torque comparing in the standard camshaft and with the modification camshaft, we only 2 point in modification camshaft is under the standard, the torque of the standard camshaft, while the in the graphic or in the power of the result of the power, we can only get 1 2 3 4 point the 4 point the with the modification result, the power is smaller than the standard camshaft power, and more data is above the modification camshaft. And conclusion, we use of modified power and torque camshaft is obtained higher compared to standard camshaft with the use of camshaft with highest torque is 13.54 Newton meter at 3,737 RPM, and the highest power modification is 9.3 horsepower at in the 5,000 RPM. With the standard camshaft, the highest of torque we get 13.28, and for the torque is increased by 0.29 Newton meter, and we can get the percentage of the torque is 1.95%, while in the increasing power with the camshaft modification, we get 0.2 HP, and the percentage is 2.2%. Modifying the camshaft should be done with grinding from the part that has the highest lobe or from the base circle, then followed by grinding the ram, then grinding the flank to determine the lift overlap and forming a profile. Grinding is done carefully because excessive grinding result in inappropriate duration. Thank you for your attention. That's all.
Okay, thank you, Mr. Anugrah. It is a very comprehensive presentation which gives us an insight how the camshaft modification in terms of LSA can directly influence the motorcycle performance. Does anybody have questions? Let me check. Is there any Q&A? No. So in the chat, no. Okay, Mr. Anugrah, maybe I have one question. Why do you choose this configuration of modification? Is it based on the previous research, or do you have other consideration?
Yes, this is I'm going to research this research before I read my literature study, and I get several paper that make the LSA to be small than the standard. But the paper before Not to use the sample in automatic motorcycle, but the sample is manual transmission motorcycle, and I interest to use this method in the automatic transmission motorcycle.
Okay, thank you very much. So you have conduct a literature review on the manual transmission motorcycle, and then you implement it on the automatic motorcycle. Okay, it's very clear. So I think we have arrived in the end of our paper presentation session. We had a very interesting session consists of 8 papers that I hope it can broaden our knowledge in topic of thermofluids, and hopefully it also can open the opportunity to have maybe strong collaboration among us. Thank you for joining this session. See you in the next occasion. And please, Mr. Fahri, as MC, the time is yours.
Right. Thank you so much to Mr. Arif Widyatama as the moderator for the final paper presentation. And so with that final session, the second and final day of the 11th International Conference on Thermofluids is about to come to an end. And now we will announce the best papers among the papers that have been submitted to this conference. So I would like to ask the media team to please put on the slideshow. All right, so hopefully you can all see the slideshow right now on your screens, and to the next slide, please. Right, so the first topic for the best paper is on the topic of renewable energy and energy harvesting. So we will announce the best paper immediately. On to the next slide, please. So congratulations to Mr. Royhan and his team for the paper titled Installing and Testing the Grasshopper Portable Incubator Powered Using the Solar Box P-Care for remote areas without electricity. Once again, congratulations. And on to the next topic, please. So on the next topic, we will have the heat transfer and energy conversion topic. And the best paper for this topic is next. So congratulations to Mr. Muritala and his team for their paper entitled Thermal and Thermodynamic Optimization of a Porous Double-Layered Microchannel Heat Sink. Congratulations, it was such a wonderful paper and you really deserve it, Mr. Muritala and the team. So on to the next topic, please. So on the next topic, we will cover the fluid dynamics and find out who the best paper award goes to. So for this particular topic, the best paper award will be awarded to So congratulations to Mr. Ko and his team for the paper titled Far-Field Flow Simulation of Contra-Rotating Darius Vertical Axis Wind Turbine. It was a very interesting paper and a very interesting presentation as well. So congratulations once again for winning the best paper award. And on to the next and final topic, please. So the final best paper award going to the multi-phase flow topic will be given to So congratulations to Mr. Chatrawadarma for his paper entitled Two Phases Flow Regime Assignment Based on Wavelet Features of Pressure Signal in the Airlift Pump Bubble Generator. So congratulations for all the researchers and the presenters on winning the Best Paper Award. You will get a plaque and a certificate from the organizers, and the organizers will contact you for further information and further confirmations. So finally, we are about to conclude this conference. So to close and conclude this year's International Conference on Thermofluids, we would like to invite Mr. Kasani, the Executive Chairman of the 11th International Conference on Thermofluids, and also representing the Department of Mechanical and Industrial Engineering of Universitas Gadjah Mada, to deliver a closing speech. So to Mr. Kasani, are you already here?
Okay, thank you.
Right, so whenever you're ready, sir, the time is yours. Thank you very much.
Okay. Well, good afternoon, ladies and gentlemen. Finally, we come to the end of the conference. On behalf of the committee and the Department of Mechanical and Industrial Engineering, Universitas Gadjah Mada, again, we would like to thank all keynote speakers, presenters, and attendees for their patience, participation, and contribution to this event. Congratulations to all the winners of the best papers. Please keep doing the research in the future. We believe that this event is still far from the ideal, so we apologize for any inconveniences during these events. We will do our best in the future. Finally, stay healthy and happy to all of you, and officially we close the Thermofluid 11th 2020. See you again in the next year Thermofluid 2021 conference. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Thank you.
Thank you so much to Mr. Kasani. And at last, this year's International Conference on Thermofluids has come to an end. We hope this conference brought you plenty of knowledge and insights on various topics regarding thermofluids engineering. I, Fahri Gifari, as the host or master of ceremony for this conference, on behalf of the committee, would like to sincerely apologize for any mistakes or errors that we have committed throughout this event. However, we hope you enjoyed the whole of this event nevertheless. Finally, thank you very much and see you on the 12th International Conference on Thermofluid. Goodbye.
Thank you. Thank you.
Thank you.
Thank you all.
We take a picture together, Mas Gifari, Mas Fahri.
Oh, sure. Maybe the,
Okay, sure.
the documentation team can help us out to take a screenshot or pictures together, perhaps.
Everyone, please turn on the camera, and then maybe the organizer can take a picture or snapshots. It will be a history because of the pandemic.
So maybe to the documentation team, you can turn on your mic and help us coordinate the documentation, if that's possible. Okay, so please stand by, ladies and gentlemen. We're still waiting for the documentation team. Okay, so should I count or are you guys going to count? Okay, so I'm going to count. Right, so I will count for the screenshot or the picture to be taken. So 1, 2, 3, smile everyone. Okay, is that enough or again, guys? Okay, again, 1, 2, 3, cheese. Okay, how many more times, guys? Is that good? Okay, I believe that's good. Thank you very much, ladies and gentlemen.
See you again 2021. Bye-bye.
Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditation. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology, over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions.